In this hands-on Kubernetes Operator course, you'll learn how to extend Kubernetes by building your own custom operators and controllers from scratch. You'll go beyond simply using Kubernetes and start treating it as a software development kit. You'll learn how to build a real-world operator that manages AWS EC2 instances directly from Kubernetes, covering everything from the internal architecture of informers and caches to advanced concepts like finalizers and idempotency. Shubham Katara developed this course.
If you already know Kubernetes, you know that there are concepts and Kubernetes objects like pods, deployments, replica sets, stateful sets, services, and so on and so forth. But do you know that you can create an object called EC2 instance? No? Well, that's the beauty of Kubernetes, because you can extend the current capabilities of Kubernetes and create something which is called an operator. So you can create an operator to control things which are outside of Kubernetes like EC2 instance, which we will learn in this particular course. I'm very excited to bring you the Kubernetes Operator course from scratch. This 6-hour plus course is brought to you by Shubham, who has 8+ years of experience and working in Trivago, have trained many on OpenShift, holds multiple certifications like GCP Cloud Professional and DevOps. And this course comes as an outcome of his work at Trivago for building custom operators in production. Yes, we'll build a full-fledged working operator end-to-end from scratch, learning why it is even important, how to do, and everything about Kubebuilder, and then building it end-to-end. I'm really excited about this course and cannot wait for you to get started.
So before we can build a custom operator for Kubernetes, we need to know what is an operator, right? And before that, there is a term that is called a controller that you really need to be familiar with. Now, many of you might know already what a controller is. It's, you have heard about this, which is the Kube Controller Manager. But what does it really do? What work is it that the controller is responsible for? So a controller is nothing, but it is, think of that as a forever running loop, right? Think of this as a piece of software which we will be writing. That is a forever running loop. And if I want to write a bit of pseudo code for that, it's kind of like this. So you always run it. And the first thing that it does is it observes the state of the resource. Whichever resource you are writing an operator for, you will have a controller for that as well. So if you want to work with pods or deployment, you want to work with services, you want to work with config map, there is a operator for all of those resources. So the first thing that it does is it keeps on observing the state of your resource. If the state is updated, again, for whatever reason you updated the state, maybe in your deployment you changed the image, maybe in your config map you edited the data of the config map, whatever reason that happens, and if the resource is updated, the second thing that a controller manager or an operator or a controller really does is it compares the current state to the desired state. And this is where you put your business logic. This is actually where you define what to do in case there is a drift that is recognized. And most importantly, what not to do if there is no drift, because it's very important to make your operators, or at least your controllers, idempotent. They have to be idempotent. I cannot stress this enough. We will talk about the reconciler loop just in a minute, but this has to be idempotent in terms of if in case your resource needs no change, there should be nothing done on Kubernetes. You should be able to run your controller as many times, but it should not result into a change if there was no change needed. And if it finds that there is a drift between the current state and the desired state, it then does an update. Or you can also say it acts on what logic you have asked it to do, what to do in case there was a drift found. And then we close this. So it's a forever running loop that never stops and keeps on watching the API server for your resources that you are managing. Now, what we are going to build is a cloud. It's a cloud controller, because what we are building will be a piece of software that actually runs on your Kubernetes environment here. Let's say this was your Kubernetes, and there you say, I want to make kind EC2 instance. Let's put it this way. It goes to Amazon, sees if this instance with this name is already there or not. If it is there, it does nothing. If it's not there, it creates something. So it's kind of what we would call a cloud controller. Think about when you run on EKS, when you go to Azure Kubernetes Service, it is very easy for you to change the service definition, the SVC, for example, in EKS to have a load balancer. You can just say the type of service is load balancer. And in your EKS cluster, there is a software which is working, which is running, that abstracts how to create a load balancer, how to make your service as backends of that load balancer. It hides away the complexity for you. And that is what a cloud controller does. There may be many different controllers that cloud providers will give you in their own EC2, in their own Kubernetes distributions to make your lives easier, so that you do not have to know the nitty-gritties of it. You just say, I want a resource, and then you get one. And that is what a cloud controller manager would be. Now, when I was talking about a controller, we spoke of this term called idempotent, and this is something I actually want to explore a little bit with you. So there are few things that your code should actually be doing. When you write a controller, when you write the logic for what to do, there are some things that can actually be done. And the first thing is a happy path. So what is a happy path? You have a logic, your reconcile, this is actually also called a reconcile loop. It's here. This drives the cluster state to your desired state. And this is what it reconciles. And that is why Kubernetes is eventually consistent. I mean, in a way that you make a change, eventually, which is a very short time again, so we think it's like this, but eventually your state is going to match the desired state that you want to do. The cluster state is going to match the desired state. Now let's zoom in this part a little bit, where we have our, case one, where you have a logic, your resource got updated, and your reconcile function is then triggered. This is where, this is the start of your loop. Let's put it this way. This is the beginning of your loop. So the first thing that you do is you get your object from the request. The way it works is, when you update a resource in Kubernetes, and there's a loop that's watching on that, there's a controller that watches on that, the controller gets a request. The controller can actually get the request that you wanted, which is the API request to the API server, and it can get the object data. For example, if you updated a config map, your reconciliation loop can actually get the YAML or the JSON of that config map. So you can verify, or you can actually, see what has been changed, or what updates has been done, what has been done by the user on that. So you can get the object from that resource, and you can then observe the desired state from the spec. What you actually do is you see, you define your config map, for example, or let's say a pod. So you have a pod, and then you have a .spec in which you define your containers. So you can see how many or what spec is there for a particular resource, and then you can compare with that spec what is the actual state of the resource. If they match, if the number of containers in your pod are exactly what you wanted, then you have to just skip it. You don't have to do anything. And this is what the happy path is. You do nothing. And this is absolutely important that you realize you don't have to do anything in this case. You don't have to make any API calls. You just ignore that request to your reconciliation loop because the actual state is equal to the desired state. And that's what happens when you exit your loop gracefully. Of course, I'm not saying you will stop the loop because you have to keep on listening on the request, but you will not make any changes. There's also a second thing that can happen. So in this step, you have your function triggered, you get the actual object from the request, you see what is the spec of the object, what object is being modified, and what is the actual resource of the actual state of the resource. And this is where it gets interesting. If the desired state is equal to the actual state that you want, you do nothing. We know about this from the previous happy loop. However, if they do not match, for example, in your deployment, the current that you have in etcd is your replica 3. Now, let's take this example. This is nice. So let's say your current one that is there is replica equal to 3. And this is for a deployment which is stored in etcd. This key is stored in etcd. Now you do a kubectl edit, you do a deployment, and then you give the name of the deployment, and then you save that file. The first thing that happens is that your reconciliation loop will get this request that, okay, because I'm watching deployment, this deployment is now updated. And that is where you made the change to be replica equal to 5. What your current is 3, your desired is 5. Now you say, okay, in your spec, you will have replica equal to 5. This is what you can do when I say observe the desired state. You get the actual object YAML, and then you observe this desired state. So you want 5 replicas, and you observe the actual state, which is still replica equal to 3. So there is now a drift. The current actually does not match the desired state. And this is where your logic would actually come into the picture. What to do in case your resources are not matching to what the user has actually asked to do. So there you will calculate some differences. You will probably take some actions. You will do a create, update, delete for the resource. In this case, you will create 5 more pods. You would create 2 more pods because you wanted 5. So 3 plus 2 is going to be 5 pods, which is actual user requirement. And then there, if your action is succeeded, you update the status field and then you exit the loop again. This is very important. Every resource in Kubernetes has a dot status. So you have a spec and then you have a status. And this is how the reconciliation loop knows if it is actually matching. If for some reason you could not create the pod, for whatever reason it may be, you can return an error and then you can requeue, you can retry doing that action. And this is what makes Kubernetes as healing. It tries again. With a back off. You can configure this that if you were not able to do this right now, maybe there was no, let's say you could not create the pod because you did not have enough memory. Your pod would actually not be created, or they actually put in the pending state. This is not a good example, but let's say for whatever reason, your pods could not be created. Maybe you were missing the role-based access control in this namespace where the pod should be created. Now it will be requeued. And the way it goes is it goes back to the beginning of the reconciliation loop here. And then it is started again. And this is what happens when I say you need to requeue. Requeue means you retry that action. And this is what Kubernetes is about self-healing, because if you give the role-based access control to the, to the controller, it will be able to create resources. It's not like I tried once and I couldn't do it. It keeps on trying again and again. You might have seen this. If you have a pod which needs a persistent volume, it goes into pending if there is no PV that the pod needs. But if you create one, the pod automatically gets scheduled, it gets started. You do not have to do that. And this is the beauty of the loop that you can requeue for your cases. And this is absolutely the brilliance of self-healing in Kubernetes. Now, one thing you have to be very careful is this: there's also a sad path. And this is something you always want to avoid when you are writing a custom controller. The things are pretty much the same. So what you do is you start your loop, you got a request that somebody updated the deployment, you see what they have made the changes to, you see if actually there or not the change there is. If actual is equal to the desired state, you have to absolutely do nothing. You have to do nothing, absolutely nothing. What I mean by that is you do not have to update the resource for anything. Because when you update the resource, let's say here, let me talk about that. Now, this is interesting. The way it works is, I'll go back to the one where you had to make some work. You calculate the difference and you update your resource. Now, if that action is succeeded, you will actually be triggering, because you updated the resource, this will actually trigger the reconcile feature again. Kubernetes controllers, they do not know what you have updated. Whether you updated the spec, whether you updated the metadata, whether you updated the status, they don't know about that. They just say, okay, the resource deployment was updated here, so I will retry my actual, I would rerun this from the conciliation loop. And now, because you updated, because you created 5 pods, now your replica is actually 5. And it will now say, okay, I get the object, the replica is 5 that the user wanted, and now, because I'm running this again, the replicas have been already created, the state matches, I don't have to do anything. You have to write your reconciliation loops idempotent. And this is what it means to be idempotent. Imagine this use case. Imagine this. Maybe you got a request and your object, you get the object, you observe them. They do not actually they don't need any work. Maybe you have got the same replica was 5 and then your actual state was also 5. You do not need anything. But by mistake, you update the status of last sync. You say, okay, it's just the metadata. It does not change my deployment, right? It doesn't change my containers. It doesn't change the image I'm using, the environment variables. It doesn't change that. I'm just putting, as a good person, I want to see when this was last synchronized. And you say that whenever a request comes, even if I make no changes, I would update the status.lastSync, which actually would then trigger an API call. And you see, whenever you update your resource, it goes back to the beginning of the reconciliation loop. And this is where you would have a forever running loop. Request comes in. Okay, you got the object. You observe the desired state from the spec. I'll zoom in a little bit. There was actually no need of any changes on the resource, but you, by mistake, you are updating the status. So Kubernetes says, okay, the object the controller is looking for has been updated. So it goes back up to the beginning of the loop, and then you update the last sync again. Kubernetes says, I got a new update, done from the beginning, and this loop will continue forever. Your resource will keep on updating without having any, without any stop. So this is very, very important that you need to be very careful of not making any changes if you do not require any changes. Now, this is the foundation. This is actually the foundation of how to write an operator. The controller is the actual logic that you have to have. Now, and there are a couple of things when you are writing an operator. This is absolutely important. I think this is a good thing. You should read this. The most important question you should be asking, or your controller should be asking, is if there's anything for me to do. That means if the current state is equal to the desired state. If not, exit immediately. Do not do anything. There should be a golden rule as well that you should follow, that you should only write to the API server when the actual state differs from the desired state. Where in this case, you see here, you are like, okay, I know that the actual state is equal to desired state. I make no calls to the API server. I do not update my resource. But by mistake, you update the last sync, which is again a request to the API server to modify the resource, and then the reconciliation loop says, there's an update. Let me go back and I would restart that. I would read on the loop, and then it's a problem. So you always have to make sure that you only make the changes to the resource when they differ from the desired state. And this is also what idempotent means, that you can run your loop 100 times. If the machine is already in that state, you should not be doing anything. It doesn't break anything. It doesn't change anything if the cluster state is equal to the desired state. That is absolutely important to be taken into account. And this is what's interesting. This is what makes these operators resilient, which is they are stateless. They don't remember what they did with your resource in the last request. They don't do that. They don't remember. They don't remember if the pod replica was 3 or 5 or 7. They don't remember if you have the environment variable or not. They always check the resources. Their source of truth, if they go to the required a place, maybe you're writing a cloud operator, they go to the cloud. Maybe you're writing a database operator, which creates a database. It goes to the database, always runs the query. And this is why these are stateless. So your container, your controller can actually be killed, or the node on which it was running, it could be deleted, it could crash. The controller will go to another node. It just starts from there. It doesn't have to have a persistent volume to store the state. It doesn't know that. And this is why it can crash, restart, and still figure out if it needs to do something on a particular resource or not, because that's what you have made it to do. You have the logic that it always observes, it always checks the desired state and the current state, and if there's anything to be done, it does it. Otherwise, it says, cool, the resource is already in that state which the user wanted me to do. Now, if you talk about, this is about controllers, but what is an operator? I think you guys might already know about operator in a way, because you want to write your own operator, but let's just go through that quickly. Imagine you guys want a house. You get a house. Let's say you are living in India, and this is a very good example that I like. Let's say you are living in India, you have a house already, maybe your parents own one, and one day you decide to move to Germany. The place is completely new to you. You have never been to Germany before. You don't speak the language as well. You don't know German. Now you need a place to stay. You need a house to stay. You call a company, in this case, you call a company and the company says, hello, sir, you're moving to Germany. We would help you make sure your move is easy and simple. We have two options. One, we can give you a full furnished house. We will give you a full furnished house. And also we have another option where you can just get a simple unfurnished, I'm saying a simple house, but let's say an unfurnished house. You can choose whichever you want, and we would be happy to give you the key when you land in Germany, once you sign the forms and everything. The company also says one thing, that, sir, while we are giving you the furnished house, we also give you a helper. Now you say, what is this helper? What is it going to help me with? the company says, if at any point in time you break a tap, maybe your water filter is broken, maybe the floor is you spill something on the carpet, are you gonna fix it? Maybe your bathroom tap is broken, maybe you break a window, you never know. You don't know anyone in Germany. You will fix it yourself, or you can have the helper do these things for you, because you don't know the nitty-gritties of where the hardware store is, how to call someone if I lose my keys for the house. Let the helper do it for you. So the helper is actually someone who has the full knowledge of this house, who has the full knowledge of how to fix things if they goes wrong. You just have to tell the helper. Maybe you lost your keys. Just tell the helper, go get me a key. He knows where the store is. He has the logic. He has the knowledge of where the store is. He has the knowledge of where to go and in what language, how to speak to the person who can make you a key in German and gets you a key. If you have a broken pipe hose, he knows how to fix it. So think of this guy, this helper, as the actual operator. Now, if you want to port this in the terms of software, think about you have a database which is called MySQL. Now, for you, installation of things is easy now because you have a container, you can simply run it, and you would be able to get your software. But what about day-to operations? What about maybe you want to do a database migration of your schema? Maybe you want to take a backup. Maybe you want to take incremental backups on a particular, a schedule. That knowledge needs to be either with you or someone who can do this for you. And this is where MySQL not just gives you the database MySQL, but also has an operator for you. This operator is actually a controller running internally. So this controller has all this logic. If the user asks me to create a database, I know how to make a database. I know how to log into the DB. I know how to create a database. I know how to do that. It knows about it. So you just have to tell what to do. In this case, this helper was the operator. And in this case, this was the MySQL database product we were actually looking for. And that makes your life a lot easier because you don't have to worry about the lower level details. Now, operator has two things. One is a custom resource definition, and then the other thing is a custom resource. You know how you can do kubectl get pods? You get a response. Maybe you have pods or not. It says, yes, I have pods, or it says no pod found in the namespace. But if you do kubectl get apple, it doesn't know what this resource called apple is, because Kubernetes has its own vocabulary. It has the API resources that it has been told to remember. And those are the resources, the internal ones that are native to Kubernetes, like pod, deployment, secrets, services, all these things. These are resources that Kubernetes knows about. But what if you want to create your own resource, which is in our case, what we will do is going to be an EC2 or instance. I could also want to create an S3 bucket. In that case, I need to expand Kubernetes' vocabulary that, okay, this resource called EC2 instance, if somebody says, it gives you a YAML, which is kind EC2 instance, you know how to create, or at least you know what that is. What to do on that, that's a different story. You know what that is. So that if somebody gives on this file, kubectl create, you don't just tell me you don't know what is this resource. You know about that now. I have given you the schema of what an EC2 instance would be. I have given you this custom resource definition. So whatever the user gives you in this kind, accept it, because now your vocabulary has been increased. And this is going to be a custom resource. Whenever you instantiate a custom resource definition, that is called a custom resource. For example, if you created a custom resource definition for EC2 instance, when you create it, and then you can do kubectl get EC2 instance, what you receive is an instantiation of the definition. That is a custom resource on which, very important, on which your operator or your controller will be acting upon. So your controller knows that on a resource type EC2 instance, it has been created, it has been deleted. If you create a resource called EC2 instance, it knows that on this resource, there was an update, which is to create the resource. The controller will create that resource for you. If you delete that, the controller will say, okay, on this resource which I am watching, there is a delete operation performed by the user. So it goes ahead and deletes it for you. So without the controller, your custom resources are nothing. They are just, Kubernetes knows about it. It does not react on that. It does not acknowledge that, okay, I'm going to do what you want me to do, because it doesn't have the knowledge. So while the CR and CRD, you use them to tell what you want, the controller with them is actually the how part of it. How do I do that? And this is what we're going to be building. We will be building a cloud controller, which is for building EC2 instances on Amazon. And this is what we will be looking for. There's also something which you need to know. Kubernetes is not just a platform now. It is a complete operating system for for people. So let's talk about how Kubernetes is actually expandable and how can you use Kubernetes as an SDK. So what's very important with Kubernetes is to look at from not just a platform where you can run your applications, but rather how can you expand Kubernetes as a software development kit, and what can you do with that on other platforms. That's also what you can do. So the first thing that Kubernetes is so widely adopted by cloud providers, by on-prem, for other softwares, is because of its extensibility. Let me get a color different. So it is because of the extensibility, because of these custom resources, because of these operators, and because of the controllers. And this is what we just talked about. Kubernetes also has API first approach. So everything in Kubernetes has an API. Everything. Your pod is an API. Your service is an API. Your API server has APIs for all of these things. And that makes it very easy to write your code for. And there are client libraries for this. And that makes it very, very easy. You have the SDKs that you can build your controllers on for Kubernetes. There is Go, Python, there's Java. There is integration of JavaScript with Kubernetes because there are client libraries for that as well. And you can also, Kubernetes has backward compatibility because it does not just delete API resources, it deprecates them first. It gives you enough time to move towards a different to a different API version, and it also versions its API. So maybe you might have seen pods /v1, or you might have seen a network, network config /v1 beta 1. So this is the version of Kubernetes API. So it makes it very easy for you to develop new APIs without breaking the existing ones. And that makes it really, really simple or really helpful. I will not say simple, but helpful to expand your APIs. And this is a plugin. Everything. You can have your networking, you can bring your own CNI, you can choose from different CNIs. Quite popular ones are Cilium. I think, Cilium is one very popular from Isovalent, which is a company acquired by Cisco. You also have different options for storage, you have different options for runtimes and webhooks, where you can intercept everything as an admission controller, which could either validate your request or which can either mutate your request. I think for these webhooks, we can have an entirely different course for it. They deserve their own time because I don't do justice if I just talk about there is an admission controller which can validate and mutate. It doesn't help. So probably something to look for in the future for us. And this is why different cloud providers, because of this extensibility of Kubernetes, there are different flavors and 1,000+ tools that you can use on top of Kubernetes. So there is OpenShift from Red Hat, there is SUSE from Rancher, Tanzu from VMware, then there's softwares on top of that, which is Kubeflow, Knative, Kubevirt, which is also quite popular nowadays. And that's what makes the developers happy because they say what, not how. Now, if you are working in a platform engineering team, you want your, let's say, this is a developer. This developer wants a machine in Amazon. He wants or she wants an EC2 instance. And you manage your cloud. Let's say you are the cloud admin who will give them the EC2 instance. They come to you, you say, okay, I run some commands, blah, 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 and this is the instance, and you give them that. That's okay, but this is a very old approach. What you can rather let these guys do, and this is what in internal developer platforms would actually help you with, or you can build your own, that you can say, okay, listen, if you want an EC2 instance, you don't have to come to me. Just give me this YAML, which is, you can explain it to them. You can have a Helm chart around this that says, I want an instance where you can say the number of instances, maybe 2, the instance type, which you want, and then maybe you can have them give the instance ID, where you can then say the AMI ID that you want to use. A very simple thing. And then maybe also the port numbers that should be open. They give you this in a YAML format, and you pass this from your controller. After you can have a pull request review. So after they have a pull request, this is stored in GitHub. You have a pull request, and then they get an EC2 instance. With this, they get to say what they want. They don't care about how to create resources in EC2. They don't care about VPCs. They don't care about anything. And also, because you have a GitOps workflow now, you can have Argo CD deploying these resources, and then the controller takes care of creating the EC2 instance. Everything is as a code. You can have a GitOps ready resources very, very simply with this platform as a product, which is platform engineering all about. So you can have the declarative options. You can use Helm to help the lives of developers easy, that they can just give you this information, you render the resource, and then your controller takes care of that. And this is I cannot stress it enough how simple it makes our lives easier. Now, because you can run Kubernetes, not because, the thing is, you can run Kubernetes anywhere. And the reason why you can run Kubernetes anywhere is because of the standardization. You can run this in any cloud. You can run this on edge. You can run this, you can run AI workloads on top of that anywhere. Kubernetes is standard because it has one pattern, which is a controller pattern that rules them all. I would say DNS just works. Again, it can be problematic, but every pod knows where every other pod is. It has its own challenges depending upon how many number of services you have in a cluster, how many pods you have in a cluster. Scalability could be another issue, but for a cluster that you have bootstrapped, it just works fine. And then you have config management for your developers, which I don't think I need to talk about. The thing that I'm trying to make here is it's not just a container orchestrator. It is a complete operating system. You want networking, it has it. You want memory management, it has that. You want compute management, CPU, storage, it has that. It has disk management, it has it. So you can actually build and package and ship your software that runs on top of Kubernetes. Any sort of software that you can, you can build and run on top of Kubernetes. It's not like you're just using Kubernetes, but you can expand it with all of these controllers and these operator frameworks that we are talking about. And this is why I love Kubernetes a lot. All right, so this was about how do you use Kubernetes as an SDK. Now let's talk about how do you bootstrap Kubernetes. How do you bootstrap a Kubernetes operator with a software called Kubebuilder? And this is where our journey would be beginning. So let's go on and do some hands-on on writing an operator. So before we can build our own Kubernetes operator, we need a place to run this operator on, and that is going to be Kubernetes. Now you can build a Kubernetes cluster in GKE. You could probably use Amazon as a managed service. You can build your own clusters with kubeadm. Whichever way you want to do, it is fine, because the operator that you are building, it will be built into a container image, and that container image can be run on any Kubernetes cluster. In our case, we want to keep it simple. So I'm going to be building the operator, and I'll be testing this operator, which is going to be running on my cluster locally, and create instances on Amazon, which is external to the cluster, just to show that you can manage infrastructure that is external to your Kubernetes environment. And this is why Kubernetes is really popular, because it lets you use it as a SDK, as an operating system of the cloud, which we will also talk about in the future. So K3D is a Kubernetes distribution by Rancher, which has many other distributions like K3S, which is also a very simple, lightweight Kubernetes distribution. It also has RKE2, which is more hardened in for security if you are working in the governance. And K3D, it lets you create containers, or rather, it lets you create Kubernetes clusters in containers. If you have Kind, you can use Kind. If you have K3D, you can use K3D. If you have a sandbox cluster somewhere, you can use that as well. The reason why I'm using this local is because it's very lightweight. It does not cost me lots of resources. It's free, of course, and it's very fast because it's running on my computer. So for K3D, we can install that very simply. Just go to the installation script, and you can download that with either curl, or you can download that with wget. I would suggest you go with the latest version. And once you have this downloaded, you can do K3D or K3D version. And I've got the latest version of K3D, which is 5.8.3. And the Kubernetes version that I would be using when I build a cluster with K3D is going to be 1.31.5. But there is a newer version of Kubernetes. What if I want to use that? Better, we are DevOps engineers. We are cloud engineers. We like to have a single source of truth for all of our applications, which is why we do GitOps, right? And would it be nice if you can just version control your clusters as well? That right now, I've got one cluster which has 2 agents. Maybe I want to increase it. Let me put it into GitHub. And that is exactly what K3D allows you to do with a very simple cluster config file. And this one has lots of options, which you can go to K3D and look on the documentation. However, I've kept it very simple. This one gives me one master. K3D allows you to create multi-master, multi-node cluster. Again, I'm just going with one because I don't need high availability. And second, I'm going to be using 2 agents here, which is going to be the worker nodes. And this bit tells me the version of the Kubernetes that I want to use. And that's the one which we will be using. You also need Docker, because K3D uses Docker because it creates containers in which it runs your Kubernetes cluster, which runs containers. And that's a whole inception going on out there. But these are the 2 things that I would be using. If you have any other distribution of Kubernetes, you can very simply use that. So I've got Docker running on my machine. I've got ObjectStack, which is actually giving me Docker in the background, which is giving me a runtime in the background, I would say. And to talk about K3D, its architecture is fairly simple. So what it does is that this is how it looks like. So you have your laptop or you have your computer on which you want to create multiple Kubernetes clusters. Now, as a developer, I might need different clusters for different applications. I might want to promote them from dev testing QA just to have a pipeline going for a complete software development lifecycle, that's also possible for me too. And that is where K3D shines really well. When you make a cluster in K3D, it creates a separate Docker network for all of them. So they are completely isolated from each other, and they have their own CIDR, as you will. They have their own network in which they would be talking to. So here you can see I've got one cluster here, which is blue, and there's one cluster which is green, cluster A and cluster B. And this is the master node, and these are just robots, which is our workers, because that's where the actual work gets done. And we have these Docker networks created. Right now, if you do Docker network list, you see the standard Docker networks that are created when you install Docker. However, when you do K3D cluster create with this config file, which is our source of truth, when you do that, there's going to be a new network created, which I just showed you. So we will see that just in a moment. Once this is created, when you ask it to create a cluster, not just it creates your cluster for you, not just it sets up a gateway for you, not just it creates your workers for you, it also updates the kubeconfig, or rather, it can help you to get the kubeconfig. And here you can see my context is automatically set to kubectl. It says you can use it like kubectl cluster info. And if I do that, that's where my clusters are. That's where my cluster is running. Now, if you do Docker PS, you will see there are a couple of containers that are just started, and this is our infrastructure for K3D. We have got 2 agents, which is our worker nodes. We have got 1 server, and we also have this Nginx proxy container, which is there for some reason. And the reason why it is there is for you to talk to your API server. Because you can use K3D to create multiple masters, you need to have a load balancer. So you should not be needing to set it. That's why K3D does it for you. And here it creates a container that is listening on your port, on your computer's port, which is 5745. And that's actually forwarding the traffic to 6443 of the master, or in case you have multiple of the masters. And that's why you see the Kubernetes control plane is running on 5745 on all the IP addresses of your computer. If you go to this port, you will be talking to Kubernetes. You will be talking to the Kube API server. Now, what can you do? Every time you have a cluster, it's good to do a smoke testing, a very simple one. So we can do kubectl get nodes. There you go. You have got 1 control plane, 1 master. You've got 2 agents which are ready. You can do kubectl get service. There you go. You can do kubectl get pods, and some of them are code DNS, which is very simple. It comes with a metric server also. It comes with traffic insert, which is, again, it allows you to expose your services outside or work as an ingress, if you will. And it has got a local path provisioner, which is for storage. I talked about the metric server already. Now let's try to do some smoke tests. And if you can do kubectl create deployment or k create deploy, it's going to be creating a deployment, and it's going to create a pod, k get pods, and here you can see it's container creating. If I do k logs, and if I can do my deployment, this is a log for Nginx. This is fairly simple. If you had used Nginx, this should be nothing new. You can also expose your deployment. We want to check the network connectivity between our applications. If one service or one pod can talk to other application in the cluster, let's just validate that. So I could do, I want to expose my service. I want to expose my deployment called my deployment, and the port number for that would be 80. Here you can see it's a service resource in Kubernetes, and it has got a cluster IP. Now, if I want one application to talk to another application in my Kubernetes cluster, I can use this cluster IP, and that's exactly what we would be doing. What we would be doing is here, so here we have a pod in our new cluster for which we just created a service. I want to test the networking in my K3D cluster, so I would create a new pod. I would try to curl this service and I should get a response from this pod. And I should be able to curl it because it is HTTP. Because I know I just ran an Nginx server and this should work because it is a single cluster. You cannot by default expose your service IP addresses outside the cluster. However, inside it should work fine. And that is where we can use our trusty curl image. This lets you just do a curl to any other IP address or host name. And that's where we can do k run. I want to use, this is my container. I want to create a curl container with the name of curl. This is my image. And I want to connect on the IP address of my service. That said, let's look at the pod. This pod is container creating and it's completed already. I should back off. That's fine. Let's check what happened. And if I do logs for curl, it wasn't a crash back off. It just started, exited, started, exited, and it's like, what is going on? It was not a cron job that runs till completion. But you can see here, this is the response that you get from the service, which is Nginx. And that tells me that my cluster is ready for connection. My cluster is ready for me to build applications. And also, you can probably go to, you can also check from your cluster if you have external connectivity, because we would be talking to Amazon. Might as well check that. So we can do k run curl, or let's say Google, and I could do https://www.google.com. Do I have a pod now? Google container creating, and let's see, and that looks Google to me. Looks fine, right? So we have connectivity between our applications, and we also have connectivity now to external environments. And this is going to be the foundation on which we will be building our application. You also would be needing to have Go on your computer, which we talked about. You need Docker, Git, the standard developer tools. So that's it. This will be our setup. Now, I think we should talk about what are you going to be really building in this course, and what is the reconciliation loop? How does Kubernetes know what you want it to do? How does the controller, or what is even a controller in the first place? How do they know that I want to do something? The user has asked me to do something, and I should do that. How do they know that the state of the cluster is not matching the state of the, desired versus current state? How do they know about it? So let's learn that now. So if you want to know how to build an operator, the best thing to use is an already available framework, which is called Kubebuilder. There are also some other frameworks that help you to build Kubernetes operators like Operator SDK. However, Kubebuilder is also one of the very famous operator frameworks that allows you to write your own controllers for Kubernetes. This is for people who are using Kubernetes and they want to develop a very in-depth knowledge of how Kubernetes reacts on certain resources, how the operator loop functions, how is it idempotent, what is a finalizer, how does operators would self-heal, or if somebody who wants to extend the APIs for Kubernetes, how would you actually compare the state to the desired state? What is a webhook? How does it work? How do you implement versioning with a Kubernetes operator? That's all, which is very, very inbuilt and which is very simple with Kubebuilder. So this allows you to have a starting point without spending so much time on what is going to be my project structure. How would I, structure my code? How would I structure my test cases? How do I generate my metrics? How do I add locking into my into my controllers? Am I going to have a leader election? How do I implement a leader election? How do I expose metrics? On what port do I export the metrics? All of that is taken care by Kubebuilder. What it does is it allows you to have a directory structure in which it has the boilerplate code for building your Kubernetes operators already there. Thousands of lines. Instead of you to have to write, it allows you to focus on the business logic. It allows you to focus on what is going to be your specification of the custom resources. It allows you to tell what to do in order to, how to react in case there is a change in those custom resources. That's what it allows you to do, instead of looking at how do I start with an operator in the first place. It also lets you generate the role-based access control. It lets you generate the cube. What's it called? It lets you generate the customized resources as well, in case you want to deploy your operator into different places. It also lets you wrap your operator into a Helm chart for its own deployment, so that it can be used in any cluster, regardless of whether you are running on cloud, whether you are running on-prem, on wherever you are running. It allows you to version control your APIs as well. So for us, let's get started with that. And the first thing you can do is you can quickly install Kubebuilder. Let's go there, and installation and setup. Or maybe I look on GitHub and there should be some releases that you can download. You can also install using the installation book. There are many different ways of installing it. Either you can download it from the releases, which one is working for you. I'm using a Mac, so I have got an ARM64 because I'm using a Mac and that's my architecture. And once it's downloaded, I think you can also use Brew. I'm not sure if you can, but how can I install that? As I just showed you, there you go. So you can install Kubebuilder using a very simple command. Now, first thing that Kubebuilder needs, or what you do with Kubebuilder, is you create a project. Now, a project, think of that project as a collection of your APIs that you will be building. And it's a simple directory structure that allows you to initialize your APIs. And let's do that now. So first thing we will do, I have Kubebuilder version already, which is available 4.5.1. I think the latest one is 4.7.1. I'm not too far behind, but that's okay. So I've got the Kubebuilder, and the first thing we will be doing is we will create a project where we will be hosting, or we will be building our APIs. So first thing, Kubebuilder init, and here is the important thing. When you are building your custom operator, let's say you are working in a company called Example. You want to build your custom resources in a certain domain, which makes it easy for Kubernetes to know where this operator is coming from. If you do kubectl API resources, and if I do less here, you can see every resource in Kubernetes is actually its own identifiable APIs. Every resource that we see is an identifiable API custom API resource. For example, if I look at, let's say, AI services here, for example, hub.traffic.io/me1alpha1. We will talk about what the group version kind is, but just for you to know, you can define the domain in which your API should be declared, in which your API should be built. So for example, I could say Kubebuilder init, I want to be building things related to cloud. And let's say I work with Netflix, for example, and my products should be under the domain of netflix.com. In this case, I'm using cloud.com, and the repository in which my code would be hosted, just as a project description. What it does is it writes the customized manifests for you, so you can have it deployed in different clusters based on your requirements. It writes a lot of scaffolding code for you. And what it does is it creates you a directory structure. It writes you a Dockerfile, which you can use to build your operator into a into a deployable image. It creates you a Makefile that you can use to generate your custom resource definitions. Maybe I open this in VS Code. That would make more sense. Maybe I open this here in Cursor. That would make more sense. So it gives you a Makefile that lets you generate your RBAC, lets you generate your custom resources, custom resource definitions. It helps you deploy those into a cluster and install them from the cluster. If you are doing a local testing, this Makefile is really, really helpful. And this is where is going to be your project. This is the project information on where, what is the name of the project, what is the domain under which your project is defined, and in what is the version of the Kubebuilder project that you are using. Apart from that, and this was the Docker file that we were talking about, apart from that, it gives you this CMD directory. Now, it has already created a lot of files and a lot of folders for you. So let's quickly go through that. The first CMD, main.go, is actually the entry point of your operator, of your controller. So this already is done for you. You would have to worry about what libraries in Go I want to import in case I want to build a custom operator. Whenever I say operator, when I'm talking about controller, because that is a loop that actually does a job for us. So you would be thinking, what library am I supposed to be importing? For example, take this, the client Go and the client auth package. So this auth package is actually the one that allows you to talk to Kubernetes. It imports all the Kubernetes client auth plugins. In case you were using GCP, Azure, you want to talk to the clusters, it lets you get the kubeconfig, and this is the package that lets you work with. You also have a package for importing the Kubernetes API machinery. We will talk about API machinery in a bit. This lets you define the runtimes that are needed to define a Kubernetes schema. How do you declare a health endpoint? How do you do logging for your operator? It lets you create a lot of code base. And this is the main.go, which is the main file from which you declare your code. This is the entry point for your code. We will talk about that when we write it. You also have a lot of config folders where you define how are you going to be working with your, it has some defaults for Kubernetes, like your services, like your customized files. It has customization that lets you deploy your operator to different clusters and namespaces. It has the customization for your manager, which lets you create a deployment and the namespace in which you want it to be deployed. It's a fairly straightforward customization file. It lets you also create role basis access control. It lets you create cluster roles, cluster role bindings. So it makes it easier for you to be running your operators. Otherwise, if you are managing, let's say you write an operator which listens on a resource called EC2 instance, but it doesn't have the permission to be listing EC2 instance in a namespace. You will not be able to manage those resources in that namespace. So without you worrying about how does my role-based access control would look like, it lets you create a lot of boilerplate code. Along with it lets you create the role-based access control as well for you. It also gives you end-to-end testing, so you don't have to write your own testing suites. It lets you help. It helps you with that as well. And the one thing that is interesting with that, which I was looking for, is where did that go? Where is my CMD config hack? I think I'm missing. Oh yes, because yeah. So this is just the project resource. This is just the project as a boilerplate that Kubebuilder allows you to do. The second thing we can do with Kubebuilder, the next thing we can do with Kubebuilder is to actually create an API. And this part is amazing. This is going to be our resource this is going to be our custom resource that we will be creating. So what we have just done is what you have just done now is we declared a project called cloud.com. Now, with cloud, you have many resources to manage. You might have things like compute to manage. You might have things like storage to manage. You might have things like network to manage. Things in compute could be your, let's say, EC2 instances. It could be your AMI in images, for example. They could be your security groups as well. In storage, it could be EBS volume. It could be an S3 bucket that you want to manage. In network, you might want to manage a VPC. You want to manage a firewall rule, perhaps. So the thing that I'm trying to say is you can create multiple APIs in a single project, in a single domain. And this is what we are going to be doing. We will be building our own API, which is going to be in the compute subdomain, and it's going to be our EC2 resource. So that is what Kubebuilder allows us to do, is to create our own API. So let's do that. I would do Kubebuilder create. Here we go, Kubebuilder create API. The group is going to be compute, and kind is going to be EC2 instance. I want to create the resource. Yes. So this has created the custom resource and the custom resource definitions for me. It has written them on the disk. And yes, I want you to create the controller as well. So it downloads many different Go packages. It also creates a directory called API/v1. And this is absolutely important. This is the API, the version of our API, and we are building a file. We are building a resource called EC2 types, and that is where we define our EC2 types.code. Now, once we talk about the EC2 type.go, we can take a look at that. How does it look like? And this is where the actual business logic would go for us. This is where the actual specification of our API would look like. Now, before you can build your own Kubernetes cluster, before you can build your own operator for EC2, let's see what would this actually look like. How are you going to use the YAML for that? So if I give EC2 operator.yaml, I would probably say kind is an EC2 operator. Meta, it would have some metadata. I would give it a name. And name would be my instance. And then namespace would look like default. API version, it's defined in compute.domain.com. This is the version 1 of our EC2 operator API. And then I would have two things. So every resource you have would have a spec, or almost all of them. And then they would have a status field. And this is something which is very, very important. When you are writing a custom resource, you have to define what the resource is going to look like. What is going to be things in the spec of your resource, and what is going to be in the status of your resource. And this is what the file in API v1 EC2 instances.go helps us to do. It lets us declare our given spec for the resource that we are trying. For example, my spec would have AMI ID, and this is going to be my dummy AMI ID, and I would have a key, or I would have an SSH key. This is going to be my key pair that I want to use on Amazon. I would have a instance. Let's say I would have a type, so maybe T3 micro I want to have. And then you could have a storage, and you would have in storage, you would then say, I want a standard disk. Maybe you could say, I want a persistence, or you could say fast disk, which translates to one of the faster block devices in Kubernetes because all you want to do is you're making the developer's life easy. You're abstracting the actual details from the developers. So they can say, okay, I could go for a standard disk of size maybe 10 gigs, and fast would be of size of 50 gigs. That is the data that I need, and this would be one of the minimum things you can use for your Kubernetes cluster. And with this spec that you're giving, every resource has a spec, and that is defined for Kubernetes. It is defined as a struct in Golang. So if I look at this EC2 operator, let's say we just keep this simple. We're gonna keep these three: AMI ID, SSH key, and type. This is going to be my things that I want to use, and let me just copy let me just comment this out. Where did that go? There. So I define the spec. Now this is the spec for my Kubernetes, for my operator, and I'm going to say my EC2 instance spec will contain an AMI ID. It will contain the SSH key and also the type of the. It will contain the type of the instance that I want to be using. Now this is where it's very important for you to give these JSON tags, because when you give a request to Kubernetes about a kind of EC2 instance, it needs to marshal your request. It needs to understand what is this key and what to do with that. This key is AMI ID, this key is SSH key, this key is type. So these JSON tags are absolutely required for serialization so that Kubernetes can know this field relates to a certain required key, for example. Then you can also have the status for your EC2 instance. Maybe you want to give out things like in this one, you might want to give the phase as probably it's running. If your EC2 instance is running or not. Maybe you want to give out things like public IP, and that's going to be a 1.2.3.4. And this is what you will be putting in the status field. So I would say, if I look in here, EC2 operator, I want to have phase. I want to have phase, which is going to be a string. This is the type of string. And I want to have, let's say I want to have the instance ID as well. And I can just simply go for a public IP. So these three things are which I want to be having. Now, this is very important when you are building resources like this. An AI editor would really help you. Like you can see, I'm using Cursor. This really helps you to speed up your development. Again, you are the one who's doing the thinking. You are the one who is coming up with the spec. You are the one who's coming up with, what should you be showing in the status. However, it helps you as a very good helper. Now, you got the spec, you got the status, because these two things are absolutely important to be in a resource. Now, how would your overall resource look like? The instance, the EC2 instance, would have the type metadata and object metadata. So when you see any Kubernetes resource, this kind and API version, this is actually coming from the type meta. So this meta v1 is actually, you can see, this is a package in Kubernetes. This defines the metadata of any Kubernetes resource. This Go package defines the metadata of any resource, and has two type of, it has two structs there. So the kind and API version that we see on all the Kubernetes resources, it is actually defined in a struct in Kubernetes called TypeMeta. And this is what the EC2 instance would look like. It would have some TypeMeta. So you can see here on, if I copy this, probably this would make more sense. Let me just copy that all the way here. And this would be, there you go. So let's comment that out. Now, this is a type of EC2 instance, which is the kind of EC2 instance. So I thought that, there we go. So the first thing this kind has is the API version and the kind. The first thing the resource has is the API version and the kind, and these two things are defined by the type meta. And then we have the metadata of the object itself, and that's defined by the object meta, which contains the name of the object, which contains the generated name of the object, the namespace, the UID, the resource version, the creation timestamp. Every object would have these two structs declared inside of that, which defines what object it is, and second, which defines what is the object's metadata. And then you have the spec, where you have defined this spec, and then you have the status, which defines the status of the resource. And this is how an API is created. This is how you declare what resources are going to be in your API. Now, I don't have to tell my developers that, guys, you need to raise me a ticket so I can create you a resource in Amazon. Oh, you wanted 10 gigs. I probably gave you 15 gigs. Maybe I did not hear that correctly. Let me delete and recreate that or resize it. You do not have to do that. If I just give this to my developer, it is so much easier for them. Maybe I can have them a simple UI that lets them declare the name of the instance, the count of the instance, what storage they want. It automatically creates me this manifest. And because I already have a Kubernetes operator and a controller listening on top of that, it is very easy for me to track every request that a developer is making for these instances. Because they can be put into a version control system. They can be put into GitHub, and you can use our code CD. That makes developers' life so easy. They do not need to know about what is a fast storage. They don't need to worry about what is a standard storage. Of course, they need to know the benchmarking of it, but they don't need to know it is a persistent disk. They don't need to know the different type of storages Amazon has to offer. It is offloading from them. And that is what it makes it very, very simple. Now, things that you see here, these ones, plus Kubebuilder, object, root, true. So these ones are called Kubebuilder markers, and they are there for code generation. They are there for custom resource definition generations for you. For example, this one says this is actually a Kubernetes resource. So somebody could say kubectl get EC2 instance. Somebody could say, for example, here is where somebody could say kubectl get instance list, and that is going to be what is returned. This defines it also has a sub-resource called status, which we are defining here above. So this is what Kubebuilder helps you with. And in the end, we are registering our EC2 instance and EC2 instance list with the Kubernetes schema. This function, it uses the resources that we just created. It gets the APIs that we just declared, and it registers that with the Kubernetes schema, which is actually, this function comes from a file called groupversion_info.go. Now, this one, it's a very simple file. It uses the Kubernetes schema runtime package from API machinery and the Controller-Runtime. What these packages allow you to do is they let you declare your APIs and the kind to Kubernetes. And here you are saying that you have a group version. So you're declaring a schema group version. The group is called compute.cloud.com. Again, so you could say your domain was actually cloud.com, and then your group was compute, and then your compute.cloud.com, and then your version is v1, and then your kind is EC2 instance group. And this is how every resource in Kubernetes, think of that as a URL. Every object on the web has its own unique identifiable URL, for example. Think of that as Kubernetes. Every resource is declared in a group. It has a version and it has a kind. Every resource does that. Every resource has it. Pod, service. If I do that, maybe I could do kubectl explain service. You can see here, its kind is called service. Its version is v1. If you do not see the group, that's because it is in the core group of Kubernetes, which doesn't have a name, but it's called the core group. So is the same for pod. If you go ahead, here you can see pod is v1. So this is why you now understand when you write kind pod API version v1, you are telling Kubernetes that this YAML that I'm giving you, it is a resource of kind pod, which is declared in this group, and I want the version v1 for this resource. Every resource have a group version kind, and this code is actually adding your declared schema. It is adding your declared group into Kubernetes. So it's loading your resource your actual custom resource declaration into Kubernetes. So when you give it a YAML of EC2 instance, it knows what spec this resource has. What is the AMI ID? What is going to be the phase that is running? What is going to be the public IP that I'm going to be returning? So it knows what is your spec and status. That is what we are doing here. We create a schema builder so that we can add our own schema, and then we have this add to schema. It does add the type in your group version to Kubernetes, and that's where the magic actually happens. This is where you declare what is going to be in your resources. Once you have that, then you can also look into another directory that it has created for you called the internal controller. And that is where the reconciliation logic happens. That is where you get the reconciliation logic of what to do. So this one is about custom resource. But what to do on top of that custom resource? What do I do with that? That's given in the controller package, in the internal/controller directory. And there's a file called your API name _controller.go. What this does is it creates its own package, and it then creates your, it creates a reconciler. In this reconciler struct, it is having two, it imports two interfaces. One is the client, which gives you the actual Kubernetes client that you can use to talk to Kubernetes clusters. And then there's a schema that we can then use to convert between the YAML that you are giving and what Kubernetes knows about, what is declared in Kubernetes resources. Then you have some custom markers for role-based access control, and this is where the actual reconciliation loop happens. This is the one, this was the actual logic that makes sure your cluster state is equal to the desired state. That's the one that makes sure your cluster state would be, it reacts on the cluster state and looks on the desired state. And so this is where your logic will go. This is the heart of your controller. This is the heart of your of what you are writing, what you want to do with that. And then you return a result and an error. Now, we will talk about these two things as well. I'm just running you through the code. When we write our own as an example, then we will look into this. Once you have the reconciliation logic, it is actually adding, it's adding the controller with the controller manager. So this setup with manager, it uses the controller manager to add your controller to. I think it makes sense if we talk about the architecture, a little bit of Kubebuilder, and that would be so much helpful. So if I go to architecture, this is the one that will make so much sense, what Kubebuilder allows us to do. Oh, wait a minute. Okay. So when you run let me go here. When you run, maybe a little bit bigger would help. Let's say here. When you run a Kubernetes controller, the first thing that it runs is it runs the main.go program. If you remember, this is from the cmd/main.go, which is the file here. It starts with the cmd main.go file. So the main.go file is the one which is responsible when you build your operator into a binary. Here's the main function. That's the entry point of the operator. So let's take a look at this main file from the beginning. It's part of the main package, and it does import quite a few of inbuilt packages from Golang. However, for it to really be working as an operator, there are many more packages that are imported. And that's from the Kubernetes itself. So let's take a look on those packages. The first one that we see here, this is the auth package, and this lets your operator use the exec entry point plugins, or talk to your EKS clusters, talk to your GKE cluster API server, or using the OIDC if in case you're using for authentication. This one's responsible for making sure that your operators can use the kubeconfig or the exec entry points, and they can talk to your Kubernetes cluster. The runtime package from the API machinery is responsible to kind of, you understand YAML, but Kubernetes does not understand YAML. It understands objects, which are Go structs, in example. So this one defines schema. This one's define objects that can help you to convert your YAML into Kubernetes understandable constructs, Kubernetes understandable objects. And when you do kubectl get pods, the YAML that you get is actually converted from the pod object in Kubernetes by using the runtime package. We also have in the API machinery util package, and this would be looking like it's the same package again, but this one's defined in PKG runtime in the API machinery, and this one's defined in the util as runtime. And this one is more like a utility function that helps your operator be stable in case there was a panic, which is kind of like a fatal error that your operator got. So instead of completely crashing the process, this lets you log that particular panic and still continuing with the operator process, so it doesn't just completely crash onto you. We then have the client Go package, which is again this is I think the SDK for Go for Kubernetes, and here we are calling the schema or scheme package, and this one lets you register your APIs that you have defined, the custom resources. It also lets you define the pod services, the core constructs of Kubernetes with your operator. Or rather, think of it this way, that it gives your operator the knowledge of the predefined Kubernetes resources like pod, deployment, secret services, and also it lets your operator register the EC2 operator custom resource that we are creating. We also have the Controller-Runtime package, and this one right here is the secret sauce, which is responsible to have you or to work with a manager that can help you with clients, caches, and the leader election. This Controller-Runtime, is the one that is responsible, that gives you the tools to construct the controllers that can listen on changes on your custom resources. And then, they can handle the caches, they can handle the clients to talk to the API server. And eventually, if in case you want to have a leader election or not, that also is done by the Controller-Runtime. So if I want to talk about a little bit of the architecture of how this controller would look like, so we would have the process, which is again started from the main.go. And this main.go would have a manager. Again, you will see this as coming ahead, but here's where a manager is the one that manages two things. One, it has a client, and this is used to communicate to the Kube API server. And it also handles the caches of your requested or the custom resource that was updated. Imagine this, you want to write an operator that reacts on a change to the EC2 operator object. And that's where the EC2 operator object YAML or the spec will be stored. We're going to talk about the cache much more in the future in the video. Not right now, it doesn't make more sense. However, for me to explain the manager, it does have the client, which is used to talk to the API server. Then we have the cache. And here's where the interesting thing comes into the picture. This is what we are writing right now. Or rather, this green bit right here is our user provider logic, which is what we are using in the reconcile function. This controller is responsible for reacting on the changes and eventually running the reconciler, which is our logic that tells what to do if in case the EC2 operator object was changed, or whatever change you made to that. This is where it's going to be, this is the logic which is going to be running. You can also have in the manager, in your controller, you can also have a webhook. This is kind of like the similar validating webhook and mutating webhooks. If in case you want your operator to also solve those webhooks, it's possible to do so. Now we also have a couple of packages for the certificate watches. This is the one which is responsible when you are working with. Let me rather draw it. This will make more sense. When you are using things like Cert, or let's say you have admission webhook in your operator, you have a mutating webhook. Here you have a mutating webhook, and your Kubernetes API server, you register this webhook with the API server, and this can then talk to this mutating webhook. The API server will simply ignore or will not talk to your webhooks. I'm not going to explain the mutating webhooks or validating webhooks because this was not a part of this course. It's something, there are very good documentations that you can read about. However, when your API server talks to any of the webhooks, whether it is mutating or whether it is validating, it has to have a valid certificate. It does not talk over HTTP. You have to have a valid certificate. And a lot of times you would be using the Cert manager to issue your certificates to this service, your controller that is hosting the mutating webhook. Now, if in case the Cert manager, again, it's used to issue certificates for your webhook, and every 90 days, I think by default, it will be rotating your certificates. And in this case, if your certificate has changed, maybe you are storing that certificate into a secret, then it is given into the pod. However, if this certificate is changed, you will need to restart your controller. You will need to restart your controller pod. So eventually, the new certificate is loaded, and the next HTTP request uses the new certificate which was renewed by the Cert manager. This offers a downtime. And to fix this, we have the Cert watcher package. This one creates a watcher for the changed certificates, and it reloads them on the fly without you to have to restart your controller package. So you don't have any downtime in case you are updating your certificates, in case you updated or Cert manager did an update for your certificates. We also have the health package, what lets you expose the liveness probes and the readiness probes that you can use for your operator. This exposes the health and the readiness endpoint probes, which you can use in your deployment when you are deploying this operator. And you can say, check at this endpoint every now and then. It's a standard Kubernetes liveness and readiness probe. We also have the Zap package, which is mostly used for logging. We then have filters package in the metrics package here. And this one, I think this makes sense for me to first talk about the metrics here, and then we talk about the filters. See, when you are writing your operator with Kubebuilder, it doesn't just let you focus on the reconciler. I mean, this is what your business logic is. That's what you are supposed to be writing. However, with Kubebuilder, your operator, which is running in a pod, it by default exposes an endpoint called metrics. And this might be looking familiar to you because this is something which we use a lot in Prometheus. When you are writing a Prometheus service monitor or when you are writing a scrape config, you give three things to the Prometheus server: the IP or the service name, you give the port number of the scrape config, and then you also define the path, the scraping path. This same you can use with your operator. Kubebuilder, when you are building an operator, Kubebuilder exposes the metrics endpoint, and it exposes a couple of Prometheus readable metrics, like what is the success rate of your operator, how many times the reconciler has executed, how many times it resulted into an error, how many times it resulted into a success. So it's not it doesn't give you an idea of how many EC2 instances have you created, but rather this is more on the metrics of the operator itself. And then if in case you want to, maybe you have a requirement that my operator can create EC2 instances, but I also want to know how many it has created successfully. So, you can also expose your metrics. You can instrument your code with Prometheus Go packages. And as soon as you were able to create a VM, on Amazon, we'll look into the code in the future, in the further parts of the video. You can then increment your AWS instance count to 1 because you were able to create just one more instance. And then you can expose this to the metrics endpoint. The thing that I'm trying to explain here is it's already done for you by Kubebuilder, and by default, there is no username or password. It is open to everyone. And then you can use Prometheus with the scrape config to scrape this metrics, the operator related metrics, into Prometheus and show that onto Grafana. However, you can also then use this filters package. This lets you define some sort of authentication that this metrics endpoint is not publicly, it should not be publicly accessible. I only want to I only want to allow someone who has this username and password. I want to have some sort of authentication on this metrics endpoints, and this filters package provides us these functions where we can use these authentication gated authentications for our metrics. We then have the webhook. Again, this is the package which is responsible for you to create these validating webhooks, mutating webhooks. There are many videos available. We also did a live stream on Cube Simplify of creating your own validating webhook. You can definitely take a look at that. I'll put the link of that in the description. And this one helps you declare your validating and mutating webhooks. These are core heart of your operator. Without these packages, without Kubebuilder using these packages, it would be very difficult for you to build an operator. So Kubebuilder is really good in terms of scaffolding your project. When I say scaffolding, it means it gives you a very good blueprint. It gives you a lot of boilerplate code, which again, you can refactor. But to begin with, you only focus on your reconciler logic. And that for me, it's amazing. Now, here's where the repository where my code is going to be in the API v1. And this is where I am calling my custom resource definition, which I declared. You remember we had API, then v1, and then we had the EC2 instance right here. This was our spec of the EC2 instance. That's what we are calling in the main.go. So I am calling my my v1 with the name of compute v1, and then I'm also calling my actual controller logic, which has the reconciler, or this is where my reconciler logic will be in the future. Now, coming forward, we have a couple of variables. This setup log is fairly simple. This sets up a logger for our for our controller. And the scheme that you see here, think of this as a phone book. This is an instantiation of the new scheme function This scheme is acting as a phone book. It is acting as a registry where you will write all of your objects that you want Kubernetes to know about, or rather your operator to know about. And that's what we do here in the function init. We use the util runtime, which is available here, this runtime package. And here's where we have a must function. So what this does is, in case this must function returned an error, in case this must function was not able to register, if there was a panic, the program will stop right here. Because your operator is completely useless, yet your operator is completely useless if it doesn't know about the core API types like pod, deployment, or rather also your own EC2 instance. So we register the default we register the default API types, and you can look at that using kubectl. Let me increase the font a little bit. We can do kubectl API resources here. You see? So think of the phone book, which is our scheme. We are adding all of this to our phone book. So we are telling our operator, this is what we have available. All of this is what we have available in our in our Kubernetes cluster. And then we also add our own default, our own custom resources, which is what we are calling from the API v1. So essentially, we are telling Kubernetes that the scheme that we declared over here is an empty book. And in that empty book, using the add to scheme function, which is here given to us by the client Go scheme, we add the built-in types. So our operator knows what built-in types are available into Kubernetes. And also, we add our custom type, which is the EC2 instance. And then our registry or the scheme is a complete catalog, and that's what our operator will be able to use now. Now, here's the main function. This is where everything starts for any Go program, and we are defining a couple of variables. For example, I want to define the matrix address, on which IP of my port the matrix would be listening to. And once we have defined these variables, we also define some flags on the command line when you are running when you build this with Go build, and when you run this binary, you can give these command lines as matrix address, probe address, you can define leader election and all that. So we define the IP address on which our matrix should be served. We declare some variables, which is the path for our matrix certificates. Because just like webhooks can be served over a certificate, we can declare that our matrix also is accessible over HTTP, or it needs a TLS config as well. And that's what we can define with these variables. What is the path of our certificate? What is the name of the certificate? And the key we want to use for our metrics. The same goes for our webhook. Now, there's a very good concept that operators can help you with, or rather when you are running distributed systems like etcd, or especially when you talk about your Kube controller manager. See, that is also a controller, what we are writing. It has it's a collection of multiple controllers, but this runs as 3 different pods in your cluster, or rather it runs each one on the master in your cluster. The thing is, when you are writing a controller, it is very important of how these controllers are running in parallel, and do they all make changes or not. For instance, take if I was running 2 copies of my EC2 controller. So this is one controller and this is another controller. And there was an update which lets me create an instance. I did an update. I created an object of EC2 instance kind. There was update, and this update was seen by both of my controllers, controller number 1 and controller number 2. They both are going to go and create me an EC2 instance, and this is not what I want. I do want high availability, but it should be active passive. There should be one leader. There could be multiple replicas for high availability, but only one at one time should be running. And this is what leader election, is something that you can use. And Kubebuilder makes it very easy for you, that it allows you to declare the leader election, which is a simple Boolean. So in that case, this is also running, but this is a leader. So if in case an update statement or an event comes from the API server, only this one is seeing it and only one instance is created, which is what we want to do. The other one is there, but it's not the leader. If the leader is no longer running, or automatically it's going to become the leader, and this will be then serving your requests for the EC2 instance custom resource changes. This is what leader election means, and then you can enable if in case you want to have leader election, and you can run your operator into high availability. We define the probe address on which your health probes are available. So you remember this package, which is the health, where you declare your health endpoint and the ready endpoint on what port number they are exposed. By default, the port number I think is 8081 here, which is the health probe bind address. The command line flag, and this is the variable that is going to be responsible for it. Do you want to use secure metrics or not? And this variable, secure metrics and metrics cert paths, name and key, they are related, because you can say, I want my metrics to be exposed over TLS. And if you say that you want them to be over TLS, then you can define your metric certificate paths, the certificate name and the key. Otherwise, there's no need for that. You can also say if your operator does enable HTTP2 or HTTP, it does not enable HTTP2. And then we have a list of functions that are our TLS options. I'll make it simpler explanation as we go ahead. So we declare a couple of variables, we declare a couple of command line flags, we define some options for our logging, that this is development true. When you say development, it actually gives you a stack trace on warnings as well. It doesn't give you any sampling. If you go for production, it only gives you a stack trace on errors, and it does do a sampling for you. So if in case you are deploying this to production, that's something you should always consider development as false. Now we set up a logger. We parse all of our flags of the CLI that was given by the user. We define our options for logging. We create a new logger. Essentially, what we're doing in this line here is we are setting up a new logger with our ZAP options or with our logging options. Now, with your TLS, when you have this TLS config, it's kind of like a list of options that you can do. One option here is if you want to disable, if you do not enable HTTP2 here, in case you are disabling HTTP2, you can append that to your TLS option. So we say, in this case, I did not enable HTTP2. So for me, in the TLS options, it would be I disable the HTTP2 and I only enable the version 1.1 of my HTTP because I'm disabling the HTTP2. Now, here's where you create some watchers for your certificates. You remember we talked about these certificates for the metrics, and there could be certificate for the webhook because you can expose both of them over TLS. So the certificate could be for your webhooks, the certificate could be for your metrics, and we have a cert watcher. So essentially what happens is, let's say this is what I already explained. You have a cert manager. The cert manager renews your certificates on the disk. This watcher will be detecting those changes on the certificates. It will load them into the memory in the current pod, in the current operator. It does not restart the operator. It does it on its own. So there's no downtime. There is zero manual intervention. Otherwise, you'll have to restart your operator because your certificate was updated by the cert manager. We define our TLS options, which is, again, a list of functions that returns as the TLS config, and we instantiate a new variable. It's kind of like we are creating an alias, and this is the one. By this time, the TLS options is the default TLS options that we would be using. And we declare a new variable, and we set that as a value, so we can customize the TLS configuration for our webhook server, if in case we want to use a watcher, or in case we want to even use the certificates or not. So it's easier for us to customize. Now, if you really give a webhook certificate path, which is here, If you did give a certificate path, that means you want your webhook to actually be serving over TLS, and that's the thing. Then, if the length of your variable is greater than 0, we will say initializing webhook certificate watcher, and I will be then using the TLS as well, and I will be using the certificate. So we define a variable error, and here's where we create a new watcher for the certificate path and the certificate key. If in case there was an error, you just simply exit one because you wanted a TLS config for your webhook, but you couldn't get one. So it makes sense to stop right there. And here we are adding a new option to our webhook TLS options. This variable, it contains right now till this point, it only has one TLS option, which is disable HTTP2. If that's what we did here. By this time, it only starts with one TLS option, which is disabling HTTP2. And if you have given a variable, if you have given a webhook certificate path, we then append onto this TLS options that we do want to use we do want to use a webhook certificate. And this is the get certificate function from the TLS config that gives us the name or the information of that certificate we want to use for our webhooks. And here's where we are creating a new webhook server with these TLS options. The similar thing happens when you are working with the metric server options. So these are the metric server options where we define the bind address on which our metrics is going to be exposed. This bind address is 8081. Do you want to use secure metrics or not? And what are the TLS options? Again, by this time, we are just disabling the HTTP2. We don't have any TLS right now because if you don't give secure metrics, which is as a Boolean, if you do not give secure metrics, then there would be no TLS options. You only work with HTTP 1.1. You disable HTTP, you disable HTTP2. But if in case you did give secure metrics, you will be using some sort of authentication that your metrics endpoint is not publicly, it's reachable, but not accessible. There is some sort of authentication and authorization, and only the authorized users and service accounts can access your metrics. Now, this was the metric service options that we started with. If in case you did want secure metrics, you give some sort of authentication, and then this is the same logic that we did for our webhook certificate paths, that if in case you do give your metric certificate path, you create a watcher like we did for our webhook. There's a watcher which is for our metric certificates. Then we append the metric certificate option, TLS options, with the certificate information. Essentially, what this does is, if you did give me a certificate path, if it's not 0, the length of the certificate path is not 0, you give me the path of the certificate, I'm going to run your metric server with the TLS option that serves the certificate information. That's essentially what it is doing. So you should not get confused on what this is happening, what this is doing. I just told you. If you do give the paths of your metrics certificate, it's just going to expose your metrics endpoint on this certificate that you have given. The same thing happened here. If in case you did give a certificate for your webhook, it's going to expose your validation or mutating webhook over with this certificate information. And here's the one which is quite interesting. This is from the controller manager, from the Controller-Runtime. You see, this is the one which I just showed you. This one lets us create a manager. Within the manager, you can have multiple controllers. It looks something like this. So here I have in my main.go file, this is my operator. This is the main.go file. In here, I have a manager. Now, wait a second. This is my manager. Let's take it this way. And within my manager, then I will have my controller. And I can have multiple controllers in a manager. If I wanted to write something about this, this is my controller. This is my main.go, which is responsible for creating a manager. using the Controller-Runtime. And then the manager is responsible to, or it's our responsibility to register our controllers with the manager. And that's essentially what we're doing here. So once we declared all the variables, once we gave all the flags, once we defined all of our TLS options, once we have configured if we want to use TLS for our webhooks and metrics, and if in case we want to use authentication with our metrics or not, once all of that is sorted, we use the new manager function that returns us a new manager, which is available here. This is our manager. This variable has our manager with all these options. What is the scheme? So our controller knows about all the resources, custom resources, or the core resources available in Kubernetes. What are our metric server options? If in case with the metric server options, do you want secure metrics or not? What is the port number for your metrics that you are binding to? What is the IP address for the metrics? What is the endpoint, which is usually by default /metrics? And then if in case you have given some certificates, the same thing happens for our webhook server. Is it secure in terms of have you given certificates to that or not? And that is our webhook server. We then declare the health probe endpoints, which is a probe address that is, where did that go? 8081. This is what your liveness probe and the readiness probes will be looking into the container when they are doing a probe. And here's where the leader election. Because when you are creating a manager, the manager should know, are you looking forward to have a leader election? And you should definitely do this when you are building an operator that you want to run in multiple replicas and multiple pods. There should be only one, which is both of them are running, but only one is active at any time. So this is absolutely your responsibility, that you can enable the leader election. And then if you could not make the manager, because new manager returns you the manager and also an error. So if you could not create a manager, you give the error that I was unable to start the manager, and you simply exit. Because if you don't have a manager, you don't have anything. You don't have a controller. So that's the that's the one that looks on to your controllers. If there's no manager, there's no reason to continue. Just exit right there. And that's why we use the OS package. Now, once your manager is created, we need to register our controller, which is the custom resource, which is what we need to do here. So if you were able to create the manager, we are using, we are from the EC2 instance reconciler. We define the client and we use the manager.get schema, which tells our manager what is the schema of our EC2 instance. Essentially, we use a function called setup with manager. And this one sets up our EC2 instance custom resource with the manager, and which is available here in the EC2 instance controller.go file. This is the one which is where our reconciler logic is and where our reconciler logic will be. So it sets up our controller in here in the main.go. At this point, once we started our manager, we set up, or we add our custom resource, or we add our controller to our manager. So the manager knows that I have this particular controller. This is what I need to listen on to if any changes are done to this custom resources, and this is what the logic is, what I need to run with the operator. Now, it's also interesting here, if in case you were having some certificate watches, if this was not nil, you add the certificates to your, you add the certificate watcher to the manager for your metric server, for your webhooks. Again, we don't use certificates right now. And I'm also not using any webhooks for mutating or validating. So I'm not going to do anything, any certificates for me. It's going to be empty. Otherwise, you will be adding the certificate watcher to your manager. So manager has a couple of things. It has controllers. It has another controller. You can have more than one. It will then have the watcher as well for the webhook certificates. It also has a watcher for the metrics certificate. And it watches and renews the certificates or reloads the certificate on the fly, so you don't have to restart your operator. From the manager, we also get a function called add health check, and this is where the health check is being done. We add two health checks or two endpoints. One is the /health, one is the /ready. And this is what you can use, like a fairly simple Kubernetes health check that lets you see if your operator is healthy, if your operator is ready or not. And here from the manager, which was written by the new manager function, this manager has another function called start. And this is the one that starts our manager. It's kind of like you got a car which has an engine, which has a mechanism for the airbag. As soon as you turn on the key, the whole thing starts. So first thing is your engine starts, it starts sending power to other components. This is a similar analogy when you are starting this particular manager. So the manager starts, and then it starts the other controllers inside of this process. It starts the watchers, and everything comes into life. Now, of course, if you were not able to start the manager or create the manager above here, so either you were not able to create a manager instance or start the manager, we simply just exit, because without the manager, there's nothing that is available. So I think this was a whole main.go file. And what I wanted to also show you here is we do import quite a lot of packages. We do import quite a lot of Go packages around here. One of them is compute v1 in our API v1 directory. And here in the spec, this spec matches to our, where that go, config CRD basis, the CRD around here. See, whatever you give in your custom resources spec, that gets reflected into a resource called custom resource definition. And here's where you're telling Kubernetes, this YAML file gets installed into Kubernetes. It's a resource that tells Kubernetes about other resources. It's a custom resource that tells Kubernetes about other custom resources. So you tell Kubernetes that I'm telling you about another custom resource who looks something like this. Its version is v1. Its name is EC2 instance. It's a list of, it's the namespaced scope object. It is under this particular group. And here's where the spec for your EC2 instance. And you can see here the same one-to-one mapping. We have the AMI ID, we have the instance type, we have the SSH key, and we have the storage, which is again given here. Now, at any time, when you are writing a spec for the API, you might want to change some things. Imagine you could say, I want to give a tag. Or you would say, I want to give a department. And this is going to be a simple string, which is what you can use as tagging, So when you create an instance, you use this department value to add that as a tag to your EC2 instance. And whenever, it's very important, at any time when you make changes to your specification, you have to run the make command. More precisely, you need to do the make manifests, because your CRD is not aware that you just make changes to your specification. The CRD is still older. Think of this as now it's outdated compared to the spec where we added a new value. Do I have a department here? I don't have that. I can't search for it. Okay. So once you make changes, we do make manifest. And as soon as we do this, you see a new department spec is now added, which is type of a string. You can also say, maybe I want to add project, which is going to be another tag. And then again, I will need to use the make manifest, because as soon as I do make manifest, you can see on the right side, it's going to be added here. You see, the project was again added. So at any time you make changes to your spec, your CRD needs to be updated on the disk, which is with make manifest. And you also need to update the CRD into Kubernetes, because see, the flow looks something like this. This is you. This is the spec and you make changes to the spec. Now, this all is happening on your computer right here. This all is happening on your computer right here. And wait a second. Okay. So this was a spec that you changed, and you changed your CRD on the disk. However, the CRD doesn't just need to be updated on your computer where you're developing. You then have this Kubernetes cluster, which is again where you need to have a CRD, and from where you can then create a custom resource. We talked about it. The CRD now, and from that you create a custom resource. Now you see, you made the change and it's updated here. It's version 2 of the CRD, but you are still using an older one. You're still using a version 1. So you can use make manifest in the make file, which is given to you by the Kubebuilder. You can do make manifest. It updates it on the disk. And if you are pointing to the right Kubernetes cluster using your kubeconfig, the environment variable, you can then use make manifest and make install. It is then going to apply the same CRD which was generated by the spec change all the way to your Kubernetes cluster as well. So they're always in sync. You're not thinking, I made the changes to my spec, my CRD is updated, but when I try to make changes here for this new change, I want to add a new field called project. It says there's no field called project, but I see it here. That's probably because you did not update your CRD in the cluster. You only updated that on your disk, and that's not going to cut it. So usually, if I ever make changes to my spec, I do make manifests, and I do a make install. So I update this on the disk, and I also install this. Make sure you're connected to the right cluster. Otherwise, if it's a different cluster and the resource, the custom resource does not exist, it gets installed there. Or if it's there, it gets updated, and there could be some breaking changes that you're introducing. So be very, very careful when you're doing it. All right. I think this was a whole explanation of the main.go, which is probably something you will not use a lot. You will not make changes to, but it's absolutely important to know all these options, what the webhook watcher does, why do we have so many packages involved. You can expose your metrics endpoint securely. When I say securely, I mean with an authentication, and you can also use TLS or not. This is something optional, both of them. The same goes for the webhook endpoints. So it is something which is absolutely important to know, that you can also do the leader election, and this is the main function where your operator starts. So now that you have a very good idea of the main.go file, which is the one that starts everything, let's see how the reconciler works. Let's see the reconciler in action. We will make changes to some custom resources, see how our operator gets those changes, and then what can we do on top of that. This is what we will be laying as the foundation of creating our operator that reacts on the changes of the EC2 instance object, and then we will move on ahead from there. Okay. So whenever you want to write your own custom operator, the first thing you need to ask yourself is, what kind of resource are you going to manage? In our case, it is going to be an EC2 instance over on Amazon. We are writing an operator, we are building a custom operator that goes to Amazon based on our behalf, and it creates you an EC2 instance. So something would look like this. You're going to have your Kubernetes cluster in which you have your operator running, and there is going to be a human, a certain someone that gives you a YAML file, because we talk to Kubernetes via YAML. The interesting thing about this YAML is the kind that you have declared. It's going to be the API version that you have declared using Kubebuilder, which is cloud, which is a compute, I think, which is compute.cloud.com/version 1 of this API resource. And the kind in this case is EC2 instance. Now, of course, in the end, what's happening, you give this YAML to, let's say, the Kubernetes API server, because it knows about the EC2 instance, which we will deploy our custom resource definitions to Kubernetes. This resource change, maybe you say, I want to create a resource of this kind. The controller in here will look on this change. It will get the data from the API server, and this is the one responsible to go to Amazon and creating you an EC2 instance. This is the one responsible for making the authentication with EC2. This is the one which is responsible to provide the minimal set of instructions you need to give to Amazon when you want to create an instance. This could be the instance, it could be the instance type that you want to give, which is absolutely required. This could be a security group you want to give, which I think is absolutely required. You also would definitely need to give some storage on how much your machine would be needing. Some things could be required. Some things could be optional. For instance, tags. They are completely optional. You can give that, you cannot give that. It is up to you. So when you are writing an operator, you are writing a custom resource like this, it is on you to have some minimum, at least most required things that you want to send to Amazon. And this is where when you are designing your spec, because when you give your YAML, you will have kind API version, then you will have a spec, and then you will have a status. So this spec, this one here, is actually matching what you give in your YAML up for other resources. And that is what you will be having. So in this case, your YAML would look something like spec.AMI-ID. This is going to be the name of the key. Then SSH key, instance type, and instance subnet. We are using these JSON tags so that Kubernetes can unmarshal. It knows what is this particular thing that you are giving me called an AMI ID, what to do with this particular object or with this key in the request that is coming to the API server. We might want to extend this in terms of, let's say, in here, for example, storage. So I am giving, I also have an option called tags in my YAML, which is going to be a map of string and string. And you can also create your custom struct types. For example, if I give storage, and then I can have a custom object here, you see, we know what is a string, Go knows what's a string, Go knows what's an integer, Go knows what a Boolean is. It doesn't know the embedded type of storage config, and that's the problem. It says it is undefined. So you can define another struct, which is going to be type storage config, storage config, and there you can give, the size of the, and that's what I love about these AI editors. So you can give the volume size, you can give the type of the volume that you want. Amazon have different type of volumes there. And then if in case you want to give your device a name, you don't want that. The only thing I would like is a size, and it's going to be the type of the device that I want, which is going to be one of the Amazon provided ones. And then you can also have additional storage, which is in here in this case. One is the root disk, and then you can have additional storages. You can have additional blog devices, and this is where this omit empty comes into the picture. It's very, very handy. The same thing could be done for our tags as well. The thing is, sometimes these options are, these things are optional. You can give a YAML for Kubernetes that creates an EC2 instance, but you may have tags. You may have additional storage. You absolutely need the instance type. You absolutely need the AMI ID. That would be wrong if I do, in here, if I go and say omit empty, this is wrong because it has to be a required field in your YAML manifest, in your resource. So you can choose when you are building your spec as into what things you want. In this case, the additional storage is a string, or it's a list of storage configs. So you can add additional storage configurations. In my case, I would keep the additional storage just as a type and a string. The same thing can happen for your status. So when you do kubectl get status -o YAML, what you see is the status dot, you will see the phase in which it is, you will see the instance ID, you will see the public IP. This is probably the information you get back from Amazon. Imagine this. If this developer gives you a YAML, let's say you are building an internal development platform, you want the developers to query the resource that they have created when they do kubectl create -f, which has an EC2 instance, and then when this guy says kubectl get EC2 instance, you need to give him some information, or you need to give her some sort of information. Probably the first thing you want the user to know is the state, if the instance was failed, if it was running, if it was pending, whatever state it was. And then you probably won't want to give them the public IP of this instance. If in case you allow, your organization allows for the instance to have a public IP, you will do that. The only place you can get this information is from Amazon. So when you are creating your instance, in this case, you want to poll if it's running in certain time. If it's not, you fail the operation. Otherwise, what you do is you get back some information, and this information is going to be the state of the instance, and then it's going to be a public IP. In our case, this is what we care about. There will be many things that can be given back as an operation of creating instance, but that's not what we care about. We want to show the user that in their status, they can see the phase, which is going to be a string, the instance ID, which is also a string, and the public IP, which is also a string in our case. Now, whenever we build, whenever we make changes to our API spec, I told you that it's absolutely important that you run the make command from from the root of this Kubebuilder project, so that it generates you the custom resource definition. What has happened? Wait a second. All right. So when I do in my API version 1 EC2 instance types.go, actually it's in config CRD basis, and then compute cloud.com EC2 instance. This is the actual custom resource definition that you have created. When you make changes into your spec, like in here, when you make changes into your spec, what happens is when you run the make command, Kubebuilder code knows how to write the custom resource definition as a boilerplate. And this is where you define the group for your resource. This is where you define the kind for your resource, and then you define the version of your resource. So this would tell you that for a single kind of resource, you can have multiple versions, because you see, it's a list of versions that are available. So you can have EC2 cloud.compute.com/v1, then this schema would apply. Cloud.compute.cloud.com/v2, another version of the schema would apply. And this is why you probably might have seen that this particular key is only available in a newer version of your YAML. There could be some key which is only available in the newer version, or in the older version, it was only available in the older one, because in the version 2, that might have been removed. The important thing is the spec in here. So we have got our properties. We have an AMI ID, we got our instance type, we got our SSH key, and then we got our subnet. And these all are required because we did not give the omit empty. But now, because we made some changes into our spec, I absolutely have to regenerate these manifests. And for that, I can simply do make manifests. So what that will do is it will be updating your custom resource definition with a few more, with a few more parameters. For example, one of them is the additional storage. It was not there before, but now it is. So then you can have an additional storage. And then there's a new option also called storage. And there's a new option as well called tags, which is a type of string. So every time it also updates the required, because some of them do not have commit empty. They are absolutely needed. This is how Kubernetes knows that this particular key is not available in the YAML. I have to cry about it. I cannot let the user give me this request because the custom resource definition has marked this particular string as required, this particular key in YAML as required, but the user has not given me that. Now, this is what you will give to your Kubernetes cluster. Before you can create an EC2 instance, before you can do anything with the operator, the first thing you need to do is you need to give this to Kubernetes, because if you do not, then when the developer creates a YAML of kind EC2 instance and then the API version, which is cloud.com, Kubernetes has no idea what is this, what this resource that the user is talking about. What is this group called compute.cloud.com? In version 1, I don't have a resource called EC2 instance. And this is something you can either use a kubectl apply with this custom resource definition YAML, or you can use make install command with the make file. That's something what is actually done for you. So you see, we use customize to build our custom resource definition, and then we apply that to kubectl apply -f and on the standard input. And this is where we now have our custom resource definition. Let me first do make uninstall to see what happens. If I do kubectl get EC2 instance here. See, if I do k get EC2 instances .compute.cloud.com, or if I just do tell me how many EC2 instances do I have, Kubernetes says I don't have that resource. But if I do, okay, I'm going to deploy you, or I'm going to give you a custom resource definition, at least don't say, I don't know what that resource is. If you have that, give the user. If you don't have that, just tell them, I do not have that resource. But don't just say, I don't know what resource are you talking about. So this is what you do when you give your, when you do a make install, creates your custom resource definition, which if I see, here you can see, this is, you can do a CRD you can do a get on your CRDs, and this is the custom resource definition that I have, which you actually can also see like this. And this is the same thing that I just showed you on Cursor, so which is not on Cursor, but in terminal. So that's how one would actually update, create the custom resource definitions. In my case, how would the YAML look like? So if I would probably ask, my AI that, okay, take this spec and give me an updated YAML for this resource, it's going to just spit out how the YAML would look like. And see, this is additional to what's going to happen. I'm just going to accept that. Here we go. So this is how your YAML would look like. It's going to be a kind of EC2 instance. Then you see some specs are there. It tells you, you would have an AMI ID, the SSH key, instance type. Maybe when you give this to your developers, you might want to make it a lot simpler, or at least make things like instance type or a VM preset, something like that, if they're more familiar with those words. Maybe you can do SSH key. That makes total sense. I think this does make sense. It would have been better for other examples, but in this case, the YAML is perfectly fine. So I would say, okay, this was what I wanted to show you as a YAML. In our case, the next thing that you would do is, once you have your YAML defined, once you have everything defined, now we need to look into the reconcile loop. See, by this time, Kubernetes knows that it has a custom resource called ec2.cloud.example.domain.com in version 1. There's a resource called ec2. Now, if someone gives it a EC2 instance, what to do on that? If someone gives it a YAML that please create me an EC2 instance, what's going to happen? How would it react to that? And this is where we will be looking into our reconciler loop. So let's get started and let's see how we will build a reconciler loop. So our reconciler loop would look something like this. It's under internal controller ec2 instance underscore controller.go. This is where the magic happens. This is where whenever you make changes to your custom resource, that's the place where it comes to. And then this is where the logic you would be given to operate on the resource that has been changed, which is your custom resource. It is in the package controller. It is importing quite a few things. One of them is Controller-Runtime. This is absolutely important, that handles the runtime of your controller. And also, you see, it is actually getting our own EC2 instance. This is going to go to github.com. In here, operator repo, API v1, and then it's going to call this as compute v1. Essentially, what this is doing is your controller needs access to your spec of the custom resource. It could also have been very simply done, but I could say, please go to API v1 because I have that locally available. Or, okay, I think it's better because I have it already on GitHub. So what's going to happen is if I show you, if I go to github.com, and here is going to be my repository. Let's go to GitHub. I should have just copied, otherwise it goes to Golang, operator repo. Here you can see an API v1, and this is where it's looking for the ec2 instance underscore type.go. This is where our code is. So this is what Kubernetes operator will be using. The controller will be using to map your request to a particular known data type, to a particular known spec or status of the custom resource. This is the heart of your object that you're creating. It creates you a reconciler, which is using the client runtime that helps you communicate to the Kubernetes API server. It has a schema object, which registers your schema. Couple of Kubebuilder markers, I think. Yes, it's a marker which is creating you the RBAC rules so that you can work on the custom resources. Because when you create an operator, it would be running in its own namespace. But if a custom resource is created in a different one, the operator needs access to see in that namespace as well. So this is where the RBAC is extremely, extremely helpful. Now, what can we do with this? This is the reconcile function. This is the one where all of your requests are going to be looked into. This is where all of your, whenever you do a kubectl get or kubectl apply, this is where the changes are going to be looked upon. This function has it returns two things. First, it returns the result of the reconciliation. And second, it returns the error in case if there was any. If there was no error, it will simply return a nil. Now, this is the beauty of Kubernetes self-healing. You know how if you create a pod which has a persistent volume claim, but that PVC is not bound to a PV yet, that pod is going to be in a pending state. It keeps on being in a pending state. But as soon as you create a PV, as soon as you add it to the persistent volume claim, the pod is then automatically started because there was a requeue going on for that particular pod. The reconciliation for the logic for the pod kept seeing if the requests are fulfilled. If they are not, I give you an error and I start the reconciliation again. It puts it in the queue to reconcile. This is the beauty of self-healing it will be done eventually once all the conditions are met, and you don't have to trigger that reconcile. You don't have to trigger another run of the reconcile loop yourself. Kubernetes does that for you, and this is where you will be giving your logic. The first thing that you do, the very first thing that you will be doing is you need to operate on that instance. For example, the basic thing when you talk to your, when you say that users can then create an EC2 instance of their type, you want the user to give the name of the instance. You might want them to give the tags of the instance. You might want them to give the storage config. So you need to extract this information. You need to extract this information from the request, from the API server request that came to the reconciler loop, so that you can use this information to talk to Amazon in our case, because it's a cloud operator. So you need to store, or you need to get all these objects that are being given in this YAML by the user in certain variables, so you can iterate on top of that. So this is very important. The user is actually creating a resource of kind EC2 instance. You also need to have a variable of kind EC2 instance, so that Kubernetes, you can use the Kubernetes schema to store your actual keys in your variables. Think like the user is sending a circle, you need a mold that can hold the circle. If the user is sending a triangle, you need a mold that can hold a triangle. If a user is sending an int data, you need a variable of type int. The same thing happens. The user is sending the data of kind EC2 instance. You need a variable that will be of kind EC2 instance. So let's declare that first. The first thing I do is EC2 instance object EC2 instance object is actually here. So I'm using the compute v1. This is the compute v1. And in here, I have declared the EC2 instance. And there you see, this is essentially what we created in our types.go. Now we do have a spec, then we have a status, but essentially this is the root of our Kubernetes object. The EC2 instance will have some metadata, it will have some object metadata, it will have the spec and then the status. So this is what we are calling and creating a variable in our reconciliation object. Then what you can do is, because the API server will be sending a request to your controller, or rather it's the other way around, the controller will listen if there was any changes done on your custom resource. And then you can iterate on top of that. So you create a variable of type EC2 instance object. I would rather make it simple just to keep it EC2 instance. And then we can use the get function. What this get function does is it uses the context, which is of your request. More importantly, it gets the namespace under which this resource was changed. I'm not saying created. I'm saying it gets the namespace of the resource in which the update happened on your custom resource, and the actual in-flight YAML, the actual context of your YAML is then going to be stored in this particular object in the EC2 instance. So think of this as you take the YAML from the user and you give it to your reconciler. So now it knows the namespace in which this object was updated, the instance type this YAML had, the storage type this YAML had, the number of tags the user wanted, that you can now create on top of this. So I would want to say, let's say log. There was also, I think before this, there was a logger that we can also use. So here you can see we have a log function, and we can say, I want to log all of my requests, and using log.info, I can do that. So I create an object of type EC2 instance, and this is the EC2 instance type. I get my object, which is coming from the in-flight request, And then I'm saying reconciling EC2 instance. And you see, I can get the name of that particular resource. Rather than info, let's just print this for now. So I would say I want to have an EC2 instance, and then I can say print lm. I got a request for an EC2 instance in the namespace, and then I could say, and the EC2 instance is EC2 instance. Just give it like that. You can also probably then say fmt.println, and you can print the entire spec if you want. I don't want to print the entire spec. I would just say I got a request for an EC2 instance in this namespace, and the instance is instance.name. You see, these are all the options that you can. Oh, wait a minute. Here it is. And the instances are here. I can say, and the EC2 instance. Oh my God, wait. So let's do that again. I want to just see the data that has been given to me. And I can say, I got a request for an EC2 instance in the namespace, and let's keep new printlns. The EC2 instance name is EC2 instance.name. And I would say then the instance fmt.println instance type is EC2 instance.spec. And you see, this is the beauty of the AI editors again. Now, you can see I am able to get all the information which was sent, which was watched by my reconciler, by my operator under EC2 instance.spec. And you can see AMI ID, SSH key, subnet tag, storage, additional storage. This is essentially what you were building in the spec of your custom resource. This is a one-to-one mapping. That is why we created a variable of type EC2 instance, and then we got the in-flight request that we received from the API server, and then I'm saying I got a request for blah blah blah. The only thing I do not have, see, I have the instance ID, I have the AMI ID, SSH key, subnet tag, everything. I don't have the name for my instance. And actually, this is the name of the object that I'm giving. But maybe I want the user also to give the name of the instance. And I would simply say instance name, because instance name could be different than the Kubernetes object kind, metadata, the YAML that you give, they would be different. And here I can say my name would be in the spec, spec.instance name. It's going to be a capital spec. Now, the important thing is I just added another object in my spec. My custom resource definition that is right now in Kubernetes, it has no idea about this new instance name. So I would have to do my magic again. So I would do make generate, make manifests, and then I would say make install. So that my Kubernetes is now updated that there's a new resource called, there's a new key in the struct for the spec, which is called instance name. And that's it. Now, once you get the data, once you iterate on top of that, in my case, I'm just printing it right now. But as we move forward, we will use this data to talk to Kubernetes, and then I will create myself an instance. That is where you would have your actual business logic. What we will then do is, once you have used the data, in my case, I'm not changing anything in the object. There was a resource created. I got information about this, but I'm not updating that resource. So then in that case, I will be returning a result, which is going to be, is if in case you are spending, it contains the result of the reconciler invocation. If you go to the Controller-Runtime on Go on the Go compiler, this result actually contains two things: whether to requeue this or not, and this is a default to false. This is very important. When you exit your reconciler function, you need to tell two things: whether there was an error in the reconciler function, and is there a requirement to rerun this reconcile loop. You only remember, we talked about this in the previous part of the video, that you only reconcile, you only rerun the reconcile loop if you have updated the API object. We are not doing that right now, so we do not need to send any reconcile boolean, which is requeue as boolean. By default, it is false. So in our case, we don't have an error, and we are also sending a false for the reconciliation. This reconcile loop will not run again. It's kind of like when you start with the reconcile loop. So this is how it looks like. You have the reconcile function. A request came over to this function. You made your change. You made your business logic, whatever you wanted to do. In our case, I'm just printing things. I'm not creating an EC2 instance. I'm not updating my custom resource with the status of the EC2 instance creation. I'm just printing this. So because here should be a bit bigger, change made. So in my case, did I make a change into the custom resource, that request came to me, which is in the EC2 instance? And I would say no, or you could say a yes. In case you have no changes, you would simply return nil for the error and then false for your reconciliation. If you did give a yes, if you made some changes, then you have to return a true for the reconciliation. And then if there was an error, you will return the error. If in case the error was nil, you will return the nil. This part we will talk about coming up. But for now, I'm not returning any, I'm not changing anything in the EC2 instance object. So I'm just returning a false. Now, at this point, guys, let me do l.log, and then I would say, let's do here, reconciling EC2 instance is the name, and I would here say reconciled EC2 instance, and this is the name of my instance. Now let's get a YAML and then see how this will be functioning. Now this is the time we run our operator in Kubernetes. Now we can make a container image. We can, push that container image to a registry and then get it from there. The good thing about using a Kubebuilder is when you have a working development environment and you have a kube config, which points to operate on your Kubernetes cluster, you can just run the main program locally, and then it will be as if like it's running in your Kubernetes cluster. And I will again call my trusted AI to use the spec and give me a dummy YAML so we can create that. This is the spec. Let me quickly get this. And then I would say, please undo everything. I don't need that change. Cool. So let's say Kubernetes. Do I have a folder called Kubernetes? No. Let me do an example. Instance.yaml, and there is our spec. Before spec, we have API version, and then we have a kind, and then we have a metadata, and there you see, you then have a spec. The API version is v1, the kind is EC2 instance, and the metadata, the API kind is API version v1, but it's compute.cloud.com/v1 EC2 instance. Metadata would be name, Kubernetes object for EC2. And there we go. This is simple, what we have. And then I would say, let's run our operator. Now we can do go run cmd main.go, because in the cmd folder, wait, where did that go? Here. In the cmd folder, you have your main program. This is the entry point. In any Go code, your entry point is always going to be the main.go file. This is the one that registers your schema from Kubernetes. This is the one that creates a client so that you can talk to Kubernetes. It registers some, some booleans, some flags, if you will. We'll clean this up because we don't need a lot of that. We already have gone through this code. The most important thing that it does is it starts the manager here. Enable. But I think we did see somewhere that it was starting the manager. Wait a second. This is the new manager function. Just gonna give the manager new. Where was that? Here. So we're gonna have a log of starting manager because we did not work with the webhooks. We don't have any readiness check, liveness check, nothing. So we should just see starting manager, and then we should we will be seeing if we get any requests on our controller. So here we will be exporting the kubeconfig. Let me increase that font a little bit, and here I would run my function. If this is a little bit small for the font, please bear with me. I hope this is seeable, but essentially what I'm doing is I'm running the main function now. So we will be running our operator. Do I have any EC2 instances? No. Do I have them in any namespace? No. How does our example look like? So if I do k-f example, wait, I need to go to operator folder here, and then I can do k-f example instance create. Let's do a dry run, see if our YAML was good, and there you can see the YAML was fine. Then I can just simply say, first I run my program in here, and this is how your Go code will be running. So you see, this is all what Kubebuilder does for you. You do not have to set up your authentication with the API server. You do not have to set up your, how would you run your controllers? How would you run your multiple operator loops that you have for different API versions? It does that for you. It starts an event source. So it's kind of like the listener for your object in Kubernetes. And here it's starting a worker, or there's a controller for EC2 instance. This is the group, and this is the kind, which is EC2 instance. So it's kind of like you have one controller for one resource. It is a one-to-one mapping. You can have multiple instances of that controller, and in this case, you would do a leader election, because if one object, if one instance is managing your request for that custom resource, others should not do that. But in our case, we only have one replica, but we have one controller per object. If I was creating more custom resources, let's say right now, I have an EC2 instance. This is my custom resource. For that, I have a controller. My controller here, you can see, it's called also EC2 instance. If I was to create another custom resource, which was, let's say, a storage bucket, maybe I want the users to be able to create buckets in my Amazon account very easily. There would be another controller, which is going to be then storage bucket. They could be running in the same manager, or operator pod. I think this is where you can review the part of the video before where we talked about what is in the operator. There's a manager, within manager, then you have multiple controllers. but it's a one-to-one mapping to the object and the controller. Think of this: if anything happens to this resource, this code will apply. If anything happens to this resource, then this particular code would be applied. Now is the moment of truth. Would something happen if I simply just say, please create me an instance.yaml? I should see something in here. That's what I am more concerned about. So let's create that. Of course, it's invalid. I cannot have, oh, there you go. So it says the kind is invalid. It must be EC2 instance. Of course, in the dry run for client side, so much example here, my kind was wrong. And then if I do a create again, you see, there is my request. I know that the instance name is my EC2 instance. This is Kubernetes now knowing about this. This is our operator knows about it. So it started the worker, Kubebuilder started the worker, and this is our code. From here till here, this is our code. We get the log, which is reconciling instance, and you can see this is the code which is started here. Reconciling instance name, and then we get all of our code in here executed. I got a request for an EC2 instance in the namespace. You see, it gives you the namespace default, and then the object name as well, which is a request.namespace. This is telling you that the namespace as well as the name of the object that you have. The EC2 instance name is, this is now reading the spec, and you can see tags are, it's giving you a map of environment. Dev owner is Alice, which is, this is what in your YAML looks like. Example and instance. So essentially what the user gave, my program, our operator, our controller, most importantly, knows about it. You see? So my storage would be size 50 and then type GP2. It's actually just printing this as an object map, but we can do that even better. For storage, let's make some changes. I want to say storage size is 50 and type is GP2. So I could say storage size is, you can say is size, and type is, you see, storage.type. You can obviously access any sort of object that was there in your spec, like this, storage.size, because this is how you access YAML. So I would say spec.storage.size, and that's also what's happening, spec.storage.size, and same for the type. You can also do a delete. Now, see, this is very, very important. This bit executed when we created the resource. When I delete that resource, you see, my reconciliation loop started again from the very beginning. This is absolutely, absolutely important. Whenever you make any changes on your object, the reconciler starts from the very beginning. It does not know whether you created the resource, whether you deleted the resource, whether you whether you updated some metadata annotation. It has no distinction of what did you do. It knows about the update that has happened. And this is where it is your duty as someone who is writing the operator, someone who's writing the controller logic, that you can make changes. You can run your reconciliation loop many times, but if no change was required, no change is actually made to your object. Which in this case, you can see, because the resource was deleted, we don't have any EC2 instance name, we don't have any instance type, nothing. But the loop ran completely. And here it says reconciled EC2 instance, blah, blah, blah. Something more evident would be when I just show you, let's say, the name of the instance. I want to get rid of all these things because I want to keep it simple. Or rather, I would say fmt.println got a request. Simple. Or update was made to the EC2 instance resource. I'm not saying the name or anything. I'm just saying that there was an update made, and this is why I am called or reconciling. That makes no sense. Now, I will run this again. I stop my program, and this is the beauty of stopping the program when you are building this with with the Kubebuilder, because it has a graceful shutdown. It doesn't just stop the program abruptly. It has a graceful shutdown, and it helps you cleanly shutting down your manager. Because I made some logic changes, I'm now starting this again. Main.go, and then I would say k-f create. So here you can see it says update was made to the EC2 instance resource, and this is why I am reconciling it. That's the main logic here. And then I got the instance type, which is T3 medium. If I maybe make some changes to this EC2 instance, let's say I want to add a metadata. I want to add a label here. So I want to say labels, and I would say hello, world. I save and exit. You see, I got another line. It's not like I created the object. It's kind of like I only updated it. So you see, I was not making a change as in I was creating that resource. I just edited that. And that was only a simple metadata change, which was the labels. But my code ran again from the very beginning. What if I add some annotations to my object? If I do here, let's go to my annotations. And I would say hello again and world. You see? The whole reconcile loop runs again. The thing that I'm trying to tell you is whenever you make any changes in your object, in your custom resource, the whole reconciliation loop will run always. What if I maybe remove my label that I had added or remove the annotation? Save that again, you see, running it again. Kubernetes does not differentiate whether it was a metadata change, whether it was a spec change. It does not do that. It just simply goes ahead and says, okay, you changed the resource and this is the update. This is why when you make changes to things like, let's say, your instance name or instance type, the reconciler finds this. This is the beauty how a reconciler would work. Whenever you make changes, let's say in your instance type, you make a change from T3 medium to T2 micro, the reconciler has no state. First of all, it does not remember that before it was T3 medium and now the user has asked for T2 medium. It does not remember the past request. It knows the status right now. It's in the HCD. But in this case, let's say when you are going and when you are saying that my type for the instance was T3 medium before, and you change that to T2 medium, this before is stored in HCD. That is correct. But the reconciler loop that will run, it will have no idea that previously the user asked for a T3 medium. They're completely stateless. What the reconciler loop will now do is it gets your request. This is your logic that you would add that allows the user to change the spec for the instance type, or maybe the user can dynamically change the tags that they want to give. So here in this case, if the user has made updates to the type key in the YAML of the EC2 resource, it is your responsibility that goes to Amazon and sees if the instance of T3 medium was available. And if it was, you delete that and you create a T2 micro, because you can't change the instance type. As far as I remember, if you can, that's on Amazon side. That's a different story. But the reason what I'm telling you is your operator, your controller, the reconcile loop will not remember the past requests. It always has to check the current state is T3 medium, the desired is T3 medium, nothing needs to be done. But if the current state in the cluster is T3 medium and the desired is T2 medium, it goes to Amazon and says, okay, this needs to go away and this needs to be in action. And this is how you do self-healing or eventually consistent. And then you update the object, which we will see in the next session. So this is how you will be building an operator that knows how to watch the API server for your custom resource changes, that knows how to watch the API server and update the reconciliation logic in case there were some changes. You change the object, which we will see. Yeah, that was it. So this will be giving you a very good idea, a very beginner idea. I will not say beginner, but it's a good enough idea for you to build your operators and then you run them on Kubernetes. Next thing that we're going to be learning is, I already have it available. This is going to be how we will be writing an operator, which will be actually creating us an EC2 instance. The next parts of this video are going to be more onto how to use Amazon SDK in Golang to create an EC2 instance on Amazon. Because we now know from Kubernetes point of view, from the operator point of view, we know how to write an operator, we know how to write the spec, how to install the custom resource definition, and how to react on changes into our custom resource in the operator. Now it's about what do you do with that change. In my case, I'm just printing it. In the actual case of the course of this video, we will be using these changes and then we will be building them on top of Amazon. We will be creating an EC2 instance. So that is what we will be doing next. Till this point, you know how to write your operator. You know you can get requests. You know how you can, the reconciler loop does it for you. So the next part, we will be using the Kubernetes SDK in Golang to create us an EC2 instance. And then we will see if in case a request was successful, we don't need to reconcile again. We will talk about finalizers, but that's all coming in the video. So let's look at how we can create EC2 instances with our operator using Golang. Okay, before we can actually get started for the code, there is something which is absolutely important for you to understand. We have been working with the reconciler loop, and we talked about that the reconciler is the one that takes your request and runs it through a series of your logic, and that's where you get your changes for the current state to be equal to the desired state. However, this reconciler is expected to return two values. One of them is the result, and the other one is actually an error, or it's going to be nil. These two return values are actually required by Kubernetes to know what needs to be done for your current reconciler request. So imagine your reconciler got a request here and you made some changes to your environment, you made some changes to your resources that you need to change, and then you have to tell Kubernetes whether you want to rerun the reconciler for the same request, or you just want to wait for new requests. In this case, you did not get any error. You did not return any error. Based on these values of the result and the error, that is when Kubernetes decides, do I need to rerun your existing request with the reconciler again? And this is how we work with things like self-healing. If you know about this, you can give this give this a try. Get yourself a pod that is in a pending state because of CPU or because of memory. Ask for resources that are not available in your cluster. The pod is going to be in a pending state. Then go ahead and add a new node that will be able to host that particular pod. And once that node is active and available, this pod gets from pending into the running state. You didn't have to do anything. You didn't have to tell Kubernetes that, hey, I got a new node. Please put my pending pod on this new node. It didn't work that way. It was self-healing because when the first time Kubernetes tries to put your pod to a node, it says, okay, there is no node available. I'm going to put this in a pending state. Think of this as a reconciler. So the decision was made that I'm going to put the pod in the pending state, and the controller responsible for scheduling your pod returns a pending, which is actually, it sends an error that for the request that came to me, I was not able to properly process it, and there was an error. And this is where Kubernetes knows I have to retry again for that request. And this is how self-healing works. While Kubernetes was retrying and retrying and retrying with an exponential backoff, you happen to add a new node. And this is when, once you added the new node, when the logic ran again, it was no longer pending. The reconciler said, okay, you asked for 8 CPUs, and I have node now, which is 20 CPU available, 20 cores that are available. I'm not sending any error. Rather, I'm going to send a nil for an error, that I did not get any error, and the pod was scheduled, and the pod then eventually went into a running state. This is something that Kubernetes does for you. And as a developer for this reconciler, it is absolutely your responsibility to tell Kubernetes whether your reconciler function was okay, or did you get any error, and would you like Kubernetes to actually retry that particular thing. This could happen for EC2 instances. Imagine when you tried to have your reconcile function and you were calling the AWS API to create an EC2 instance, and you were not able to do that. You had the right credentials, you had the right access for IAM for your user that you are using, but maybe there was some network timeout happen, or anything that could stop your request from processing happened. You would like to retry again, right? Maybe after like 10 seconds or 20 seconds or whatever your time is, you would like to retry. In this case, you can tell Kubernetes that there was an error. My reconciler function is returning an error, that please retry that again. And based on the requests and the error values, Kubernetes decides, do I need to retry this particular request, or do I need to wait for new events or new updates to the custom resource for which this reconciler is listening on? So there's a very simple a condition that your reconciler can actually look into or look for. And this is also in the priority order. If your reconciler function, if your reconciler is returning an error, so your error is present, you are returning an error, this result is completely ignored. That means whatever you send in the result is completely ignored, and you are then using an exponential backoff. A little bit about the result. What are you actually sending in this result is two things. First, you are sending, do you want to requeue or not? Usually it's a boolean where you can say I want to requeue or not. And second, you're sending time for the requeue. If you are sending an error, if there is an error present in your reconciler, this result is completely ignored and you will always be retrying. Kubernetes says, okay, the reconciler function or the reconciler is giving me an error. That means it could not properly process the request that came in. I will retry this. And this is where the self-healing loop comes into the picture. If in case you are not sending any error, so this is the second thing. If you think, okay, everything is fine, I have processed my request, I'm not sending any errors, and you do send a custom requeue after, and this requeue after is actually this time. Rather, I should have put this as, wait a second, I can probably get a better color here. This should be requeue after. This is the time after which your reconciler should again be started. And this is like a forever running loop. So imagine this, you create an instance, it's okay. You probably want to check for the instances every 10 seconds or every 20 seconds. Maybe you are doing some sort of drift detection there. And if you were able to look for your instance, everything was fine. That means you're not having any errors with that instance. But you want to retry that again after 20 seconds. And this is what you are sending. You are not sending any error because you did not have any errors. However, you are sending a fixed time. You are telling Kubernetes that there was no error in my request, but I want you to rerun this reconciler every 20 seconds. And this is kind of like a forever running loop. It never stops because you don't have any errors, but you always want to retry that again and again. You want to rerun this. What could be the reasons for it? I just told you. Maybe you want to do some sort of a drift detection. The third condition could happen if you are not sending any errors and you want to, requeue and your custom timeout is not set, which is kind of similar that you have no errors and you also want to requeue, but you don't have any requeue after set. That means you are asking Kubernetes that, hey, my reconciler was okay. I want you to retry again, but I'm not telling you in what frequency do you have to try. It's kind of like similar to level 2, which in this case, you're also not sending any errors, but you are telling how frequent do you want to try. In this case, you're also not sending any errors, but you're not also telling Kubernetes how frequent do you want to try. You are letting this with Kubernetes, and this is going to be the exponential backoff. This is where Kubernetes will say, okay, the user said there is no error for the reconcile loop. The function was running properly fine, but they are not asking me to run this in a forever loop. I would probably, I'm going to use an exponential backoff. So it will run your request, and then maybe another time it takes 2 milliseconds. The next time it's going to take 4 milliseconds. The next time it's going to take probably 16 milliseconds or so. And this is going to be an exponential backoff until I think the maximum limit is 1000 milliseconds. Until then it stops doing it. And the last condition that you can return for your reconciler is you do not have any errors and you also did not send any requeue flags. Probably you just said result was empty, and then you are sending a nil. You are returning a nil. This is where Kubernetes says, okay, everything was fine. I'm not doing anything. I'll just wait for a new update, or I will wait for a new event where the custom resource has been updated, kind of like for the new requests here. This is absolutely critical for you to understand. Otherwise, you might see your reconciler making changes again and again, or you might see your reconciler running again and again because you did not send the right set of values. You did not put the right return values for the reconciler and for Kubernetes to understand what to do. Now, as I was talking about, once this is understood, I was talking about we will be looking into the Go code. So let's take a look here and let me get that here. So in your screen, you can see that I've made some changes to our instance spec. Before now, it was a very simple one. It was just having an instance type, an AMI ID, probably a key pair, and a security group. But when you want to make things more robust and when you want to make things more production ready, you have to think from an overall point of view. When you want to create an EC2 instance, there could be many things that you have to give. You definitely have to give the instance type, whether you want to use a T2 micro, T3 micro, or any other instance family. Then you absolutely have to give an AMI ID, which is going to be the AMI ID you want to use. You have to give the region as well under which your instance should be created. You need to give the availability zone. You have to give the key pair so that you can log into the instance. You need to give the list of security groups around here, the subnets in which your instance could be running, and also when you want to provision the machines as soon as they boot up with your changes, we usually use Amazon's user data. And that also is what you can give. You can probably give tags as well. You can also give some storage. You have to give storage. And whether you want the instance to have a public IP or not. This is kind of like a boolean that you can give. Now, on the right side, you can see this omit empty. This is actually a place where you can control what kind of fields in a YAML when you give your EC2 instance spec are optional or what kind of fields are required. For example, tags could be optional. User data is optional, but storage is absolutely needed. AMI ID is absolutely needed. Instance type is required. So this omit empty lets people define the only important or the required fields. Otherwise, the other ones could just be skipped. So here you can see I have a storage, which is a type of a new struct called storage config. And here's a new struct called storage config where we define a root volume, and then we can also probably give some additional volumes as well. This is an example where you give your root disk as 100 gigs, and maybe you want a VM for a database. You can add a bigger disk in the instance, and this could be done by the additional volume. And both of them are of type volume config and a list of volume config, because additional volume itself is a list of additional disks that you can add to your instance. And this is a very simple volume config where you define the size of the disk, you define the type of that disk, the device name, which is going to be available in the instance when you mount it or attach that, and the encrypted boolean, if in case you want the device, if in case you want the disk to be encrypted or not, because Amazon allows you to encrypt your disks in case you want that. So think about the EC2 instance as a more holistic approach, whether you want to give or you want to allow the users to be able to declare their set of data and the metadata. In this case, you are allowing the developers to create an EC2 instance, not just create one, but also you are letting them log in with their key pair, and you are also allowing them to use their user data that you can give to Amazon when you're creating the instance that lets it pre-configure before they can even log in. And the VMs are exactly how they want it to be. So this was a bit of a change in our EC2 instance spec to make it more production ready, to make it more not from development, but actually to production. I've also made some changes to the status where when you do kubectl get EC2 instance, you will see the spec and also you will see the status. So in the status, I would like to see the instance ID. So it is easier for people to see what is available on Amazon and what your Kubernetes knows about. The state of that instance, if it is running, if it's terminated, it is unknown, it is stopped, all those Amazon EC2 instance states. And also a very important thing is going to be the public IP. Because when I do kubectl get EC2 instance, I should have enough that lets me log in to this public to the particular instance, and this is a public IP. And that's what I want to show when someone does an EC2 kubectl get EC2 instances. And then again, we have the standard struct of our EC2 instance, which contains the type metadata, the object metadata, and our spec and status. And this is kind of like just when you get a list of instances, what's going to happen. And this is how Kubernetes knows what is an EC2 instance would look like for you. Now, I've already made the changes, and I told you, whenever you make the changes, you have to run the make manifests command, and then you have to install that to your Kubernetes cluster. So my Kubernetes cluster already has this custom resource definition. If I do kubectl get EC2 or CRD, which is EC2 instances.compute.cloud.com-OYAML, and let's look at this. You can see the name is EC2 instance, the list kind, the plural, the singular. It is a namespace scope resource. And there you can see I have got a couple of things such as a kind, and there's my spec. I have got the AMI ID, the associate boolean, a public IP or not, it's a boolean, the availability zone I want to run my instances on, and things like my security group, which is type of an array, because you can give multiple security groups. And then I've got my storage configuration, where I give one root volume, and I have got additional volumes, which is type of an object, which is then again, globally, it's a type of an array. So you can give multiple additional volumes, but you can only have one root device. You can only have one root block device. Now, once we have defined our spec properly, there is going to be now some code that actually uses this and creates you an EC2 instance. So let's see that. Once I have my instance type, I can actually go to my EC2 controller, and this is where everything starts. This is where you will be seeing the reconcile loop. We saw this before. We used the reconciler to actually see what happens when I get a request. And this is what your to-do is. My logic starts, and I have created a logger for this context that is aware of the context. And you can use l.info, which is going to just print stuff when you are running your operator. So it makes it more verbose, and you can see what is going to be, what's going to happen, or what is happening with your controller. It prints out a function. It prints out an info message that the reconciler loop has started, and this is the namespace under which you got a request. So REQ is the request that comes to your compiler, and then you send a result back to Kubernetes. So it came from this namespace, and the name of the request was request.name. That's the name of the object that we are working with. Then there are some comments which I was building this. I put some comments for us to be easily understanding this again. But you know what we are doing. We are creating a variable of type EC2 instance so that we can marshal the object which is coming to us in this reconciler loop by Kubernetes into a variable, and then we can easily iterate over on top of that. We get the object into our EC2 instance variable from this namespace, and if you could not get the object, and this is absolutely very important, see, you may have any problems for getting the object. Maybe you have a wrong YAML. Maybe you probably were supposed to give a string, but you give a Boolean to one of the keys. Or you probably did kubectl delete the object. That's correct. Even if you delete the object, it is an update to the custom resource. Then again, this reconciler is going to be started, and you have to check if the error that you got when you are trying to get the object is not found. This is one of the errors from Kubernetes. Kubernetes has a package called errors, and let me show you here. And here you can see it has all these errors defined for you. So it makes it easier for you to declare what was the error. In my case, see, sometimes when you create an object, it gives you the object already exists. It's an error. But you can actually see what kind of error it was. Because if I was just saying, get me the object, and if error is not equal to nil, I would just say, okay, there was an error, please try again. But the user will never know what the error was. In this case, I can say, hey, you know what? I was trying to get your object. I was trying to get it into my variable, but I got an error while trying to get it, and the error was is not found. And that is where it returns a true if the condition was that I could not find the object. This is probably when you are deleting the object, it again runs the reconciler. So it looks something like this. You have the object here. Whatever change you make on this, the reconciler will be running again. So the change could be you added an annotation. That's an update. Then the reconciler. The change could be you added a label on top of that, the object. Again, the reconciler would be running. It is your responsibility to write this reconciler in a way that if it surely should not be changing anything, if the change that you did to the object doesn't require a change, it should not be changing the actual resources. For example, your object could be EC2 instance, Maybe on this Kubernetes object, you want it to give a label. That doesn't mean you have to change something external to the Amazon instance. That should not happen. So this is something you have to code in your reconciler. Even when you say kubectl delete, when you say delete, the object is deleted, there was a change on the object, and then another run of the reconciler would happen. So you have to check that when you were trying to get your object, you could not get that, and there was an error, and the error was actually is not found. You will simply say the object does not exist, or there's no need to reconcile because the object was deleted, and then you just return an empty result and a nil. Remember, this is one of the return types that you have to say. What you're telling Kubernetes is everything is fine. There was no error from my side because the object does not exist in our case. And please wait for the new requests which are coming to the reconciler. This one request that came in is all good. If you could not get the error for any other reason, then it is not found. Maybe you did not have right RBAC to get the object in that namespace. For whatever reason you could not get the object of the request, you will then say you will send an error. And you see here, the moment you send an error, you are telling Kubernetes, please retry this object. Please retry running this reconciler. Please retry the operation of the whole reconciler loop. And this is where the self-healing would work. Probably you had some problems where you could not get the object, but you try again, and if it works, then you're happy because you don't have any errors anymore. Otherwise, you send an error again, and this is going to go ahead with an exponential backoff. So it's like when the first request comes in, it was an error, but it was not an is not found error. You return an error. Okay, it goes back to the reconciler again, runs to the reconciler. There was an error again, which was returned, goes back to the reconciler, and this happens with an exponential backoff. This is where return values of the reconciler function are absolutely critical. Absolutely critical. Now, the next thing is, whenever you delete an object, you set a deletion timestamp. And I will talk to you about this in the future. We are not going to talk about this right now. This is when you delete the object. We will first learn how to create one, and then we will delete one. And this also is about deletion. This is the logic of deletion. We will talk about that later, and I'll tell you why it's here. This is the logic of checking if the instance is already there, because you want to be idempotent. You don't want to create the same instance with the same instance ID if it is already there. And this is also the logic which I probably would talk to you about later. This also is a logic which I will probably talk to you about later. So here is where we start in our loop. The first thing you do is you start your reconciler, you create an object, you try to get the object into your EC2 instance variable, the custom variable type that you have created. And then you say, okay, I'm starting completely new. I have no idea. I have no instances on my Amazon, and I'm going to create a new instance. The first thing you do when you create an instance or when you create an object, it's a very good idea to add a finalizer. You might have seen this in Kubernetes. When you do kubectl get -o YAML, you might see this finalizer in the metadata section of your object. What this finalizer actually does is very interesting. So let's say when you created this object in Kubernetes, which was an EC2 instance, and there you added a finalizer. Finalizer is nothing but it's a list of key value pairs that you can add. Let's say I add my finalizer as hello : world. Then this object was created, and your reconciler actually went to Amazon and give you a new AWS instance. All right, everything is happy. You got the instance now. The thing that happens with finalizer is when you say, I want to delete this object, when you say, I don't need this instance anymore, I want to delete this particular object, you can delete this from Kubernetes. However, that's not the only thing where you need to delete it from. You also have to delete this from Amazon. So how do you tell Kubernetes that why I am deleting this from an external resource, from an external platform? Do not delete this object from Kubernetes. Only when this instance is completely gone from here can only you delete this particular object. That is the role of a finalizer. Finalizers will hold the deletion of the object in Kubernetes until the actual cleanup has happened. And once you have, once you have deleted the object, you then remove the finalizer, and then Kubernetes will allow you to delete this particular EC2 instance Kubernetes object that we have created. As a good practice, when you create the object in Kubernetes, that's where you should add the finalizer. And this is extremely important. This finalizer is being added to your Kubernetes object, which is EC2 instance. And this also is an update. And this is also going to rerun the reconciler loop. Any update to the object, whether you are adding a label, whether you're adding a metadata, whether you're adding anything really, whether you are updating the status of the object in your code, that will start a new reconciler loop. So this is where you have to be very careful of idempotency in your code. And you see what happens? We print a message and we say, I'm about to add a finalizer, and I use this this append function because it's just a key value pair. I'm adding in my EC2 instance .finalizer because I've already marshaled this using the r.get. My EC2 instance has actually the YAML of the request that was given to me, and I'm creating a key in here called finalizer, and I'm appending my finalizers here in called EC2 instance EC2 instance.compute.example.com. I'll show you how it looks. It just creates a new key under your object in your object, and then it just adds this as a list there as an entry in the list, because you can have multiple finalizers in your object. Once you have declared that I want to add a finalizer, the actual way of updating your object is going to be r.update, reconciler.update. There are a couple of functions we get with the reconciler. Get lets us get the object of the the get function lets us get the YAML of the object into our variable. And then you can also use r.update. This lets you update the object that the reconciler is working on right now. So in this case, I'm updating my EC2 instance where I'm actually creating and adding some finalizers. And we will see this. When you create the instance, it will actually give you the finalizers when you as soon as you create the instance. And because you made an update on the object, it will start a reconciler again. Not right now, though. This is very important. See, it's very important to remember when you have the reconciler. Let's say when you have the reconciler, it starts. Let's say here you made an update to the object. Maybe you updated the annotations. This is where you will start another reconciler, but not right now. You will move ahead in your code and you probably make another update. In this case, you updated the labels of your reconciler, of your object. Kubernetes also records this as a second time it has to run. Then you do a return and you do a nil. What's going to happen is Kubernetes will run this reconciler twice because you made updates to the object twice. It's kind of like it remembers that this is where an update was. I have to rerun the reconciler. This is what an update was. I have to rerun the reconciler. It is a golden rule of reconcilers that any update to the custom resource, whether it was done by you with kubectl commands or whether your reconciler is doing it, will start another reconciler loop. It will not stop the current reconciler. It's not like it got an update, it will directly go from here. It's not like that. It will finish the proper execution, and then based on how many updates did you make, this is where the reconciler loop is going to run again. And this is your responsibility to make sure that when you run this again, this update does not happen, this label does not happen, because they're already there. And then you will say, okay, I did not make any changes throughout my reconciler on this object. I need to do nothing. I don't need to start the reconciler again for this particular custom resource. If you make a new custom resource, then again, yes, the reconciler will be started and the loop will keep on running. Extremely, extremely important to know about the return types of the reconciler. Now, once I have updated, my object, I'm telling Kubernetes, please add this finalizer to my object. And if I got an error that said failed to add finalizer, actually, if I got any error, I'm printing an error that says, hey, I was not able to add the finalizer. And I say, please requeue, and I'm sending an error. So this is where you are returning another return type. And you see, whenever you get an error, whether you are trying to get the object, whether you're trying to delete the object, whether you're trying to update the object, you want to retry again. And this is where you will return an error. And whenever you return an error, this whole result is completely ignored. It's absolutely, absolutely important to understand this. When you are returning, or when your reconciler, you see here, this reconciler function is returning two values. One is the result, the second one is an error. If you return an error, the result is completely forgotten. Kubernetes says, you know what, the reconciler had an error, I'm going to retry it again with an exponential backoff. And this is how the self-healing works in Kubernetes. Now, once you have added the finalizer, I'm just printing an info message for info log, which says finalizer was added. This updates a new reconciler loop execution, but the current will continue. And this is where we create an EC2 instance. I'm just sending a log. I'm just printing a log, continuing with the EC2 instance in the current reconciler. And this is the beauty, what we were waiting for. This is what's happening when we want to write an operator that talks to that creates me a Kubernetes cluster. Guys, this is where it all comes down to. We have our spec of the custom resource. We have the logic that listens on the update of our custom resource. We have the logic to get the manifest, or think of this as this way, to get the YAML of what the user has given in my EC2 instance. Now I need to create an EC2 instance. This is absolutely important. Now it's going to be so much fun. Now, when you want to create an Amazon instance, you know what you need. You absolutely need an Amazon account. And you need to have the credentials. You need to give the credentials to your operator or to your controller, so it can go on your behalf and work on Amazon. And this is exactly what we were doing. Before we can actually go ahead and create an instance, we need to figure out the authentication. Then we will use a client that we created using this authentication, and we will give it this particular YAML, and we're going to ask it to go ahead and give me an instance on Amazon. And this is exactly what's happening now in this create EC2 instance function. So I've created an EC2 instance. I've created a function which is called create EC2 instance, and I pass the user's requested YAML. I pass the user manifest, the EC2 instance, and let's see what this function actually does. This function, which is a create EC2 instance, it is accepting a value of type EC2 instance, which is the whole YAML from the user, and it is returning two things. First, it returns it is returning a variable, it's returning a type of created instance info. See, when you create an EC2 instance, you get a lot of output, you get a lot of data, but we don't want all of that. We only want to, when a user creates an instance, probably they care about the state, whether the state is running or not. They care about, created or not, true or false. They also care about the public IP. That was it, created, what was it there or not? Do I have a public IP or not? And for this information, I have created a new struct, which looks something like this. Created instance info, and this helps me to send back the data from my create instance function. What I'm sending back is I can send an instance ID, which is important so people can know what instance IDs are there on Amazon. Using kubectl get, I'm also sending a public IP. I can send a private IP, a public DNS, private DNS, the state. That is all I can send from my function. And this is the return type. And my function, which is going to create me the EC2 instance, it is returning two things. First is a struct, which is the information of the created instance. And second is an error, which is, I probably could tell the user that I tried to create the instance, but there was an error. Maybe the authentication was a problem. Maybe you don't have enough quota in your region, in your account. I want to send them something so they are aware of what has really happened, why the request failed to create the instance. So we create a logger, which is create EC2 instance. This is good. You can have your logs with custom log name, and this is easier for you to know which file, which function created this particular log entry when you do kubectl logs in your operator. So I'm putting up a info, which I'm saying I'm starting the EC2 instance creation. This is going to be the AMI ID. I'm going to use what the user has given from the spec. This is the instance type, and this is the region under which I'm going to create my instance. So the first thing I have to do is to create an EC2 instance client. Guys, now it has nothing to do with Kubernetes. It is completely how you create an Amazon instance in Golang. It has nothing to do with Kubernetes because you already have the instance YAML, or rather the instance info, because EC2 instance is the whole instance that should be created. Now you are doing the generic things on how to create instances on Amazon. The first thing you do is you create the EC2 instance client with this AWS client function. What this is eventually doing is it's reading the AWS access key and the secret key from your OS environment variable. You see, because you need to give some sort of authentication on how you would talk to Amazon. I'm using the AWS key and the access key, and then I'm using the config from Amazon to load the default config with these credentials that I have given. And then if I could not create the config, I return an error. Otherwise, if you have the access key and the secret key, you are able to create a config, and then you are returning a new config. Think of this as this function is just returning an EC2 client. And this is absolutely important. You will use this client to talk to Amazon. So you use your access key and your secret key to create an EC2 client, and then this EC2 client is here. Till this, you have the authentication to Amazon. Till this 24, you have the authentication to Amazon. Now you need to say, hey, Amazon, please create me an instance with this key in this subnet. This is the minimum count. This is the maximum number of instances I want of such. This is going to be the instance type that I want you to create, and this is going to be the image AMI ID I want to use. These are the input instance parameters. You are creating an instance Amazon expects you to give certain instance inputs, and these are one of them. There are many other instance inputs that you can give. If I show you, you can tell Amazon what is the maximum count of instances you want, what is the minimum count of instances you need, any block device mappings you have. You probably can say what is the capacity reservation specifications, the CPU options you can give. Is it a dry run or not? Is it a EBS optimized or not? So there are many different options you can give when you are creating Amazon. This is just something when you create Amazon instance, this is the information you give. You can also give security group IDs if in case you want the security group to be used for creating this instance. I'm just keeping it very simple so that we know what's really happening. We are creating our query to create an EC2 instance with these inputs. And once I have my input declared, I'm using my client, EC2 client, which I created above, and there's a function called run instances. And this is the function from Go SDK of Kubernetes of Amazon that launches the specified number of instances using the AMI for which you have the permissions for. And this is absolutely the one that is creating the instance for you. So far, you created the client, you created the instance input, and now you have created your actual instance here. Now, for whatever reason, this run instance is going to be returning two things. First, it returns the actual output. See, I told you, when you create the instance, you get a lot of output. So this is what's going to be returned. So if you look into this, EC2 instance dot EC2 dot run instance output, if I look at that on Golang, here, you can see I'm going to look for the run instance output here, and this is what is being returned to you. You are returned. Where did that go? Whoa. I think I was a bit quick there. Let's wait. Run instance output here. So you see, you are returned the groups. You are returned the instances that were created, and this is the metadata. There's something wrong with my browser. Wait. Essentially, what you are given is where did that go? Return instance output. There's a type. So you get the instances, and this is where you have the instance metadata. What is the primary? What is the private IP? What is the instance ID that was created for you? What region it was running in? What zone it was running in? So think of that as the metadata of your instance when you created that, and that's what we are saving in the result. If in case there was any error, because this run instance does return an error as well, you will say failed to create the EC2 instance, and then you return the error back to the main program, and you say this was the actual error because of which I could not create the instance. There could be many reasons why you could not make one. Perhaps you did not have the permissions in that region. Perhaps you did not have quotas in that region. Perhaps you used a wrong AMI ID, which doesn't exist. Could be a typo or anything. You just are returning this to the user. It's a good thing to return them the reason why it failed. So that's what you're checking. If the instances returned is 0, you will just say there were no instances returned for me. And till here, if we have no error, we have an instance for ourselves. And this is what has happened so far. Our code, we had the client, and then we use the run instance function to actually create an instance, and it gave us some output back. Till this time, this output contains things like the state that was, when the instance was created at that time, what was the region, the metadata, the private IP, the private DNS, DNS name. By this time, there is no public IP. However, there's one thing important. Second, When you make an API call to Amazon with this run instance function, what you essentially got back in the output is the state of the instance at the time when AWS received that request. It might not be running. You know how when you create an EC2 instance, it goes into pending, creating, initializing, then it eventually goes into the running state. At this time, you have an instance created for you, but it might not be in the running state. It might take some time for the instance to be in the running state. And this is what you want. You want to wait until the VM is running. So when you when you execute the run instance function, it creates the instance and gives you back the metadata. What it does not have, however, is the public IP and the state, whether the state is running or not. So it's kind of like you say, hey, Amazon, create me the instance. Amazon says, cool, I will give you one. Here's some metadata, but you don't get the public IP and you might not be in a running state when you created this actual instance. But this is what you say. If I got back in my result, because you see, this run instances, it gives you back the list of instances and you are checking. If there was, an actual instance where I did not have any errors and there was an instance created, you will just send an info that says, okay, I was able to create the instance successfully and this is the instance ID that was returned to me. You store the result of, you store the output that was given to you, and there you can access things like instance ID, private IP, public IP, because it's all returned by Amazon to you. And now we wait for the instance to be running. See, it's a good idea that you created the instance, but it's not like, imagine this, there's this developer and he goes to you and says, can you give me an EC2 instance? And you go to Amazon and you say, please create me the instance, and you get back the private IP. In your company, you guys are using a Bastion host, which is available, and using this Bastion, you can talk to the VM which has a private IP, because you might not have a public IP. You might have disabled the public IPs. So essentially what happened, the guy asked for a VM, you said, hey Amazon, create me a VM, and you got the private IP and you gave it to him. You never waited to see if the instance was actually in the running state or not. Maybe the instance was created, but it never reached running. Maybe there were some problems in the region of Amazon, or maybe the instance malfunctioned. Whatever could have happened, you were not waiting for the instance to be running. You gave it to him, and he logs in to the Bastion only to find out that this instance is not running, so he cannot use it or she cannot use it. And that's where the problem is. As an operator, it is your responsibility that you create that particular resource, you create the instance, and you wait for it to be in a certain state that you want. In our case, it is running. So what I could have done is I could have had a for loop. I could have had a for loop that keeps polling Amazon. Hey, is this instance now in running? Is it now in running? Is it now in running? Every maybe 5 seconds. That's also doable. Think of this as a while through, and I would say think it like this. So I'm using a while loop, check the instance, and that's it. This is kind of like my function. It keeps running. I'm giving it an input to describe me the instance, and I'm describing the instance with this function, and I get some responses back. If the state.name is running, think of this as a pseudocode, then you break. Otherwise, you keep running. So you keep running every 5 seconds or 10 seconds. That is a doable option, but it's not a good idea. It's not a good idea because Amazon gives you these waiters that can do this for you more gracefully. A waiter is nothing, but it's a construct from the from the Go package of Amazon that waits for a certain time for a certain state to be reached of the instance. In my case, there's a new instance running waiter. If I go to that and if I show you, or probably even here, there is going to be a new instance running waiter. Now, what this does is it defines a waiter for instance one. This one actually has the logic to wait for the instance to be in the ready state. It does the polling more efficiently compared to me having this writing in my logic, in my code. So you can define a waiter, which is going to wait for the instance to be reaching the running state. You can also give the maximum time for which you want to wait, because it's not like if Amazon takes forever for your instance to be created, you just say the checking loop will keep running forever. You have to give some feedback to the user. And typically, you can give the run max time, which is going to be time.minute and 3. So you're giving 3 minutes that you want to wait for the instance to be reaching the running state. And this could be depending on your requirement. You can increase this or decrease this. Every request that you make, this waiter will be exponentially backing off. So it's kind of like it starts from like every 10 seconds and then it increases this timeout up to your given time. So it does it a lot better. You create a waiter and then you use the wait function to ask it to wait on this instance ID. So you are telling this waiter that please wait for this instance for this maximum time for it to be reaching the running state. And by this time, if it was not reached the running state, there would be an error. And if the error was not equal to nil for this time, you will just say failed to wait for instance to be running, and the instance could not reach the running state in 3 minutes. Now, this is important. You do say the maximum time for your instance or that you want to wait is 3 minutes. However, if the instance has reached the running state in the first 30 seconds, then the loop will stop. It's not like you're going to wait for 3 minutes dedicated, even if the instance reached the running state before. It's not going to happen like that. This is why the waiters are quite interesting. They have the logic for it, so you don't have to deal with that. This only comes from experience when you are using the SDK. These are the things that you can also Google. How do I make my code more efficient? How do I use waiting? And you will get that. Now, by this time, when the instance has been created, we get the remaining information back. We got the state because we were waiting for it to be running, and we only break our loop when the running state is there within 3 minutes, of course. Now, by this time, Amazon has also associated your instance a public IP. 3 minutes are good enough for Amazon to give your instance a public IP. And there, then, what you can do, so actually, okay, this was a bit wrong. By this time, we are just waiting for the instance to be running. We don't have the public IP yet. This is where I probably skipped ahead. When you are using a waiter, you were only waiting for this instance to be running. And once the instance is running, Amazon will give you a public IP. So you have it running, but you don't have the public IP yet because it was not given to you in the output when you created the instance. This is where you will use another Amazon function, describe instance. Now you say, okay, I created the instance. I waited for that to be in the running state. Now I'm describing this particular instance. Now I'm going to get my public IP as well. Of course, given if you have the public IP allowed in your Amazon account. And this is where another request happens to Amazon. So we waited for it to be in the running state within 3 minutes. And then I'm saying, calling Amazon describe instance API to give the instance details. I tell Amazon that I want to describe an instance whose ID is what I got when you created this instance for me. And I want to store this result, which is of the describe instance function. And I want to store this into a describe result variable. If I could not describe the instance, again, this is a very simple go check You will say failed to describe the instance, whatever reason you are having, you just give the instance. Or if you could describe it, your result is going to be in the described result, which is again a type of describe instance output. Now, when you describe the instance, you get a struct back from Amazon. You get some data in a specific struct, which we can see it here. You do get some output with describe instances. Wait for that. And this is the describe instance output. What you get is you get the information about your reservations, which is the instances on Amazon. And within these reservations, you have the instance information. So if you look at the reservation, there you have the instances that were described for you. So you can call the reservation, because I know I only created one instance, so it's only going to have one element in the list, because the reservation is a list of reservations. And for these instances, which is only one, the public DNS name is going to be describing like this. So I print the public IP, and then I say the state is state.name. Again, this is returned by the instance struct of the GoLab. Because if I show you here, if I go to instance, it will have public DNS. Let's look for that. There you go. The instance struct is returning a public DNS. It is returning me a public IP address. And also, it returns me the state here. The state is of type instance state, where we also have an instance state name. So it's kind of like they have created packages for all the other one. And here you see you have the name. So you have asked for, I want to describe my instance, and the input is this instance ID. I store the result. I store all the reservations that was returned to me by Amazon and all the instances inside of it. I know I only have one instance, so I can call it with 0 index and tell me the public DNS name and tell me the state of the VM. Now, here's an interesting thing. By now, you have all the information you need for your EC2 instance. You've got the private IP, you've got the public IP, you've got the instance state, you've got the name of the instance that was created, the key name that was using, and now you can actually so by this you have all the resources that you need for your Amazon VM to be given to the developer who has asked for this instance. The next thing that you can do is you can get the information about the instance, but this thing is not needed, because we already requested the instance information. That's not what we are doing. However, this is what we are returning back. This is extremely important. See, when you have all the information about your instance that you have created, we want this to be returned back to the actual controller, so that this is where we have the instance information. This function is returning me a type which is created instance info. And I just showed you the created instance info here. Where did that go? In my API, this one. So here's the struct which is created instance info, and that is what my function should be returning. This create EC2 instance should be returning, and this is what I'm preparing now. So I got all my instance information in a variable called instance from the described result, and then I'm preparing my return type, because this function is returning two things. First is an error, if there was any, and second is the created instance info, which contains the public IP, the private IP, which contains a public DNS, private DNS, the state, and the instance ID. And this is what I've prepared now. So once this is done, we will simply say, I've created my EC2 instance, and there I'm returning my return types. Because I did not have any errors when creating this instance, I'm returning a nil. And I'm returning the information of my instance which was created. What might be interesting is this function called derefer string. What this does is it is actually just dereferencing my pointer. The reason why is we are dereferencing this pointer is because when you talk to Amazon SDK, it is returning you things like public IP address, which might not be available at that time. So when you are returning this, it might be it is a pointer type, but you are returning a nil pointer, and that's a problem. So this is important that we are able to distinguish between whether it was an empty string or whether it was a nil value. If it was indeed a nil value and you were trying to dereference a nil pointer, that's going to be a problem. And this is essentially why we waited for so long for the instance to actually have a public IP. This dereference function just dereferences my string to return a string, which I can give back to my main function. And by this time, I have an EC2 instance that was created for me. Now, the create EC2 instance function doesn't just create me an instance on Amazon, it does return me two different values as well. One is an error, which is a good idea that your function does return an error if there was any, or it returns a nil, so that you can use that error in the further steps. For example, we are using it here to say if there was an error, we want to put that error as a log output of our reconciler. So when people are looking at the logs of our application, which is a reconciler in this case, they will know why there was an error, which stopped you from creating an EC2 instance. And then you can use this error to be sent as a reconciler's return value, because you remember the reconciler here, it is expected to return two things. First is the result of the reconciling function, which is the current reconciler, and then if there was any error with that reconciler. Now, it depends how you are creating, your reconciler. Maybe you want to retry. After waiting some time, you want to retry creating that EC2 instance, and this is why you can return an error within the return function. What you're essentially telling Kubernetes is, I tried to do an operation, which was in my case was to create an EC2 instance, and I could not do that. Whatever the problem was, I want you to take some time and retry that process again, retry that function again. And this is where Kubernetes will say, okay, I'm going to retry running that reconciler loop. So I'm going to retry to create that EC2 instance for you. And this is kind of like being done in an exponential backoff. It tries, it fails, it waits a little time, it tries again. If it fails again, it waits a bit longer. And this is how the Kubernetes will be doing its exponential backoff with your request. So you're not getting rate limited by Amazon, that you keep trying and asking for an EC2 instance every 2 minutes or 3 minutes or whatever your reconciler is. It waits during the time, and it's an exponential backoff. Now, once you have the EC2 instance, once you were able to create the EC2 instance, I'm returning the info as well, which is, if you remember, it's a struct that we created, probably somewhere around here. This is the struct that we created, and this is the information I want from my create EC2 instance function, because this is something I want to give to my users when they do a kubectl get EC2 instance. They should know the instance ID, and most importantly, they should be knowing the public IP of the instance, so they can always log in and they can start working there. You also would probably want to give them the state of that instance. How is it right now on Amazon? It is running, is it stopped, is it terminated, or if any other state there is, you want to update them as well. So we do a very small log. We are saying that, okay, I was able to create the instance and now I will update my status. If you remember, every EC2 object that we create, every EC2 instance that we create has a spec, and it also has a status field. This is much like with any other Kubernetes object, which is where you have the flexibility to tell what status should be. In our case, we are telling the instance ID. In our case, we are telling the public IP. In our case, we are telling the state of this instance, whether it is running, whether it is stopped, whether it is, terminated, or all the other states that Amazon instances can have. And that is where we are appending the actual object. This EC2 instance here, if you remember, we actually create a variable for it, and we got the object from the request that came into our reconciler. So the user asks to do something on the EC2 instance custom resource. We got that YAML. Think of, you get the YAML from the user with the r.get method and store this into a variable. Now, this EC2 instance has a spec which you are reading, and you are using that information to work on. So this is where the user is giving the instance type they want to use. The user is giving what the object is for the storage, what user data they want. That is a spec. We usually use the spec to do our operation. We use the spec of this EC2 instance to create ourselves an instance that the user is asking for. And then the status is for us as a Kubernetes developer to tell what happened with this particular object. And that's where the EC2 instance dot status is where we can tell that what is the instance ID, what is the state, public IP, private, public DNS, private DNS. This is all actually is what we have defined in here. You can see our instance, our EC2 instance also has a status struct, because the way our actual EC2 instance looks like is it has the metadata for the object and the type, and then it has a spec, and then it has a status. And this is what we will be updating now, because we already did an operation. Maybe it failed, maybe it was successful. If it failed, we handled it. We asked Kubernetes to rerun the compiler. But if it was successful, you want to update on the status, and that's what we are doing. So the status for my instance ID, the state, I'm actually getting it from this function. So the instance ID is given to me from this function under the create instance and created instance info variable, which is having an instance ID. And then we are setting up the state, the public IP, all on the right side of these substitutions is given to me by this function. And I'm updating the status of my custom resource, which was picked up by the reconciler. Now, you have associated the output of the function to the status of this EC2 instance variable. It doesn't just update it, however. You need to use a function called r.status.update, because you actually want to update on the status. If you see here, the reconciler has got a couple of functions. One, because R is the type of EC2 instance reconciler, it has a couple of functions. First one is the r.get. This lets you get the actual object which is coming to the reconciler. In our case, think of this as it lets you get the YAML of the EC2 instance object which the user has created. Then the other one is also r.update. In this case, you are doing an update on the EC2 instance. We will be using this. We use this in case of adding the finalizer. You are adding on the object that there's an update, which is the EC2 instance and the finalizer. You can then also update the spec, which is using the using the status function, and you want to update on this status of the object. You are not updating on the metadata. In here, you are not updating on the spec. You are only updating the status, and that's why we tell our reconciler that we want to work with the status of our object, and essentially we want to update the status with this information that we have just added here. So to sum up that again, you use the create EC2 instance function. We get some information from that, and then we are updating our object status with this information. If you were able to update that, everything is fine. But if there was indeed an error when you were trying to update the status of this object, just say, I could not update, I could not update the object, and then you return an error which will try to reconcile it again and will try to re-update your status. And if everything is fine, we reach the end of our loop, and then we just say, it's all done, nothing needs to be done. keep looking for the object updates, and this reconciler is all ended for. However, if you remember, I did tell you a couple of things. If you remember, any update that you do, any update to the object, in our case, the object that the reconciler is looking for is the EC2 instance. If you update this or a user updates this with kubectl edit, it does not matter. If at all there is any update to this object, there's going to be another run of the reconciler. It's absolutely important for us to understand. So the way your reconciler is working right now is, first thing, it gets the object. Second, it tries to create an instance. It then updates the finalizer on the object. Then, if the instance creation was okay, it goes ahead and it updates the status of the custom resource, and then we reach the end of the loop. The problem, however, is you updated the object here. So there was a change on the object here at this place. Because when you update, or even if you want to add a finalizer, maybe you add a label to your object, maybe you add an annotation to the object, it does not matter. Kubernetes does not differentiate what kind of change you did on the object. It says, okay, the reconciler looks for an update. You did an update here. Also, when you were able to create the instance, you got some instant information back, and that is where the status was updated. So here was also an update. The way our reconciler works is it starts from here. It sees that, okay, right now, the instance that the user is looking for, it is not there because it's a new instance. Then what happens is it categorizes this. It's a new instance because this object, when I say object, it's the EC2 instance object. It does not exist in my Kubernetes etcd. It's a new object. Then it says it's a new object. It creates you an instance, and then you add the finalizer, and this is where you update the status. When you have updated the status, you actually give the instance ID in the status. And you can only give the instance ID if you have an instance ID, and you will only have the instance ID when the object was created, when the instance was created for you. So think of this as what's happening here. You got the instance, and then you are updating your status of with an instance ID, and this will be triggering a new reconciler event. Because I'm telling you again and again, every time you make an update to the EC2 instance object, it does not matter whether you update the label, whether you update things in the metadata, whether you update things in the spec, or you update things in the status, and the reconciler will start again. And this is where it is your responsibility to make sure your reconciler is idempotent. Because what's going to happen then, when you reach the end of the loop, it's not just going to wait for new EC2 instance object. Kubernetes remembers it. When it is running through your reconciler, it marks that, okay, this particular operation, which was updating the finalizer, this was an update. So I will rerun the reconciler. It doesn't just stop the execution current one. The current will go ahead. But think of this as a handler in Ansible, if you know about that. It says, this particular step asked me to update my object, which is the EC2 instance. I will run the reconciler once again. And then it goes on the fourth step. And here as well, you update the status of the custom resource. The same thing happens here. It says, okay, this operation, as well as updating my custom resource, I will rerun the reconciler again. So in this case, when your first execution happens, you will start again on your reconciler to be running, and this will happen 2 times because you have updated the object here and here 2 times. When you get a kind of like, when you update the object, the current execution does not stop. It's not like you reach 3 and you start again. It doesn't happen that way. You will run through the entire reconciler. You will keep noting which operations were updating the custom resource, and then for how many times that was updated, the reconciler would be running. And now this is your responsibility to make it idempotent. Imagine, guys, you created this instance, you got the instance ID, and when you run it again, you create one more instance and you update the object, you update the custom resource, then again, you will create a new instance, update the finalizer, update the status, and then you will go again and you will keep creating instances. And this is kind of like a forever loop. And the reason why it's a forever loop is because the reconciler has no state. It does not remember that the last request is where I created the instance. It doesn't have any remembrance of what was happening with this in the end. So it is your responsibility that once I have executed through my reconciler, when I updated the object here, let's say, and I also updated the object here, for this object, when the request will go again to my reconciler, I should be checking the state of the, what is my current state. You have to check the current state and you have to check if this is meeting the desired state. In our case, for the EC2 instance, we have to check that. See, here we update the status. Here we update the status and we give there is an instance ID. When you make a new EC2 instance object, this will not have an instance ID because it is brand new. But once you run this through the reconciler, you create an instance, you update the finalizer, and then you update the custom resource object with the status, and there's an instance ID. It is then you can use in your reconciler. You can check if the request that's coming into me for this status of this object, is there an instance ID? If there is an instance ID, I already have run. I've already worked with this instance before. I do not need to create a new instance, is not needed because this one already has an instance ID. Then you work on that instance, see if that is running, that is stopped. You do the drift detection, but at least a new instance doesn't need to be created. And this is essentially what's happening in our loop. Once we make a couple of updates, in this case, we are updating the spec and also we are updating our finalizer. Here we reach there. So we will say, okay, I'm done with the reconciler. I would have waited for a new object, but because in the reconciler, I did update my status, I'm going to go on the very top of my reconciler and run it again. So it's going to start from the very beginning again 2 times because your reconciler is updating the object twice. Absolutely important. Without this, you will be creating a reconciler that keeps on working and it doesn't really stop, or it doesn't really know what to do. So to understand this a bit better, let's see how your reconciler can go into a loop and do the things again and again and again, and how you can stop this and how do we stop that in our controller. So this is kind of like the request that you give. Imagine this is your EC2 instance request that you are giving. You give things such as your kind. Oh, wait a second. So you give your kind here. You define your object's metadata. And what you are also defining is the spec. That's what you want the instance to be created as. And right now, there would be a status, but this one is actually empty. Because you are creating this object in Kubernetes for the first time, it will not have any status. It will only have a status once the reconciler has run through its logic, and that is the one which will be updating the status. So you feed your object, you feed your object information when you do a kubectl create -f on this object. That is then sent to the reconciler, and the reconciler logic says, I will be creating an instance. Now, this one, imagine what's happening here. It goes to Amazon and then it gets information. It creates you a VM. The VM is running here. It gets the public IP, the state of this instance, which is we are more concerned about it should be running. That's why we have a waiter that waits until this VM is running. And this is the information we get back from Amazon. It's a very simple description of what we are doing in our code. Once we get this, and once we are able to create this instance, what we then do is we update this particular object. In our case, we are updating this for the finalizer. So we update the object to add the finalizer here, and then we update the status of that particular object. Eventually, once the object will be exiting your reconciler, this whole thing here is kind of like the reconciler. This is your reconciler logic. It makes sense for me to increase the thickness so you will see this. This is the actual reconciler that's happening. Reconciler, let me increase the size of that a little bit. There. So the reconciler creates an instance. It updates the object, and this is the output of your reconciler. Apart from the Amazon VM that has been created on Amazon, you get your spec back. And also, one interesting thing is this bit. Now your object has a status. Because we updated on the status. It will also have a finalizer, which I have not added there because I want to keep it simple. But we have a status now. And because you updated the object here, this is very important. Because you updated the object, you will be passing the same object, you will be then passing the same object to the reconciler. And then what's going to happen is you will be creating the instance, and then what's going to happen, you will be updating the object, and then what's going to happen, this is how you will be reaching a forever running loop, which is then going to be problematic. Because the reconciler has no idea that it has created the object already, it has created the VM on Amazon already, it doesn't have a correlation between what it did and what to be done because it has no state. So essentially, what you would be looking for is once you have made changes to your object, which is in our case, you have this status added there, I will change my logic a little bit. What I would say that, okay, create instance if the object dot status dot instance ID is blank, which is then if it's empty, then it's a new object that the user has created. When I'm saying object, I mean this particular YAML. If this does not have a status, or at least it doesn't have a status and an instance ID, that means it has never run through me. The reconciler has never created an EC2 instance for that. And that is when you should be creating a new EC2 instance. Otherwise, if it is not blank, then just skip directly. Do not make any changes whatsoever on the object. Because as soon as you make a change on the object, it starts again, and your reconciler would be doing any change that you make in your reconciler to the object of the Kubernetes object, it will trigger a new execution. You will trigger a new loop. And that's exactly, I have this sort of idempotency done by this particular function. See, we already get the object which is coming to a reconciler using the r.get. We get the YAML, the spec and the status of my EC2 instance in this variable. And then I'm checking if the status field is populated and the instance ID is not blank. You remember now, right? It will be blank if it was a new instance. If it was a new object, and for a new object, I need to create a new instance. But if the object is not new, it will have a status, it will have an instance ID, and then I'm saying if the instance ID is not empty, we simply say requested object already exists in Kubernetes, not creating a new instance because I've already created an instance for the same instance ID on Amazon. That's why you have the instance ID, because I was able to create that, and there's no need. Then simply I would just be returning a nil, and I'll wait for a new update on this object, which is EC2 instance. Nothing to be done. This bit makes our code idempotent. Now here you can be a little bit more chefy if you want. You can be a little bit more, complicating things where you can introduce a drift detection. The thing is, imagine you did create the EC2 instance, which is on Amazon. So here is AWS. You did create the instance and it was in a running state. You get that back and you update your status of the object here. And when somebody will do kubectl get EC2 instance, they will see the instance ID, they will see the public IP, and then they will see the status as well, which is running. That matches your Amazon instance. The problem is, if you go outside and you stop your instance, it does not update the status of your object because Kubernetes does not know what you did to your instance outside. It just doesn't know that. So it could be your feature in the program, in your software, where you can say, if this instance ID is not empty, that means on Amazon, I do have an instance. It might be running, it might be stopped, it might be in some other state. I don't know. I have it. Then I will go to Amazon and then check if it is indeed running or not. So this goes to the reconciler. You will say, you know what? The instance ID is not empty. So I will not make a new instance, but I will just go to Amazon and see if this instance with this instance ID, what is the state of that? So you go there, you find it is stopped, you then update your state from running to actually stop. So you can have a drift detection. If the instance was stopped there, you also update your status here. This is kind of like a chefy thing you can do. In my case, I'm keeping it simple because I'm saying the instance was already being operated on. It is there on Amazon, and it's also in Kubernetes. So I will not do anything. I will not create a new instance. But you can have a drift detection as well, where you take the instance ID, describe the instance, get the state, update the state. We know how to update the state. We did it here. And this is going to be your own little drift detection. And I think that's going to be interesting to build. So if you have followed the course till here, I would really encourage you guys to add this functionality as well, which I'm leaving deliberately because I don't want to make it too much complicated. And if the instance ID was not empty in our case, we already have an object, and then I'm not creating new instance. See, my program will just back off from here. It will not create new instances. And this is actually what's going to happen. So now I'm going to show you a bit of a demo of how all this look like to here. This is where we will actually deploy this to our Kubernetes environment, and then let's try to create and see this in action. I already have this running, but what you can do is, first thing you can do is make manifest. And you know about this. We already did this when you were building the API. This creates the custom resource definition, and then you can do a make install. It installs or creates those custom resource definitions in your Kubernetes cluster. I already have that because if I do k explain EC2 instances, it knows about my instance, which is in the compute.cloud.com. And this is the group, this is the version, and this is what my fields can be for the EC2 instance. I can also do kubectl get EC2 instance, and you can see it doesn't say I don't know what this object is because I did a make manifest, and you can do these things together, make install. It creates you the CRD. It installs it on the cluster. And then so far, what we have built, we can run our reconciler using go run cmd main.go. I'm in the root of my project, and now you can see this is what my reconciler is now running. If you go through the logs a little bit, it starts the manager. The manager manages multiple controllers, and then you can have more than one worker for a controller. And this is what you see here. We start the manager, we start the controllers, and then there are a couple of workers. I only have one, but you can read about multiple workers, and you can create more than one if you have much workloads. But for us, one worker would be enough. Now, to actually create an EC2 instance on Amazon, let me just quickly open up my AWS console and show you how would this look like. And right now, I don't think I have any instances which is running. That makes sense because I didn't make any instances. Let it load. Hello, hello. Let me try that again. Okay, wait a second. Now let me try that again. All right. Probably it was my tail scale that was behaving a bit weird. But as you can see right now, I do not have any running instances. Now what we can do is I have an object which looks like the spec that you would like. Here you can see I want to create an EC2 instance. This is the name, this is the namespace, and I've given my T3 medium, my AMI ID that I want to use. It's in the region for Amazon Linux 2. The region is Central 1, the availability zone. I already have this key pair. I already have the security group. I already have this subnet in my Amazon account because you need these things before you can make a VM. And this is how my instance is going to be created. Now, because we already have our controller running, as soon as I say, please create me an EC2 instance. As soon as I say, please create me this instance, you will see your logs acting up. Let me just do it here so you will see that better. Now let me do a kubectl create. There you see automatically, as soon as you gave a create instruction, your reconcile loop started. And this is the logic that we have given from the very beginning. That's the log we are seeing. Reconcile loop started. And this is where you get the object, you create a variable of that type, you get the object, and then you see if the instance ID is there or not. If it has the deletion termination timestamp, nothing is there because it's a new object. And then you will see creating new instance, adding the finalizer. The finalizer would be added. All that we went through will be happening now. So let's go through the logs a little bit. You can see the reconciler loop was started. And then I see the log of it's creating a new instance, and then you add the finalizer. It's interesting to see this in the object. So if you do kget EC2 instance, you see this is the eventual output you're going to get. And there was an instance created on Amazon for me from my Kubernetes and from my Kubernetes cluster. That is exactly what we were working through. We are able to create an EC2 instance from our Kubernetes environment using the controller that you just have written, and you're able to get the information. The state is running. The public IP is the same public IP that you see here, 35.159.299.229.7. It's the same here. And it is the same instance ID. Now, this time, I got an instance ID because the VM was created. But what I'm more interested to show you is this thing, which is going to be the finalizer. You see? We get the log on the left side. It says about to add finalizer. You can see here, about to add finalizer. And this is what the update that we did to our object. If you see this here, this would make sense. You add the finalizer, which is ec2 instances.computercloud.com, and then you do an actual update on the object. And that's the result of this update function. Then once the object was created, once the instance, let's go forward and see the logs. How did they go ahead? So we say we are creating a new instance. We are about to add a finalizer. We add the finalizer and it says, this update will trigger a new reconcile loop, but the current will continue. As I've already told you, we do an update, we register this so that we will come back and restart the loop again, but we keep continuing. We don't break the existing execution right there. So you add a finalizer to your Kubernetes object, and then we continue with the EC2 instance creation in the current reconciler, and that's where we actually create the instance. Once you make a call to Amazon to create the instance, you can see here, we call the run instance API. The EC2 instance creation was completely successful. And this is now where, for the first time, we get the instance ID. You will only get the instance ID if the instance was created, right? When the instance was running. So we then make another call to Amazon to get the public IP, because you don't just get the public IP as soon as you create the VM. It takes a little time for the public IP to be populated. And we just say, I'm calling the Amazon describe API to get the instance details. And this is where you just print. This is just like some debug that I was doing with this code. And here you can see we get the private IP 172.31.25.250, which is the same in here. If I check that, here you can see 172.31.25.250. That is my output. My domain name is, this is the public domain name. This is the instance IP, the region, and the metadata that was given to me by the describe instance API. You can see the name of the key that you were using when you were creating this instance. And here you now have the public IP. Very important. Till this, we have made update to our reconciler one time. We have made the changes to the reconciler once, which is updating the finalizer. Now we update the status as well. Now we update the status, and what actually happens is now you will be updating things in here. This is the status update. So we do the status update, we update the instance ID, the private DNS, the public IP, the public DNS, and the state of that which is running. Out of these 5 things, we are only showing 4: the public IP, the state, the instance type, and the instance ID. Now, it is absolutely important to remember, we made the changes to our object. The reconciler will be starting again. And there you can see, after you made the changes to your status, the reconciler was started again. However, this time we saw the requested object already exists in Kubernetes and not creating a new instance. This is where we introduce the idempotency in our Kubernetes, in our controller. It is missing one log, however, which is a bit misleading, that you might think because we made updates to our object twice, this should be running twice, and that is absolutely correct. I think it's missing a log. So let's try that again. Now, what might look like there's a missing log entry, and it could give you an indication that I said whenever you update an object in Kubernetes as many times, the reconciler loop will be running those many times. So we updated our custom resource once at the finalizer, and then we update our custom resource once with the status. So 2 times the reconciler loop should be running. But we only see the log entry here once, which says, this is the reconciler loop now started and requested object already exists. We should be seeing this twice, because that's what I've been telling you, because we updated the resource twice, but we don't see that here. And I think it's going to be a lot more clear when we see the internals of how the operator is knowing that there was a change and what really happens internally. So let's say you are working on this Kubernetes resource, which is our custom resource, and you do an update. or you add this resource. Whatever you do, you have triggered a change on this custom resource. Now, any change that you do to any resource in Kubernetes, the first one that knows about this or gets to know about that is your API server. This is where you have your authentication. This is where you have your authorization. And once you have gone through the authentication, once you have gone through the authorization, and also the admission controllers, the webhooks, this will be persisting your change into etcd. This is the time where you have made a commit to the etcd, and this is your source of truth. This is your single source of truth, and that's where you have added your desired state. Okay, that's where you have added your desired state. Now, as soon as the API server makes an update to this etcd, this API server kind of not really broadcasts, but you can think of that. It tells everyone that, hey guys, there was an update to this custom resource, which is of kind EC2 instance. And there are many controllers in Kubernetes responsible for different resources. For example, one is a pod controller, which is responsible for changes into the pod. One is a deployment controller, which is responsible for changes in the deployment. One is a service controller, which is responsible for the service. What they do, they are only reacting on the resources which they have been programmed for. In our case, we do have a controller which is only listening on the EC2 instance type of the resource. So the API server tells everyone, think of this as broadcast, but it is not really broadcasting. It sends an event to anyone who is watching this custom resource. The pod controller watches the pods. The deployment controller watches the deployment. In our case, this EC2 instance controller is watching the custom resource of kind EC2 instance. So this update is listened by this guy, or it's watched by this controller. Think of this as your controller subscribes to the API server, and it is telling the API server, whenever there is a change of in this kind EC2 instance, tell me. The API server registers it that, okay, there's this guy who is watching and listening for it. And then the API server will be telling, once it triggers an update like this, once it triggers an event, then the EC2 instance controller who's watching this update, this event, gets to be notified about that. Now, if we zoom in this controller a little bit, let me create what's really happening in this controller. So this will make more sense, because I just said the EC2 instance controller gets it. But really what happens here is that this particular controller who's watching, the API server, the one responsible for watching or doing the watch is called an informer. Think of informer as a piece of software that opens a long running or a very long living stream to the API server, and it always catches these updates that, hey guys, okay, there was an update, I am now notified about it. This is the part of your controller. Your controller has an informer, which helps you to open a watch to the custom resource that you are interested about. Now, as soon as there was from the API server, it says there is an update, the API server sends this update as well as the object. And the watcher consumes it. The watcher subscribes to it. And this is how this informer, when I say watcher, it is the informer. This informer gets the actual update event, and then it gets the actual object, which is the YAML. This object is kind of like the YAML of our Kubernetes resource. Now, this informer has a couple of things to do. The first thing it does is it stores the object. It stores this object, which is given with this update event, into a cache. This cache is managed in the controller itself. You don't have to do that. Kubebuilder already has bootstrapped these things for you. Using the Controller-Runtime, there are packages that manages caches for you, and this cache is where you are storing your whole object that was given to you with this event of an update. The first thing that the informer does is always adds it to the cache. Then the informer has a couple of something called handlers, or we call them event handlers, or we call them resource event handler. These are, think of this as functions that would be running when you make a new add operation, when you do an on update operation, maybe you did an update to your resource, or when you do a delete. These functions, they are not doing anything except all three. The only thing that they do is when the informer has stored this object into the cache, the informer will be triggering this handler, and based on what you have done, they add this object's key into this working queue, into this work queue. This is the infamous work queue that we have been talking about. Now, what's really added in the working queue is not the whole object of your custom resource. It's not the whole object. The thing that is added in this working queue, is the namespace, and within that, it is the name of your object, which is the name of the EC2 instance kind, and then you have the metadata, so metadata.name. That's what's added. It does not add the entire object, the spec, the status, they are not added there. Now, once your handler has added this in the queue, then in your controller, you have workers. Or we have the reconcile loop that we have been working with, and there's a worker running this reconcile loop. This worker keeps on looking in this working queue. As soon as there is a key in this working queue, which has been added by the resource handler in this case, the worker runs the reconcile logic. And this is eventually how your Kubernetes, how your controller, how your operator gets to know about that there was a change, and so that I have to run my worker. Now, during our reconciler, we did update our spec. We did update our object 2 times. One was for the finalizer. So look at what's going to happen. Once you update this for the finalizer, the same thing begins from here. It's kind of like the same process, because whether you update your custom resource, whether you do this or an application does that, the API server has no differentiation of who made the change to this custom resource. All it knows, there was a change. That's all I care about. Now, the first time when we added the finalizer and we updated the object, the same thing happened. This update was sent to the API server, then it was stored in the etcd, and then your controller was called because it has the same thing. The informer was there. This informer then triggered a handler, and this handler added this particular key in the working queue. And let's give this the namespace as default /EC2. That's the name of my kind metadata.name. This was the name of my object in Kubernetes. That happened. And while you were running your loop, the second thing that you did is you updated, the status. For the status, we updated things like the instance ID, we updated the instance ID, then we updated the public IP. Wherever at any time there's an update, the same thing will happen. The only difference is this working queue is kind of single for one controller. There's one working queue. It's shared for that controller. So the handler adds it here, and the same thing will be happening here. So let's say you update the status now. This update to the custom resource is seen by the API server, adds it to the HCD. Then the informers are watching. First thing, they update the cache locally. They update the cache locally, and then the handler is called. Now, what was happening? This is where the one single log line explanation is coming. See, your handler is responsible to add the namespace and the name of that object in the working queue. But what happened was, when this handler wanted to add it, it said, I want to add an object which is in the default namespace, and the name of my object is EC2. This working queue is smart. In a way, it says an object with the same name in the same namespace that you are trying to add is already in the queue. So I'm going to do something called the deduplication. And this is such a powerful mechanism, because if you did not have that, you will be kind of running a reconciler storm. Every time you make changes to your object, imagine this. While running your reconciler, maybe you made changes to your object 10 times or 20 times, right? You made changes to the object 10 and 20 times. You do not want to run the reconciler 10 or 20 times. Just one run, because you already have that. The same key is available in the working queue. It's going to use the spec of that object and be done with it. This deduplication is already handled by this working queue package in Golang, which is, again, we are using this for the Controller-Runtime. We don't see this, but this is eventually what's happening in the background. So we do not add it again, or rather you can say you add it, but then it is getting deduplicated. Now, once you finish your reconciler, see, this is what happened. You update the finalizer, you then create the EC2 instance. If you haven't forgotten the flow, this is what is happening in our reconciler logic. We update the finalizer, then we add the EC2 instance on Amazon. Now, once we added this EC2 instance, we update the status. And here, once we have updated the status, we are done. The worker is free. The worker now here is free. Now, the only thing the worker is ever responsible for is looking at this particular working queue as soon as it gets free. When I say it gets free, I mean the reconcile loop has run successfully, and now the worker is looking for any other changes, or it is looking if there is a key in the working queue. These are the two reasons why the reconcile loop would be started, or why the worker will run the reconciler again. For the worker to be running this reconciler, there are two ways it could do that. First, there was a change made by the user to the custom resource, which is what I told you, the whole process just now, where you make a change to your custom resource, the API server, and then the worker sees the working queue. Here's the working queue. It starts that. Or second, the worker will be running the reconciler. The worker is going to run the reconciler in case you have some changes made by the user to the custom resource, or your requeue interval is done. And then it's time to retry that again. If in case there was a change to the custom resource, if not, it doesn't do anything. It should not do anything. It should just simply be exiting the reconciler loop. The third reason why it could run after it is finished is there is an object in the work queue. It's kind of like, imagine, you are moving bricks from point A. This is point A. You have a brick here, and you have a work to move this to point B. This is you. So either if there is no brick, let's say if there is no brick, you wait. And every 10 seconds, you see if there is a brick. There's no brick. Okay, I don't do anything. This is the requeue interval. Every X seconds or minutes you are watching, but there's nothing there, so you don't do anything. Second one is, your manager or your owner or whoever that is, this guy places a brick in here. He does it on himself, and then he tells you, I have added a brick. Now you get active, you put this brick in your hands and you move it to the point B. This one's when somebody has made changes, when somebody has made changes to the custom resource manually. The third reason why you might move this brick, is, imagine that this is point A and this is point B. There was a brick. You were watching this. Here, this is important. You are watching this now. So there was a brick. You're watching this. You move this brick there. And while this brick is in the, think of this as it's transporting here, another one comes up. Another one was added. Now, as soon as you finish moving this brick from point A to point B, your work is done. You immediately look at here, there's another one. You move it again. And this is kind of like there was already an object pending while you were finishing your work. Someone put another brick, and as soon as you are done with moving that brick in your hand, you look back, there's another brick, you move that. That's the working queue that we are talking about. As soon as there's an object, your worker will be starting again. And this is why we only see one log entry, because when the worker finished creating the instance, when the worker finished updating the status, it was done, it was exiting, and then it saw that there was a new object in this working queue. In this case, the third, third stage is applicable to us. So the worker saw, hey, I was making, because there was already a key added to this working queue, I started working on that. But something already added another key in this working queue. So as soon as I'm done with the current run of this instance creation, I look there and then I run that again. I run the reconcile once more because there is a key in my working queue. And this is why you only see that once, because we already have this idempotency that if, for our status dot instance ID is not equal to null, that means we already have worked on this. This is the idempotency you have to add in your operators so that it doesn't keep running in a forever running loop. We talked about this already, but this is where you only see that once, because there was only one key added, even though you had two updates, even though you made changes to your custom resource twice, the deduplication happened in the working queue and there was only one object. And as soon as the worker is taking this, it reads the object from there, the working queue gets empty because the worker is working on the only available key. It reconciles it, sees the idempotency kicks in, and then there's nothing. There's no object in the working queue. The worker is now waiting. The worker is happy. Now, the worker will be triggering the reconciler if there was a change made by the user, or when your reconcile interval is you have configured your reconciler to watch for or to ask the API server, is there a change to my object every reconcile interval, which is, I think we have it here. So somewhere around, I think we do not configure a I think we do not configure a requeue interval. So this is also a very small piece of information. When you write your reconciler, I'm not sure if I've explained this already in there or not. I think I did, but let's talk about that again. For the reconciler, you can define a requeue after, which is, if I show that again here in this result, we can send two things. One is the requeue. Do you want the operator to requeue after the worker is done working? You want to try that again for a new object. And what duration after? So think of this as, you might want your controller, in easy words, you might want your controller every 1 minute to run again. Even if there is no object in the working queue, you want it to be running every 1 minute. And this is how you can configure, when you are returning the result, you could say requeue after time.1 second. So this is kind of like making this as a cron job now. You can create your operators as a cron job, or you can make them behave as a cron job by using the requeue after. You say, I'm not returning an error, so there's no retry needed. However, after this time, requeue should happen. So that's like making this as a cron job. Imagine you want to delete the pods which are container creating error state. So you want to scan through all the pods, delete the ones which are in container creating state as a cleanup, and you want to rerun this process after X amount of seconds or minutes. So this is kind of like a cron job, but your operator can do that as well with this requeue after. So now that you have a very good idea of how the internals of your operator are working, where is the working queue managed? Again, the working queue is managed in the operator itself, in the memory of the controller. The informer is part of the controller. The handlers are part of the controller. This cache is also a part of the controller, and this working queue is also part of the controller. The worker is part of the controller, and again, the reconcile loop. It's all what's making up the controller. And that's something important. Now, with this cache, you might think, why is this cache, created here? What is the reason of this cache? Think of this as, when API server makes a change, it sends the update that I have made a change to the custom resource, and it also sends the actual object, which is the whole YAML of the object of the custom resource. It sends an update event. And the object custom resource, or the whole custom resource object, let's put it this way. It sends the custom resource object, and this event is seen by the controller. This event is seen by the controller. Now, what's happening, once this controller sees this event, the first thing or informer inside this controller is the one that watches it. It adds this object into its cache. Or I should rather, wait, I will do it like this. This whole object is actually added by the informer in the cache of the controller. And then you know what happens. There's then the event handler. This adds the key in the working queue. And then there is a worker that keeps looking at this working queue. As soon as it finds that there's a key in the working queue, which is added by the event handler, the event handler adds this key, which is the name and the namespace of the object. Now the whole YAML, not the whole object, but just the name and the namespace, the worker starts it. Now, if the worker needs to access the spec, that's what we are doing in here. Let's say if I say create instance, and that's what or rather if I begin, I'm saying it here. See, I'm checking if this object has a deletion timestamp. I'm reading that object. I'm seeing if that object status has an instance ID or not. I'm reading that. So whenever you want to read that object, whenever the worker logic or whenever the reconciler logic wants to read the object, it does not read it from the HCD. It doesn't go to API server, then reads it from the HCD. It does not do that. It reads it from this cache, which is faster in orders of magnitude, compared to when you were going to the API server and reading it. And this cache is always updated as soon as this update event or add event, or delete event comes in. The first thing the informer does is refreshes the old copy and updates the new one, so that your reconciler will always be getting the latest state from the cache of your custom resource object. And this is how it's reading the object. The worker reads the spec, the worker reads the status. Whatever you do with this object, it's being done from this cache. And this makes it really, really fast. You don't have to go out of your process, or rather the controller, to the API server, then to the HCD, then read the spec or the status. It's right there whenever you need it. So I think this was a very good idea of just explaining why we only saw one line, one run of the reconciler, not two. I think this was the right time for me to explain this, and I hope this is clear to you guys how the API server sends an update, how the informer is looking for it, how the watcher and the informer, which is one of the similar things, is looking at that, how the handler adds it to the key, and then the worker reads the working queue, and then, runs the reconciler logic. Now that you know all this will be giving me a good idea to tell you how Kubernetes handles the object deletion. We talked about how does it create one. We talked about how do we work with the caches, we work with the informers, the handlers, the working queue, how the reconciler does that, how the deduplication works. So now let's talk about how Kubernetes will handle the deletion of objects. This is where the deletion timestamp will be coming into the picture. When you have an object, and when you say kubectl delete the object, the reconciler does not know whether you have asked for deleting the object, whether you are updating the object, whether you are updating the finalizer, whether you are updating the status of that object. It absolutely has no idea about that. And this is where, how would you differentiate that the particular update was to delete that object? How does Kubernetes know the user is asking for deleting this object? It knows about it by adding something called a timestamp, or essentially it's a deletion timestamp. See, if you look at my object now, if you look at my object right now, it's less. It does not have a deletion timestamp. What it has is a creation timestamp. What it does not have is a deletion timestamp. But I can run this on a loop. Let me show you that. Kubectl get pods, and then you can see it here. Probably I can just show you the metadata. So you can see here, this is my current object right now. This is my current object that I've created, and you can see my reconciler is happy. It knows about this object, that it was already created. It is on Amazon, and you can also see kubectl get EC2 instances, and you know the public IP and everything. That's okay. But when you want to delete this, The way Kubernetes knows that this was a deletion operation is by adding a deletion timestamp, and this is what our program can actually look for. So you can see here, this is what the program could look into. Here, that's where you can check if it was a deletion request or not. So as soon as your reconciler is started, it doesn't know the reason why it has started. Was it an update? Was it a delete object? Delete operation on the object? And this is where you can use this deletion timestamp. If the deletion timestamp is 0, then it's not a deletion request. However, if the deletion timestamp is not 0, that means you can say the user has actually requested a deletion. The instance is now being deleted. And then you can call Amazon to delete your instance, clean up properly, and once only you have done the deletion, then you can remove your finalizer. And this is how finalizers are used when you are deleting an object. As soon as you give a request to delete something, finalizer will hold the deletion of that Kubernetes object until the actual resource has been terminated. And if you were not able to remove the finalizer, you do not delete that object from Kubernetes. You just say, try again. You keep on doing it. And once the instance was gone, then eventually you let the finalizers be removed, and the object will actually be gone. Now, this is what you will see in the logs. Right now, as soon as I will do, let me go to the directory, and as soon as I will do delete on this EC2 instance, I hope you can see this in the in the size of the font. What I essentially want you to look at is, as soon as we give a delete request to Kubernetes, there will be a new deletion timestamp. And because it is an update to our object, the reconciler will be started. Then the reconciler will know, oh, it has a deletion timestamp. So basically, I need to delete my instance and then delete it from Kubernetes. So if I do kubectl delete, see what happens. It got a deletion timestamp. Automatically, my object was updated, and then my Kubernetes reconciler started again, and it saw, oh wait, it has a deletion timestamp. And you see my object is not deleted yet. It's waiting. It did not give me the response back. It's waiting because I have a finalizer that is holding the deletion. So you see, it says has update deletion timestamp, instance is being deleted. Then we call the delete EC2 instance function, which I'll just show you. The instance termination was initiated, and it is waiting for the instance to be terminated, which you go here, you will be seeing the instance is no longer running because it is right now shutting down. This is the instance that we just created. It's right now shutting down, and I'm waiting for my object is waiting until it goes into the terminated state. As the other instances are in terminated, we want for the instance to be properly terminated. And once the instance is now, you can see it's terminated. See what happens? We're waiting for the instance to be terminated, and let's just give it a little time to actually, the maximum time it's going to wait is for 5 minutes for deletion. This will be then updating and removing the finalizers for me. And eventually that's going to be then cleaning up. And that's what happened. I only was able to delete my object once the instance was terminated. You see here, waiting for instance to be terminated. It was waiting, and then once it returned the terminated state, we say EC2 instance successfully terminated. And again, because you deleted this object now, it is another update on the reconciler. So you can see the reconciler has started again. So see what happens again is, this is very interesting. Any update that you make, it starts. So what happened is you have an object, you do a deletion on this object. This object gets a deletion timestamp. And this is seen as an update by the reconciler. The reconciler runs, it sees, okay, it does have a deletion timestamp, so I need to talk to Amazon to delete this particular instance. I need to delete this particular instance. And once it is deleted, once it's deleted, what I will do is I will remove the finalizer and then let the object deletion be done. And here's where you're making an update again. Now see what happens? If I go back to our code, how it works, you can see we delete the EC2 instance. This is a very simple delete EC2 instance function. All it does is it says deleting the instance, and then it runs the terminate instance function for terminating the actual instance. It waits for it to be terminated. This is quite similar on how we were doing a running waiter. We have a terminated waiter, and we wait for the waiter to actually return terminated, and then we say instance was terminated just fine. If we were not able to terminate that, if there was an error, we try again. But in our case, we did not have any error. That means we were able to terminate the EC2 instance. That means this cleanup has happened. Now I can remove my finalizer. And this is again an update. This will again start the reconciler. Absolutely important. Any update that you make, it's going to start the reconciler. So you remove the finalizer using the controller-runtime, using the controller utils, and you say, please remove this finalizer, and then you update the object. And there you see, as soon as you update the object, Kubernetes says, cool, I will go back and run the reconciler again. And at this point, the instance is terminated and the finalizer is removed. We go back to the beginning of our reconciler here, and that's what you see now in the logs. When we were able to terminate the instance, because we updated the finalizer at this location, the reconciler loop started again for a particular object. But you see here, it's quite interesting. Between the time when you remove the finalizer, when you were removing or you removed the finalizer, which is registered as an update to the object, and a new run of the reconciler, your object in Kubernetes, is actually gone. It's deleted. Think about this, that the custom resource for which you remove the finalizer, it's UID, because every resource in Kubernetes has a UID. Think of this as it has a UID was ABC. Then what happened? You removed the finalizer, and then you updated the object. Let's start that again. So between the time when you remove the finalizer, which is registered as an update, your object was actually deleted, but the reconciler says, because you updated, I'm going to start the reconciler again from the beginning. And I will start it for an object whose UID is ABC. It's not a new object. Because you updated an object which existed, and then it was not existing anymore, but the reconciler does not know that it is deleted. It just says, I start the reconciler again for the same object. And this is where you have to tell the reconciler that even if you are starting again, if you try to get the object and you get an error, you will get an error because there is no object that exists with that ID that you are trying. But if the error is not found, when you do kubectl get pod xyz, you get the pod is not found. It's kind of like that error. Simply just say, okay, it was a cleanup. I will not do anything, and I'll just wait for the new request. And that's what's happening in our logs. it started again. You updated the finalizer. The object was deleted. The update was registered. The reconciler was started for the same reconciler object, but it is gone now, and that's where we are handling it. We say, or otherwise, the reconciler would have said, not found, not found, not found. We want it to be handled saying the instance was deleted that you are trying for. If you cannot find this object, it's okay, because that's what you get. Not found. That was the error. That is not found. And that is the entire end-to-end functionality of our controller. By this time, you know how to create resources on Amazon. Your controller is able to ignore or have idempotency, so it doesn't keep running the loop again and again and again. It can handle the termination of instances. It can handle the finalizer as well. And only when you remove the finalizer, it will clean up, or it will let Kubernetes clean up the object and subtly ignore if the object, for which there was an update that was registered and the rerun of the reconciler happens, but the object is gone meanwhile. We handle it that if you try to get the object and the error that you get while getting the object is not found, Kubernetes has a package called errors, which is where all the errors are defined. You see, is already exists or is not found. Sometimes you create an object and you get Kubernetes says this already exists. And you can use these error types in your program. I'm using one which is called is not found. And this is what it says. Is not found returns true if the specified error was created by new not found. So you are trying to get an object, but you get an error because it doesn't exist. And the error is not found. So that's what we are doing. If it's not found, simply say, okay, the instance is deleted. No need to reconcile. And I'll wait for new objects to be coming up to me. And that is what you will see. This loop now will only run when a new object of EC2 instance type is created or updated. Let's try that again. I will do it that please give me a new instance. Because I don't have this object in Kubernetes, it's going to be creating a new VM form. So let's do that. And you will see this in action again. Create, and you see on the right side, the reconcile is started because there was an update, which is create on our instance. And this is the same thing happening. We see that this object is new. So we create the instance again. We add the finalizer, and then the finalizer was added. And then I call the Amazon API to get me an instance. I describe the instance, get the public IP, and I update my status. Go back to Amazon, and you will now see that there is an instance which is running. There we go. This is the instance which is now, it's in the running state. And we had a waiter for it to wait for the running state, for the instance to be reaching the running state. And this is the same public ID, and this is the same thing that we see in here, 364, 147, 52, and the same instance ID. Now, I will actually, I wanted to show you something, which is, again, that's what's happening here. We do get the object, and as soon as we update the status, the reconciler starts again, and it says, the requested object is already existing because you have an instance ID. I will not do anything. Try the deletion again just to see it's working. I do a deletion. This time I will get the deletion termination timestamp, and we will clean up the Amazon instance. Then we remove the finalizer, remove the object, and handle the next run of the reconciler by saying the object was deleted. It's okay. Nothing is required to be done. So you see, it got started again. It found the deletion timestamp. That means the instance is being deleted. See, you will not have the deletion timestamp if you do not delete an object. I showed you in the previous examples. It was only having creation timestamp. But as soon as you add a deletion timestamp, that is a cue that you are trying to delete an object. And that's what we are looking for. If your object has a deletion timestamp, that means it should be terminated. And there you can see my instance state is changing from running to shutting down, which is what we saw before as well. It will wait for some time for that to be terminated because we're using a waiter. Golang, the Go SDK for Amazon lets you wait using these waiters instead of you waiting for 2 seconds, then polling again, then polling again. There's a waiter that lets you do it very, very easily. Or you can also do kind of like long polling if Amazon supports it. I'm not sure, but you can do a periodic polling that you wait for 5 seconds up to 5 minutes, and then you poll if the instance state is terminated and blah, blah, blah. But you see here, my object is holding the deletion, or Kubernetes is holding the deletion of my object. I'm waiting for the finalizer to be removed, and the finalizer will only be removed when the object is cleaned up because of our logic in here. We wait for the object to be deleted. If the object was properly deleted, then only I remove the finalizer. Otherwise, I just send an error and I go back to the beginning and try that again, try the deletion again. And because I would be able to terminate my instance, it's waiting a little bit longer. And this is the beauty of using a waiter. It's not like you are waiting for dedicated 5 minutes. If using a waiter with the Golang SDK of Amazon, if the instance is terminated even before, you don't wait for the entire 5 minutes. It's more efficient waiting for the resources. And then you can see now it is terminated successfully. So you remove the finalizer, that triggers that registers an update. Your object is deleted. That registered update start the reconcile loop again, and then you say cleaned up, no need to reconcile. This is the beauty of Kubernetes operators. What this shows you is that you are able to manage your Amazon instances right from your Kubernetes environment. And this was entirely that this course was about. You can make this more chefy, as I said. You can have a bit of a drift detection, or in my case, I didn't have it because I want you guys to build it in your own program where you can say, if the instance is stopped on Amazon, it updates my status of my of the Kubernetes object from running to stopped. It cleaned the public IP, that all. But this is a very, very good example of using Kubernetes as a platform to manage other platforms. You can use Kubernetes not just as a destination platform for your applications, but you can use Kubernetes as a platform to manage your resources on any other platform, which is the beauty of Kubernetes. Expanding it or extending that using the operators is what you can do. So this was the entire demo. This was the entire code that I want you guys to try again. And now let's see how you can package this properly with Helm and how you can actually run this inside of Kubernetes, because right now, this one is running on my local computer. It is using the kubeconfig environment variable to actually connect to my Kubernetes. But let's package this using Helm and then see how you can ship it and you can run this inside of Kubernetes. And let's get started there. So now that we have seen our application, our controller is running end-to-end and it's able to create the EC2 instances. The way it is running right now is there's my computer and I'm running the Go. I've installed Go there and I'm running it with Go run. Here's where the reconciler is running, connecting to the Kubernetes cluster using this kubeconfig environment variable. There are a couple of environment variables as well, which is the AWS access key and the secret key, which is used to connect to Amazon and eventually create an instance because I need to authenticate to Amazon. And from there, we are able to get ourselves an instance, and this gets reflected in my Kubernetes cluster. The thing, however, is you're not going to be running this application here. Essentially, an operator runs inside your Kubernetes cluster. It's running here as a pod, as a generic pod that has access to the credentials needed to talk to your Amazon environment. This pod is running in Kubernetes with a service account. Now, it's quite important how RBAC plays a role whenever you are writing an operator. Imagine this is a namespace called name A. Give it any namespace. And you have another namespace under which your operator is running. Let's say this namespace is actually called bidding. You have a team whose name is bidding, and they do bidding for clients, and they are using your custom resources, which is the EC2 instance. So they create an object of EC2 instance. Now, to let your operator know that in this bidding namespace, there has been a change in the EC2 instance object, because your operator listens on these objects and changes, you need to run, you actually need to give the access to the operator pod, which is running with a Kubernetes service account. So you need to give the service account access in this namespace to be able to list, get, the basic Kubernetes RBAC. You need the service account to have access to these namespaces for the object called EC2 instance. And you would be needing to give the service account access to both read of this object and also to write for that object, because you need to update the status of this EC2 instance. So both of them are needed. And this is how your operator will be able to manage this namespace, or at least manage the object EC2 instance in this namespace, and be able to go to Amazon, create an instance there, and eventually update this EC2 instance status, giving the bidding team the public IP of the instance which was just created for them. For that to be running inside the namespace, for this operator to actually be running in the Kubernetes cluster, we need to build a Docker image. And this is no brainer. You saw this coming miles ago. We need to build this image, and you will be pushing this image to a repository. And from there, you will be creating a deployment in Kubernetes. You will be creating a deployment in Kubernetes that uses this image, and then you will be deploying this pod, which is the operator pod. You also need the credentials here. You need the AWS access key, and you also need the secret key. Now, you will also then need to create a secret in Kubernetes, reference the secret in this particular deployment, and then roll out that pod. So eventually the pod has the logic for creating our instances and managing them on Amazon. And then it will also have the right authentication artifacts needed to talk to Amazon. For this building of your image, there is a Makefile available from Kubebuilder, which is very, very simple. So let's see how this looks. This is a Makefile in the project, which is from Kubebuilder. And first thing you will need to change here is the URL of your image, where you want to be able to push the image, where you want Docker to tag this image and eventually push it for you. For me, it's my Docker Hub repository, and I think I'm keeping this public. So if anybody wants to use that, they can. And this is the Docker image, and it has lots of targets available. You have this Makefile, and you already used it for creating your manifest. When you update changes in the API spec, you had to regenerate the manifests, creating the custom resource definitions. You have some targets for testing your application environment. You also have some linters available, and here's where things gets interesting. You can just say go run what we have been doing, go run cmd main.go. We can also say make run. So it's kind of like an alias. It generates the manifests, the boilerplate code. It formats your Go code, and also runs another vet. What is it? It runs the Go vet against your code. What we are looking for is the Docker build. It has a target called Docker build. Essentially, what it just does is it runs your container tool. For my case, it's Docker. So it will be running docker build -tag, and it's giving me the image tag, which is what I have declared above here. And essentially, it builds me a Docker image with that particular tag. And then I can do a Docker push to push my image to a registry. Now, this goes without saying that your Kubernetes cluster will need access to this container registry, because without that, they will not be able to pull the images. You also can build images from multiple architects. Right now, I'm only building for ARM because I'm running this on Mac, and my Kubernetes cluster is also running on Mac. So it's all ARM for me. But you might be building this on your Mac, and you might want to run this operator for an AMD machine. You can use a Docker BuildX target to build it for different platforms and then generate a single manifest and be able to deploy it there. This Makefile makes it very, very simple for you to be able to build your images for your platform that you are running with, or for cross-platform as well. So let's do that. I will do make docker build, and what this does is it's building me the Docker image from my main branch for this repository, which is the EC2 operator. Now, this is where it takes a little bit time, you see. It's building it for Linux, but it's building it for ARM64 architecture. And this is where we are building our source code into an executable binary, which is going to be called as manager. So let's wait for that to finish. And once this will be done, you can see the Golang version we are using is 1.23. If you want to see the Docker image, it is very minimal. You are using the Golang 1.23 as your builder. You copy your Go mod, you copy your Go sum, set up a working directory, copy your APIs, internal, your main.go, and eventually you go ahead and build your manager, because this is the one which is running your controller manager. From the distro images, you just execute this manager binary, which you have built with Go with a user 65532. So it's a non-root user, which is a good thing. You always almost want to run your container images with a non-root user for security reasons. And once your image is built, I can simply say make docker push, and this is going to push my image to the registry. I've already pushed a couple of few layers because when I was trying with this course, I have it. And now this one is pushing your container registry, your image to the registry. If I want to see this, let's go to Docker Hub. Can I see that here? Of course. So hub.docker.conf, and there will be the image. Search for my username, and there will be a couple of images I have. What was the name of the image? EC2 Kubernetes Operator. Here it is. So this one is where I have the tag, which is only latest. You can have a CI/CD pipeline. If you're storing your code in GitHub, you can use GitHub Actions to always update your images in case your API spec is changed, in case your main.go file is changed, or your internal folder, which contains the actual controller logic, has been updated. You can trigger a new build, and then you can trigger a new deployment. With this thing aside, we have our image. However, these artifacts still are needed. We need a deployment. We need the secret. For this deployment to work, we need a namespace. So building this image wasn't as big as a problem because you need to have quite a few of resources here. You also need Kubernetes artifacts for the role-based access control. You need to give the service account running this pod access for EC2 instance resources on the cluster level, because it should be able to work in any namespace, at least for this object only. So this RBAC is also required. So you should be getting where we are going with this. We need something to be able to ship this application for other customers, and that's what we will be using Helm for. You can create a Helm chart, which will be, one of the things that I wanted to do with this course is a Helm chart, which shows an end-to-end delivery of this application. Helm, you can do that yourself. We have the Helm init command. It makes it very simple for me to create a Helm chart. Then you will update your deployment to set the environment variables from the secret. You will create the secret. It's simple. However, there are two ways in which you can do, in which Kubebuilder can actually help you. So first one is you can do make build installer. There's a target called build installer, and what it does is it reads your Makefile. It reads your Makefile. It reads the image that you have. It then generates a file called dist/install.yaml. And if I show you this file, what this looks like, it's a new file. And you see, it has all of these artifacts which is needed for your application to be deployed in Kubernetes. So it creates a namespace called EC2 operator-system. Then it has the custom resource definition, which is our EC2 instance. Then it has the service account, which is going to be running our actual pod. Then you have a couple of roles. You have some cluster roles. You have some cluster role bindings. At least it lets you be able to create, update, delete in this API group for these resources. Kubebuilder really helps you to be able to bootstrap your deployment strategy. So with a Makefile, with this target, you can create a single deployable unit. And here's the important thing. It gives you a service as well as it gives you a deployment here. This one, you see, it's using our image that we just had pushed. It has a couple of liveness probes. It has some readiness probes as well. In our program, we did not create an endpoint at /health. We do not have a liveness probe. We don't have a readiness probe because I wanted to keep it simple, focusing on the operator. So you will probably be removing them. So getting rid of, the liveness probe. It's here. And then you will be getting rid of the readiness probe. When you're actually deploying it for production, these things are really, really good to have. So you can check the health of your, you can check the health of your operator. Now, for this run container, because you also need some environment variables. So you will see, you can say environment, and you can see here, you can have these access key environment variable and secret key environment variable, and it's coming from a secret called AWS credentials. And then in the end, you can actually append here, and you can create API version secret. There you go. Some random data is being filled, but that's okay. This will give you a complete deployable YAML file, which you can just do a kubectl apply -f and be able to deploy this application. However, there's no version control on this file, as we would be able to do these things on a Helm chart. Somebody who wants to deploy this controller, they need to know the the lower level details of where to create the secret, where to update my AWS access key and secret key, where do I update my controller parameters in the deployment. So that is still a problem. And that's where Kubebuilder helps you. Instead of giving this big file, which is a single deployable unit, you can use Kubebuilder edit command. What it does is you can tell Kubebuilder that I want to use the plugin Helm/v1 alpha. Essentially, this gives you a Helm chart created to deploy your operator. And if I do that, you can see here, generating Helm chart to distribute the project, and you don't have any webhooks created, which we discussed in the beginning. So it doesn't do that. However, it gives you all these role-based access controls. It gives you all the templates for your deployment, for your service account, for your services, everything in the dist chart folder. And this is how your Helm chart would look like. If I want to show you, this one is created here. So the name of your chart is EC2 Operator, which is also the name of your project. And once you have this, you can look at the templates where the actual resources, Kubernetes constructs are created. You have them for CRD, which is the actual custom resource definition. And of course, we want to be able to deploy that. The Cert manager for the issue. So what you see in the template folder is a couple of resources created, which is the Kubernetes construct. We have the CRD, which is essentially what we want to be able to deploy. We also have Cert Manager, which is going to give us an issuer certificate. And this is for the webhooks in case we were using any. We want to use Cert Manager for that. Here's where the interesting thing is. This is the deployment of your manager. This is where you will be using a values file to define your the values for your resources. You also can see if you have metrics available for the service, if you have metrics available from your operator in case you are sharing them for Kubernetes. You can create some network policies. You can have Prometheus service monitors, and then here's where a plethora of RBAC rules which are created for you. So this makes it very, very simple for you to ship your project without you doing a Helm init and actually creating all these resources by yourself, letting you easily control the behavior of your operator by the single Helm chart with the values file. So the values file, which is shipped with the Helm chart that we just built with Kubebuilder, it controls the deployment of my controller manager that I'm shipping up with my operator. So this defines how many replicas do I want of my controller manager, where's the image coming from, and this is something that you pushed with Docker. So if I do Docker push, this is where the actual image was pushed. So let's take that and let me change that here. Now, there are a couple of arguments available to your controller manager. I don't need the push, so that can be taken out. There's a couple of arguments available. The first one is leader elect. This is something you would be using in case you have a leader election where you run multiple, replicas of your controller. In our case, we are just running one, so it doesn't make much sense for us. And there are two arguments, which is metrics bind address and the health probe binding address, which we will talk about in a little bit. This is a standard concept of Kubernetes where we define how much limits for my CPU and my memory the application would be needing. And here's where it is really, really interesting. See, usually when you are building an application, it is your responsibility to run an HTTP server inside of it if in case you want to use the HTTP GET type of liveness probe or the readiness probe. And it is your responsibility to create an endpoint. For example, in this case, it is the health endpoint, and so is the ready endpoint as well. Usually, you write the application, you make these API endpoints available, and then you tell Kubernetes that check my application on this port number and on this path and see if you get a response which is 200. If you do that within this period seconds and the delay, after the initial delay, my application is live, my application is ready. Otherwise, do what you need to do in case when an application fails its readiness probe or the liveness probe, which is either you stop sending traffic to it or you kill the container and redeploy that. We did not create any sort of API for the health and the readiness right now. And that is the beauty of this operator framework that we are using, which is Kubebuilder. These API endpoints are already available to you in your controller, so you can make use of them right out of the box using the readiness probe and the liveness probe. And this is where I'm configuring that my health probe binding address is any address in the container, and it's on the port number 8081 on which my health and the ready probes are running. It's also important to understand that you get some metrics out of it, out of the controller manager already. When you're using Kubebuilder to write your own operators, you don't have to implement the logic of how would I export some metrics of my application. It is automatically done for you by Kubebuilder. Of course, it's a very limited set of metrics, which we will see. We will explore what kind of metrics there are available, but it makes total sense from the controller's point of view if it's working properly or not, how many times it has reconciled, how many times it has failed, how many times the reconcile loop is successful. All of that is right out of the box for you to use in your operator. Then there are a couple of security related contexts that we don't want to run our container as a root user, and the service account name we want to use. And here's where things gets interesting. See, when you are working with Kubernetes, you usually in the same cluster, let's say this is our Kubernetes cluster. In this cluster, you create a namespace for your operator. And then there are, this is a customer namespaces. So here, let's say I give this as EC2 operator. This is where my operator usually would be living, which is running as a pod. And here is where I will be creating my object, which is EC2 instance. Now, if a developer is creating this, object in their namespace, the pod, or my controller, I should say, should be able to react on this change, because that's the object that my operator should be listening into. Rather, if there was any number of namespaces anywhere in the cluster, if the EC2 instance is actually created or deleted or updated, my operator should be able to see that change. And this is why my operator pod is running with a service account. I will need to give access to this service account, that this service account has a role and a role binding, or a cluster role binding, which allows the service account to list, get, update, patch, watch, delete the changes happening on this particular Kubernetes object. That is absolutely important. Otherwise, you will only be able to create your instances in this in the same namespace, but that's not what we want to do. A pattern for Kubernetes is you create your operator in a different namespace, in a dedicated namespace, and you let users use that operator in their own namespaces by creating the object on which this operator would be listening onto. And that's what we are doing here. We want to enable all the role-based access control needed, which is again coming from the templates and RBAC here. All these role-based access control roles, role binding, cluster role, and the cluster role bindings that are required for my operator, which is running with this service account, to be able to list, get, patch, update all those Kubernetes related constructs that I can do on an API endpoint, and I want it to be allowed. Otherwise, it would be you who have to figure out what roles I need to give to my operator, what role bindings I need to give to my operator, what on the cluster level I need to do for allowing it access on the namespaces on the EC2 operator resources. So this Helm chart from Kubebuilder really makes it simpler for you. You can also control if you want to enable the custom resources. So this Helm chart does not just deploy the controller, it also deploys the custom resource definitions for you. And here's where you can say enable true, that yes, I want to deploy the custom resource definition as well. And I want to keep them in case someone does a Helm uninstall for my chart. See, you will be using this Helm chart to deploy this operator. You would be using this Helm chart to deploy this operator. Now, you might decide that I want to uninstall, but what to do with that CRD? Would you like that CRD to be here available? So somebody could also deploy an operator, maybe manually, creating a deployment. At least your cluster would understand the custom resource definition. Or you also want to clean this up. This is the flag where you can just use, it will be keeping the custom resource definition, or it will be deleting the custom resource definition. There's also metrics available. As I said, the operator that you have written with Kubebuilder, it comes with pre-given metrics available. We will explore these metrics, and you can say that you want these metrics to be exposed or to be accessed from outside the pod. And for that, what it does is it creates you a service in the namespace. So if I go to my templates and if I show you here metrics, and here's what it's doing. If values matrix is enabled, all it does is it creates you a service type of resource in Kubernetes, and the target port, the port on the service is 8443, and the target port is also 8443. However, in our case, the metrics port is listening on 8080. So I will change that here to 8080. So this will create me a Kubernetes service type, which will be listening on port 8443 and forwarding it to my pod at port number 8080. This is used by the Prometheus service monitor. Again, my cluster does not have Prometheus installed, but if it would be installed, this enabling of the Prometheus key will be creating a service monitor, which then uses this particular service to see if the pod is running or not and to scrape the metrics from it, just to show you in Prometheus. And then you can have a dashboard available on that using that Prometheus as a data source in your Grafana. Pretty straightforward stuff. And here's where we have access to controlling in case we want the Cert Manager injection to our webhooks or not. Right now, we are not working with any webhooks, so I'm just going to keep that as disabled. And I'm also not using any network policies, so I would be disabling that as well. You probably want to allow this if in case you want to have metrics, and those metrics should only be created by Prometheus running in a certain namespace, and you can use metric policies to control that behavior. Now, once you have this, we can deploy this Helm chart, but it's missing one thing. See, your pod is responsible to go to Amazon and then create resources on top of that, which happens to be an EC2 instance. You need access to Amazon. In that case, you need the authentication. Now, when we were doing this locally, which I explained to you, when we were doing this thing locally, I had my Amazon environment variables already exported. But right now, my pod does not have them. The code reads them from environment variables, but I also need to set them in my pod. So you have to set some environment variables for the AWS access key and secret key so that you can authenticate to Amazon. And that's what I had already done in my shell. If I show you env grep for AWS, and you can see these are my access key ID and this is my secret key, which again, by the time you are watching this, I already would have disabled them because there's no way I want those keys to be exported publicly. Now, once you see this, what you can do, there are two options for us to pass these environment variables into our controller. The controller is created by a deployment, which happens to be here. So this is the deployment, which is responsible for deploying our controller, which is using the image that we have given, which runs the manager command that's being set by the Dockerfile when we build this container image. And here's where we can define some environment variables. You can create a secret. So you could do something like this. So I would say AWS secret.yaml, and this is going to be kind of secret. And you can see you can create a secret called AWS credentials in that namespace, and then type is opaque, and you have your AWS access key and the secret key. Of course, you will put them as plain text, and then you can refer that secret. For example, in here, I can say access key ID and secret key ID. That's one way of doing that. And that's probably a better way because you have your sensitive data in a secret. You use that secret into the deployment, and then you deploy the application. Eventually, it's going to get the secrets it's going to get the sensitive data, which happens to be the access key ID and the secret access key from your secret, and then the code will be running fine. That's one way of doing it. Another way of doing that is, which I'm going to do, and that's a little bit, that's quite wrong. We should not do that. But for the demo, I'm just doing it. This deployment that is created by the Helm chart, it reads the environment variables from values.controller-manager.container.env. So I can actually set some environment variables like this. This is my AWS Access Key ID, and this is my AWS Access Secret Key. Of course, this is something you would be creating a secret for and then referencing, which I just showed you. But for me to keep it simple, I'm just showing you there's another way of doing it, which is a bad way, but you have been warned. So be very careful about controlling your access key IDs and secret keys. You should never put them in plain text in your code or in your Helm charts or in your values file. You should never do that. Probably in this case, when you are on a journey to build an operator, you already know about the external secrets operator project. And that's what you would be using to read these secrets from a secrets manager like Vault, like Google Secrets Manager, or they have integration with other things as well. Now, once we have this, once we have our controller, we define the number of replicas I want, we define the environment variables, we have the right image repository, we define the liveness probe and the readiness probe and everything else. It's time to deploy this Helm chart to our cluster. And for that, I can just go to dist chart because that's where it is created. This is my values file. I can say, let me just see if I have any errors in my file somewhere. And probably not. It looks good to me. This is the range again. This is the end of the if condition. Looks good. So let's do that now. Helm install. First off, I have no EC2 instances. I already have the custom resource definition because I was trying this Helm chart, but let's delete that as well. Delete the custom resource definition. So that is deleted. My Kubernetes resource does not understand. It could not find the requested resources. And let's do that now. So Helm install, give me install my EC2 operator Helm chart. That's the name of my Helm chart. I want you to create the namespace. The namespace name is EC2-operator, which is already existing, but if it's there, it doesn't do anything. So there's no problem. It's kind of like an idempotent field. And here's the values file, and dot would be my Helm chart that I've just created. Now, let me look at the pods, and you can see the pod is running now, which is using our image. If I describe that pod, here we can see we have the liveness probe, we have the readiness probe, we have the environment variables as well. And this is running. We can do k-cat pods. It is running on this particular node. Now, I'm using K3D, and I have got some nodes available. There's one control plane, one is master, and then there are two worker nodes that I have. All of them are actually Docker containers. If you remember, when we were setting up the environment for our, the development environment, we are using K3D. And if I do Docker ps grep for agent 0, you can see K3D EC2 operator agent 0. That is the same name of my worker on which this pod is running. What I want to show you is if I exec into docker exec -it sh, if I exec into this container, I can get the IP of my pod, and I can say port 8080/health. It doesn't have cur, but if I do wget, that also fails, saying on this IP port 8080 there's no health. Let me check what was the endpoint for my health checks. For the health probe, it was 8081. That's correct. So I need to look on port 8081/health to find out if my pod is healthy or not. And it says health already file exists. Let me do a little cleanup. Health ready metrics, because I was trying this before, so it was already there. Let's start from the beginning. I want to see inside my controller on this pod 8081, is there a health endpoint? And you see health is saved. If I do cat health, it's okay. So this tells me my health probe, my the liveness probe is working fine, because I have on this port number, I have this API endpoint, and it returns me a value of okay. The same thing goes on if I use the ready endpoint. Maybe let me increase the font a little bit. And here you can see I also get ready is saved. And if I do cat on ready, that's also okay. So on both of these endpoints for my liveness probe and the readiness probe on this port number, on both of these endpoints, I get an okay. That means these endpoints were created by the controller runtime for us so that we can do a health check. It's also interesting that we have some metrics as well on port number 8080. So if I do wget on port number 8080 on the metrics endpoint, you see, there was something available on this endpoint as well. And if I do less on metrics, these are all the Prometheus metrics which are already built in and exposed by the application which you have built. This is not what you have done. This is already given by the controller. And here's where you can see the controller runtime total. How many times the controller runtime has reconciled and resulted into an error? How many times it reconciled and resulted into a requeue, a successful requeue after? And all of this is what you can use this information. You can use these informations and how many errors total you have had so far to show a dashboard of how your operator is doing. And with these metrics, if in case you see that the errors are going up, you can make changes to your operator, you can make changes to your code, eventually to be at a better stage than the previous one, because you have metrics, you have insights of how this is going on. You can even do your own code instrumentation for a bit of metrics. For example, you can tell how many EC2 instances have been created by this particular operator. Having Prometheus in your code and then exporting those metrics in a way that Prometheus understands it and can scrape it is a different topic altogether. But if in case you know that, it would be nice for you to have this instrumented in your code, and then you can export this information of how many EC2 instances were created, deleted, so you can know how much people are using your particular your operator. So it looks like my pod is running. It looks like my pod has got the right health endpoints. My pod has got the right health and the readiness probes, and also I've got the metrics available. But now I want to create an instance because that's what it should be doing. It's okay, everything is happy, but is it really doing what it's supposed to do? So let's do that. And I'm going to look on the logs of my EC2 operator. You can see it's starting the workers. It's all healthy. It's waiting for my resources. And now what I'm going to do is I'm going to do the same thing what I did when we were running this out of the cluster, which was on our computer. And I'm going to create an EC2 instance, which looks something like this. This is my EC2 instance. I give the instance type, the AMI ID, the region that I'm using, the availability zone, the key pair. This is something we already had used before, but I want now that operator, now it's running in my Kubernetes cluster to create me this instance, because eventually that is where you will be running this inside of the Kubernetes cluster. So if I do create, this is the moment of truth, what we have been working towards so far. And right now, for me to keep it simple, you can see AWS console. You can see I do not have any instances running. So there's nothing running. Let's do that. And I will do a create. Now, as soon as I did that, this output should be looking familiar to you. This is where we got a request. It says the request was new, so I'm creating a new instance. And then we go to Amazon and we add a finalizer. We go to Amazon and we wait for the instance to be running. And you can see the instance is already created. If I do EC2 instances in the default namespace, and here you can see. Can I ping this instance? Of course. And that was the beauty of my operator. I got an EC2 instance, which I can access right with the public IP from my computer, right from the public IP of my of my comfort just to get kubectl get instances, get the IP and log in, and I start working there. The important thing is this object EC2 instance is in the default namespace, and my operator is actually running in the EC2 operator namespace. So these are different, and this is what I was talking about here. This namespace is default, and here's where the object was created. And this is the pod which is running in my EC2 operator namespace, went to Amazon, because here's where the instance available. You can see it's running now. And once it's done, my EC2 instance operator went to this object and it updated the status. So my operator needs access to not just read the object, but also to write to that object so that it can update the status, such as it can give you the state of this instance, the public IP, and the instance ID that was created on Amazon. And that is what we have been looking forward to, so that we can, we can go ahead and create our instances or manage our Amazon environment. To clean it up, so I can show you, it's actually also deleting resources. Let me do a little bit of, a buffer. So we start from when we delete our instance, what happens? As soon as I do a delete, my reconcile loop starts because there's an update to the object and I see it has a deletion timestamp, instance is being deleted. So we print that we are now deleting the EC2 instance, and then we use Amazon API to send a terminate request to our instance, and then we wait for the instance to be terminated. And that's essentially what's happening in here. So you see it's not running anymore. It is now terminated. This was the instance which was terminated. And as soon as it got terminated, my waiter said, okay, it's all fine. It's not terminated. And eventually I was able to delete my EC2 instance object in the Kubernetes cluster. It was pending. It did not delete it until the actual resource on Amazon was cleaned, and then the finalizer was removed from my object, and then essentially the object was actually deleted. So this is how you will be building an application. You will test this locally, you will build it into a container image, and then you will ship this to your different clusters that you want to deploy using a Helm chart. Essentially what we were able to do locally is now all happening in your Kubernetes clusters, because the operator should be running in your Kubernetes cluster. So this is what I wanted to show you guys, an end-to-end, starting from bootstrapping the project, then going ahead, building the project, testing it, and eventually making it work. And then we deploy that with Kubernetes and essentially run this in the cluster with all the proper role-based access control, with all the proper liveness probes, the readiness probes, and also the matrix, which is nice to have to see how your controller is really doing. And when everything is good, there's no need to reconcile. All is happy. So I think this makes a lot of sense to write your own operators. And I want you guys to try this out and see how this works. And let me know if you have any questions. And I'll be happy to help. And let's move on ahead. All right. So the code for building this operator for the cloud that manages your EC2 instances is now coming to an end. And I have to admit, it's quite a lot. But trust me, what you have just done with this course is that you have actually understood one of the most advanced concepts in Kubernetes, which is the Reconciler, which is how to write applications which are self-healing, which is how to write an operator. While you know the basics now, while you know a very good understanding of how to work with operators, there's no limit to it. Think of this course as a logistic that makes you, that enables you to go ahead and build cool stuff that runs on top of Kubernetes, not just using container images to run on Kubernetes, but rather software that runs on Kubernetes and manages your other infrastructure, which is what we did with Amazon. You might be using Azure. Try to make the developer's life easier by managing resources using Kubernetes on Azure. Maybe you're doing this on GCP. The sky is the limit for you now. Now, you not just know how to use Kubernetes, but you also know how to write applications which are native to Kubernetes that manages your different other environments. So you know how to work with the reconcile loops. You know how do you design the API endpoints. You know what is a controller logic is. You know what the integration looks like when you're working with cloud. And you are very much applicable now, or you already are probably working as a platform engineer. You might be a site reliability engineer. You might be a DevOps engineer. But now you know how to extend and expand on Kubernetes. Kubebuilder as a project, we have looked into good detail. In this course, we have really struck the nerve of using it to create a production-ready Bootstrap operator. But I would not say it is right now production-ready. When you build an operator, you run it, it fails, people complain about it, you refine that, and eventually it becomes a production-ready. But you have the tools now to go to that journey on yourself. Next, try to build your own operator. Try to extend this particular operator to have the metrics available. Try to write your own operator that manages the S3 buckets now for people. Try to write your own operator that manages EFS file systems on Amazon or maybe anything else. No, it doesn't have to be limited to the cloud. So go ahead, have fun. Have fun building new operators and have fun building new tools that runs on top of Kubernetes. And if you have any questions, let me know.